embodies special relativity. The Biot-Savart law was written back in the 1830s, and it embodies special relativity. It's built into that equation. Just by changing the phase angle of the electron, we call that torsion, creates the quantum tunneling effect. And of course, the outside of the electron is, of course, what I call the Higgs field. Okay, so I came up with, applying torsion, and you can apply torsion to various components that we find in equations here. And all that is Euler's formula, okay, applied to the moment of inertia, angular momentum, the energy, the mass of the electron. So that's done in this slide here. The standard model of physics is destroyed. This Russian fellow wrote this paper, and he shows that all particles in the accelerators that are known can be replaced with fast-moving electrons and protons, which are stable fundamental particles. So he's saying all the artifacts that were discovered in these particle accelerators can be explained as electrons and protons. And of course, in Todd Hutchison's universe, there's really only one fundamental particle in the universe. The rest are just manifestations of the virtual particle flux and electrons, with positrons being a time-reversed charge of the electron. And that is my presentation. That's what I presented today. And so there's our website. I'm with ISA Industries, and that is my presentation for today. So I want to thank Tim for giving me this opportunity.
Wonderful. Well, Bill, before anything else, let me thank you. That was an amazing presentation. Absolutely amazing.
Well, it's real. What can I say?
Yeah, well, it was wonderful to see such an in-depth run through on things, and and being able to connect all of those dots. So before we do anything else, I am not going to unmute everybody, but let me put it on gallery view, and let's all give Bill an enormous applause.
Great job, Bill.
Thank you.
Yeah, again, absolutely wonderful. So let's move into our question and answer. And let me see if you're, okay. I'm going to remove the spotlight from you. And so in chat, go ahead and start putting your questions in the chat if you'd like. And then I should go probably to Hector Serrano, who he mentioned a couple of things. Hector, did you want to, okay.
Yeah, there I am. No, listen, in our own research, which is totally different than yours, and by the way, great presentation, loved it. In my own research, I was saying that we actually saw exactly what you talk about. So if I may suggest, for a simple experimental, possible experiment for you is, we rented the same thing that NASA was using for gravity shielding, which is where actually we got the idea from. We used the same kind of gravity meter, which they have way better ones now. But the Lacoste-Rumbic gravity meter, it was sensitive enough that it actually detected a decline in the, every time we energized our system, our device, it actually detected an actual dip in the mass, which obviously the rest mass couldn't have been changing because it was a closed system. So we interpreted that to be a change in inertial mass, or a change in, and it was a negative change. It was not a positive gain. It was a negative. It was a dip. And as long as the system stayed energized, we saw that. The system was Faraday caged, good distance. So it's something to think about if you guys want to see if experimentally you can demonstrate that if what you're saying is true and what you suspect is true, then these meters are sensitive enough in theory to actually see something.
Right. Right. Yeah. Yeah. You'll see a change in mass. You know what Tom Bearden talked about back in the 90s. Um, he says that, you know, the scalar wave, it penetrates everything.
Oh yeah,
Okay? You really can't shield it, you
it's
know.
true. That
Right.
we also
Right.
observed that.
Uh-huh. Yeah, because it's, you know, it's this pumping action, okay, that you get with these type of systems,
Hmm.
and it penetrates everything.
Yeah.
And so, like what we did with our PCM systems is that you send in a positive energy wave, and you get this reflected wave coming back of of the time reversed of what you're putting in.
Right.
And so we see this large power reduction. And of course, that's what's reported by all these other researchers as well. You know, we
Yeah.
see Nikola Tesla, we see Stanley Myers, Floyd Sweet. They all reported a big reduction on the input side of this.
Yeah. We observed we observed similar things. Basically, what we observed was the amount of thrust per unit power was ridiculously better than anything that you could conventionally approach.
Right,
So,
right.
and the kind of explanation you're talking about here is along the lines of what we have observed experimentally. And keep in mind that almost everything we've done has been strictly experimental.
Mhm. Right. Now Tom Bearden mentioned back in the 90s there is that when you see large scale free energy effects, you'll also see large scale gravitational effects as well. Okay.
Okay.
So the idea is to improve the efficiency as high as you can get it,
Mhm.
uh, and that you'll see a large scale anti gravitational effect occurring as well.
Hmm.
And I suspect that's exactly what's going on. You know, if you were to use mercury or even using opposing magnets as well.
Okay.
There was some research done back in the 50s. Bill Lear. I don't know
Oh
if you
yeah.
ever heard of Bill Lear and
Yep.
Learjet.
Yep.
Yeah, he
Absolutely.
sponsored a researcher by the name of Larry Wilson.
Okay.
And Larry Wilson in his lab, he built a system using counter rotation.
Okay.
I figured, well, this is maybe something that the Germans were doing with the Nazi Bell device. You know,
Hmm.
it's counter rotating opposing magnetic fields that breaks the entanglement that you have, broken entanglement,
Right.
which gives you this anti gravitational effect, and that when you start to rotate the system, amplifies the effect. And so Larry Wilson, he built this device, and it turns out that this one guy that gave presentations at the conference was a kid at the time back in the 50s, used to hang out in Larry Wilson's lab,
Oh, nice.
saw what he was doing, okay, with this counter rotating magnet system. And he was saying that although he didn't see it, he did report that it floated off the ground, okay? It was
Well,
just counter rotating magnets.
now, Bill, if I can jump in. So our next question, Hector, let me mute you back out. Our next question was Mark Fiorentino. Now, you were talking about torsion just a moment ago. Mark had asked, mechanically speaking, how do we apply a physical torsion to the electron? Mark, you with us? Do you want me to unmute you? If I can find you. There we go.
All right.
Okay.
Okay, there we go.
Yep. Yeah, just the question I just asked. Basically, I'm trying to figure out and visualize how you're accomplishing this rotation of, or torsion reaction to the electron.
Right. Yeah, you set up opposing field action. Okay. The magnetic field has to be in opposition to one another. This is where Tom Bearden he spoke about opposing fields, where you take the cross product of that opposing field action. And when you do so, you end up with the zero vector. The problem is that you cannot apply Heaviside math to this. Okay, anything that's related to Maxwell equations after they've been simplified using Heaviside's equations, you cannot apply that and get an answer to what you're looking for. Okay, Tom Bearden used quaternion math to expose what's really going on in that system. And so what we're dealing with here is what I call it a torsion field effect. So if you take two opposing magnets and you force them together, the physicist would tell you that, well, it's just field cancellation. You know, it's your zero vector that's coming into play here and nothing else. Well, there's nothing else in their equation, okay? But then if you go and look at Tom Bearden's quaternion math solution, you find out that that zero vector has structure in it, okay? It has a real scalar component associated with it. So you're not just canceling the field, you're setting up this, it's a system that's under stress. See, and that's why in general relativity, you know, you have your tensors, your stress tensors, okay, in place there, because you're dealing with a system, a static system that's under stress, okay? And that's what Tom Bearden emphasizes.
So then doesn't that mean you would have to have a real existing ether for this to work?
Well, yeah. You can't have something that's empty and you're trying to do something like this because you need something to transport, okay, what's really occurring there. And so that's why I say that what physicists say is an annihilation and creation process is completely flawed. Okay, there's no such thing as annihilation and creation events. Everything is still there in the ether. It's just that you directly measure it. Okay, so if you have this mass cancellation effect going on with the virtual particle flux, is that virtual particle has no mass associated with it, but it's still there. You know, it's a system under stress. The thing is that the physics that we have today isn't going to tell you that, okay, that there's something there because it was taken out. You know, Heaviside, he took out all the quaternion components through his simplification process. And this is why Tom Bearden says you cannot equate electromagnetism to general relativity. You can't do it. And yet we see physicists like Sarfatti or Helputov trying to equate electromagnetism to general relativity. You can't do that because the math in the Heaviside math tells you that there's nothing there. But yet the quaternion side, when you look at the complex side of things, tells you, yeah, there's something really there. Okay, you have the stress field that's really there. And of course, you have to have an ether to be able to transport that stress. And the ether's there. You know, it's there as virtual particle flux.
Okay, well, Bill, now let me jump in. Let me go to actually, so let me go to Eric Hermanson, and then I'll go to Jeremy Reese after him. But so Eric was asking if you could put up the voltmeter slide again.
Yes.
And Eric, do you want, if I can find you, there we go. Do you have a question, sir?
Sure. Thank you. Hi, Bill.
Hi.
Yeah, I'd just like to see the, because I missed the first half of your presentation. I apologize. And so some of these questions might not be correct, but I guess the first one is the input. So our the input power is the output power is almost 4 times greater than the input,
Right.
and so that is usable wattage.
Yes.
In other words, I mean,
This is,
can you charge a Tesla
well, you
Tesla with
see,
it?
I have see on the right side of that picture, you just see a little sliver of it. That's a programmable AC power supply.
Okay.
And what I can do is sweep through the frequency to find out what the resonance is of this split flux transformer with the capacitor. I can find out what the a resonant point is. And that's the point of least power being supplied to that transformer and capacitor network, okay? And it's right around 200 hertz. That's what this is tuned to, okay?
Okay.
So at that tuned frequency is where you start to see the amps. You know, as you sweep your frequency, you know, maybe you're starting off at 500 hertz or something, and you'll see that the current is actually very high. You know, it could be like an amp, maybe 2 amps. Okay.
Mm-hmm.
So as you start to lower that frequency to that resonant frequency at that point, you'll see the current start to drop.
Okay.
Until you reach your resonant point of minimum current here, and that's what we're seeing here, a 0.22 amps.
So you are resonating with the an LCR circuit where the capacitor is
Right.
C. Okay. Now,
Yeah,
so
it's basically an LC circuit.
there's no resistance at all. I plug these numbers in, and I see about I didn't do it right. It's about a 30 ohm resistance. Now, so is this power?
Well, there's no resistor there. You know, it's just an LC
the wires,
circuit.
So what are the gauge of the wires? Do you know? The wires will have resistance.
Oh, they're just what you see there are just the normal cabling.
Okay, so
Okay. That's all that's there. Just
maybe 20 gauge. I don't know.
Yeah, they're just jumper cables.
So those will have resistance, which means that your power output is potentially higher. But what I'm asking, I have the two questions are: is this true net output, over input, where you can literally use the power to power a load, for instance, to charge up a Tesla car with one quarter of the necessary energy input?
Well, if you set it up as an LCR circuit, okay, where you put a load on it as well, yeah,
yes,
it's still over unity. Okay, it's still over unity. We still see more power out than what we're putting in.
Okay, because like you can go right to Elon Musk. Go ahead.
Oh, yeah, the patent that we filed covers a DC charging system.
Okay.
Okay, that's operating this this LC circuit in switch mode. Okay, so the idea is to run this at a fundamental frequency, a resonant frequency, this LC, in a flyback configuration where we see maximum or minimum input power, okay, but maximum output power.
Right. So does it take time? How long does it take to get the, I don't know how you can get it. Like, how long does it take to get to steady state and to get this power multiplier?
Right away. You know, it runs right away.
Right away?
Resonant frequency, which is right around, this particular circuit here is right around 200 hertz.
Because, the capacitor is going to be charging up and so if it takes a while, so the capacitor is an energy storage device, and then if it's connected to an inductor, then the current will go between an electric field and a magnetic field. It'll resonate back and forth, but the circuit is still going to be a charged, it's going to store energy. And so what I'm asking is, how much energy, do you know how many joules of energy are being stored by the LC circuit?
Well, it's very small. The joule energy is very small, but in this is just a demonstration here.
No, I understand that, but what I'm worried about, I mean, I'm not worried about it. What I'm thinking is that you may be charging up the capacitor, and then, however, though, if you connect it to a load, you might find that the capacitor will discharge and your load will gain energy, but then you'll have to put an equivalent additional amount of energy in. In other words, you won't have a net multiple of output energy. Maybe I'm not understanding. I'm throwing it out as a possibility.
Yeah. Well, see, if you look at this circuit here, okay, the using a fluorescent tube, is that we're running this transformer in a flyback mode. And so, I mean, it's kind of similar to what we're doing here, except rather than having this negative resistance here we would have the transformer as the split flux with two converging output coils. But we're still running it in a flyback mode. So you're putting energy into it, and then the energy we get out of it is in this flyback configuration, but it's through a capacitor. Okay?
Oh, so there's two inductors, not one.
Right.
So it's
So the inductors have to be
an L2C circuit.
Yeah. See, I don't really show that in this slideshow here.
Yeah.
I mean, the second
but
inductor is right there.
Sorry, I should mention we have a bunch of other questions stacking up.
I know. Can I ask one that's really, really quick one? You said negative energy is coming out. Can you explain what that means? And does that just mean it's out of phase, or because I don't know what negative energy truly means?
Yeah, it's this right here. This right here, a PCM resonator.
Mm-hmm.
See, we're doing, if you look at the PCM resonator device, it's essentially the same thing as the typical device above. I mean, in reality, you're still putting in a kilowatt. Okay, to get a kilowatt out, you still have to put in a kilowatt. But what's being reflected back due to this pumping action that we have going on in the PCM resonator, okay, you get this reflected energy wave coming back, and that adds, okay, to your input wave. This is why.
All right, so I mean, what's coming out are just electrons, though. I mean, like there's none of this like negative. I mean, some people talk about negative energy in a different way, but it's.
Yeah, well, it's a time reversed replica wave. You find this in optics. I mean, this is for real, okay? But it's been very well studied in optics and acoustics of this phenomena, is that you have a time reversed replica wave being reflected back, okay, to your input source. And that's what we have. And here, okay, this is your phase conjugated mirror, okay, your PCM, and this shows the waves coming in. Wave 1 and wave 2, those are your pump waves, Okay, and this is what creates the stress in your nonlinear medium. Yeah, it has to be under stress in order to get this phase conjugated component to reflect back to your input. So your output is still, you're still outputting a kilowatt, okay? You're inputting a kilowatt, but then the reflected wave that's coming back is like what, 999 watts coming back? And those two waves can add, okay? Those two waves add. And when they add, you can have, when you read your meters, okay, when you read the power coming in, you say, gee, I'm only inputting a milliwatt of power and the output's a kilowatt. You know, what's going on here? Well, this is this transverse replica phase conjugated wave that's coming back. And this is why we see very little power coming in with a whole lot of power coming out.
Okay, thank you.
Okay, now this is well known in optics. This actually occurs in optics and acoustics.
Bill, if it's okay, let me go to Jeremy Reese. He's had his hand up for a while. Again, I should apologize. We have a kind of a pile of folks asking questions. So let me go to Jeremy next.
Well, everyone's trying to understand this stuff. You know, it's tough. It took me 20 years.
Hey Bill, thanks for presenting. Look, I didn't get the message in time, so I only caught the tail end of this. So I'm piecing it together, and we are live on my YouTube channel now. Finally, I was able to get the stream up for the last probably like 5 or 10 minutes of your talk. So a lot of people are just tuning in live for this. We have about 60 people watching. I was watching, and a couple questions popped out for me is the whole thing of negative energies. What do you mean by when you say this thing creates negative energies, and how are you measuring this?
Well, this is, you know, I'm not inventing anything here. You know, I'm kind of standing on the shoulder of giants, and to me, a giant in the field would be Tom Beard. Okay, so I kind of picked up on what he was talking about, and believe me, it literally took me years to figure this stuff out. Okay, what's going on here? And this whole thing about negative energy, it is well known in optics. Okay, about a transverse electromagnetic wave that is a replica wave of what you put in. So W3 is your standard wave coming into this medium, and that what's reflected back is a time reversed replica of what you put in. And those two waves, they add, okay? They add. And when they add, you end up with something that looks like this. Okay, you have these two waves. One is your time forward input wave of, let's say, a kilowatt. Okay, let's say that I'm inputting into this device a kilowatt of power, but what's being reflected back, okay, through this device is a time reversed of that kilowatt coming in of about a little bit less, because you're going to have losses in your system. Okay, all systems have losses. So it could be heat, you know, the medium itself, eddy currents, whatever inside your device. You're going to have losses.
Okay, now
so
Bill,
what's being reflected back could be 999 watts of power.
Bill, let me go next. And again, I should apologize. I'm trying to kind of burn through these. So Todd Desiato had he actually kind of a bunch of questions wrapped into one. Todd, are you with us? Let me have you ask this one yourself. I'm not sure if I can find you in the list. You have to unmute though.
Yeah, hey. How's it going? The device you're talking about is a it looks to me like a ferroresonant transformer. I used to design these and UPS inverter systems that drive ferroresonant transformers. So when you hook the capacitors to the coils like that, you're driving the capacitor into a resonant with the inductance of the coils, and then that resonance builds up to a maximum depending on the flux density of your interlinking core. So once that starts to saturate, the voltage doesn't go up anymore on the capacitor. But if you measure the current on the capacitor, it's very large. The VA, volt amps on the capacitor, is very large, but the watts are 0. And so when you tap off the transformer to get a load, that's when, well, backing up a second, when the capacitor is in resonance and you're feeding it, the VA on the capacitor is very large, but the watts are 0. And yeah, that waveform transforms backwards to the primary side where your input current goes to 0 because your watts are 0. But you have this huge VA stored energy circulating in the capacitor. Well, then when you tap off the transformer to draw a load, you're going to be limited by whatever your transformer can handle and the capacitor can handle. And then at some point, the watts is going to completely collapse the resonance of the system. If the resistance is too low, it'll change the inductance and your resonance circuit will fail. But at no time does the watts output exceed the watts input. The VA on the output could be much larger than what you measure for watts on the input. So without that phase angle in your data, it's meaningless. And I don't mean to be insulting. I understand this intimately.
Okay, well, this was why we operate these transformers in a flyback mode.
Doesn't matter. I've run them in full bridge, half bridge, push pull. Doesn't matter. This is what's going to happen.
I would agree with Todd, and it sort of he kind of answered my question for me in the next part that I was going to ask before I got cut off, and that was that these flyback converters, it's basically you're only changing volts for milliamps in these buck boost converters. So there's no free energy out of it.
Yeah, whenever you're dealing with the resonance circuit, you have to be extremely careful to measure your phase angle between the voltage and the current. Just measuring volts and amps is insufficient because without the phase angle, like you said, you're measuring it, you're describing it perfectly. You've got a huge VA on the output and your input current goes to 0. That's the way it works because you've got all this stored energy in the capacitor circulating. Okay, I don't want to take up any more time. Thank you.
So,
Yeah, this is the actual test data of what we see here.
another question I would have is the output being hooked up to a oscilloscope so you can see the actual waveforms? And are they a clean AC?
Yes.
Also had a question from Greg Chase. We are doing this live on my channel as well. We got started from the very beginning. And he wanted to know, one second, does Mr. Alek know that inertial drag changes along the gravity field vector of a planet compared to open space? He's asking about the gravity field vector of a planet versus open space.
Okay. Do I know anything about that? No.
Okay. Also, I wanted to ask about the ARV that you brought up earlier, the spinning aluminum disc and the coil around it. What do you think that component of the ARV diagram is meant to produce?
Okay, that would be right here.
Yeah, because that's something that we're actually working on here in the lab. I have an aluminum flywheel and an electromagnetic coil and spun it up, and we were looking for weight losses and stuff. But what are your thoughts about that specific component of the craft, and how does it operate within the craft theoretically?
Okay. Yeah, see, my read on all this is that, when you look at this drawing here, okay, you can say, okay, well, we have a Tesla coil in the center column, capacitor plate on the bottom here, and it's producing a very high voltage flux field, okay, around this craft. But the thing is that there's nothing here to keep it stable in flight. And that's where I feel this aluminum flywheel, okay, would keep this craft stable. But the thing is that you're still going to have, what they call a propeller effect. The craft is still going to rotate in the opposite direction of rotation of this flywheel. So you're going to have this propeller effect occurring here.
That doesn't make any sense, because if you want something to stabilize a craft, you use a heavy metal like iron or steel or something, or tungsten even. I mean, you can use the aluminum for the center part of it, where the mass doesn't make that much of a difference. But if it's really a flywheel, and for stabilization, like they have on boats, they use a very heavy metal and a thick bar on the edges in order to maximize the stabilization effect.
Okay.
And if you had a problem of the rotation, you'd have two of them, counter rotating.
Right.
So that theory doesn't make that much sense. I was going more on the lines of Frederick Alzapon. He said that it can induce a state of dynamic nuclear orientation by pulsing the electromagnetic coils, and that's something that we're working on here in the lab, and I'll show you that a little later.
So you think that would stabilize the craft?
No, it would make the craft weightless or close. It's one of the key components to what makes this craft fly.
Okay.
Okay, well, Mark, let me go to Jeremiah. Jeremiah, are you with us?
Yeah, I'm here.
Okay.
And I have a few questions for you, Bill, about the test device that you built. So if you want to shoot forward in your slides. So the device that you're measuring in order to look for the effects, the high energy out versus energy in. Now that's a PCM system. I was wondering how these components play into creating effectively an electrical version of a phase conjugate mirror. I mean, what part of this is creating this phase conjugation? I guess I was confused by the physical components versus the concept that's in place. I just didn't connect how these components are producing that effect.
Well, the output gain of this is controlled by how balanced these output coils are. Okay, to set up a converging network, and that the inductance of these output coils actually they subtract. When you hook them up to a meter, the output coils, the inductance subtracts.
So you're effectively you're saturating the magnetic material there. I'm guessing it's laminated iron or some kind of transformer metal.
Well, it's a met glass material.
It's a met glass. Okay, so it has a really high permeability, really high flux capability. Then,
right?
Is it fast material?
Oh yeah.
And I'm guessing it also has a really strong BH curve transition where it goes through saturation and has these nonlinear effects.
Yeah, it's very good material. It's made by Hitachi, and it's called met glass. And
yeah, I've heard of met glass.
Tom used this material quite a bit in his research.
In his Meg, right?
Yeah.
Okay, that makes a lot more sense
The
than how
Meg
you're
is to me, the Meg was a switched reluctance type device, which I think was a departure away from these PCMs.
So this device probably wouldn't work then with standard transformer lamination iron. Then it would have to have a nonlinear
Oh
type
no,
of
it still
magnetic.
works.
It
No,
does.
it
Okay.
will work. Oh yeah, yeah. I've used on this device here permalloy. Permalloy works quite well as well.
By magnetic zinc. Yeah, that is a good material too. I have yet to pick up a small spool of that stuff. I was looking for some 1-inch strip, but they won't sell it to me directly unless I buy 500 pounds of it. So unfortunately, I have no idea where to get this stuff. Whatever you're using there, though, I might want to ask what material that was and how you got it in such a small strip size in a small quantity, because that would be very nice to work with for a variety of other applications relating to this technology.
Right. Yeah, yeah. It's made by Hitachi, and it's met glass material.
All right, awesome. Well, that helps clarify what's going on then. Thanks, Bill.
Mm-hmm. But now, I operated this resonator as also under load as well. And so it's still over unity when I put a load on this.
That's pretty fantastic.
Okay, well, so let me go to Sean next. Sean, you've had your hand up for quite a while, sir, and I should apologize.
Yeah, no worries. Could you explain inertial leakage a little bit more? And have they found a way of preventing it?
Okay, that would be this fellow here, Bob Boyce. Yeah, he approached me at the Extraordinary Technology Conference back in 2016. And he said he was hired in to solve this problem of inertia. He called it inertia leakage. And it came about as not having a perfect field around the device. So what happened is that when the device would lift or float and you make a rapid acceleration, if the field is not consistent or it has holes in it in the field, that allows inertia to leak into your machine, your ARV. And he says that it would ultimately kill the pilots. And so his job was to fix this problem of inertia leakage.
If I could jump in real quick, and I apologize, Sean and Bill.
Yeah, no worries.
It sounds like this would apply when you say ARV in this context. This would apply to any kind of vehicle like this, right? So this would be your TR-3B or your, God knows, your stealth blimp, your UFO, any kind of vehicle that has some kind of inertial modification will probably have the same potential issue, right?
Right. Mm-hmm.
That was why I really wanted to bring it up, because I figured that'd be very important. So thank you for answering that.
Absolutely. Okay, so let me see who is next. I'm scrolling through our questions. Let me see. And so there's Ben McMahon. A lot of these are kind of been answered already. Jeremy, did you have another question?
Yeah, I think I'm understanding a little bit better maybe what's going on with Bill's machine now. Someone pointed out in the chat that the analogy of that third coil being like a swing, and that, a swing, if you hit it with the right resonant frequency, you can keep pumping energy into that swing. And if you can keep pumping energy into a swing like that, you can easily pump it up to energies where you can get you can go over the bar, so to speak, and that's when you get nonlinearities, and that's where our conventional laws of physics and stuff break down. Is that would that be a good description for the layman out there of what's going on?
Oh, Bill, and that would be so. I think what Jeremy was asking was, yeah. Okay, sorry about that.
Okay. Well, See the pumping action, if you look at the split flux, for example, the pumping action occurs on the input side of this. You have a primary coil on the input side, and then you have two output coils. And then you see that there's two met glass cores on your input side, and that's your pump. That's your pumping action, along with your signal wave coming in to this. It's also creating a pumping action of flux in your system here. So that if we go to this diagram here, your wave 1 and wave 2 would be your flux action occurring from the primary side, creating this wave 1 and wave 2 of your pump. And then the input is your input power into this device. And so you get something that looks like this. Right here. You get this, this reflected wave that comes back out, which reduces your input power.
And do you have a description of the boundary conditions for that reflection and transmission coefficients?
It's really a function of how these output coils are balanced. When I go and measure the inductance of the output coils, one might be 31 millihenries and the other one might be 30 millihenries. Okay, so they're not perfectly balanced at all. And so when you go and operate this this coil arrangement, you see that the inductance, the overall output inductance drops to maybe 10 millihenries. And that's due to the imbalance of those two coils. Okay, so if they were perfectly balanced, you wouldn't have any induction at all. Okay, and in a way, that's what you're really looking for. You know, in order to increase the efficiency of this device, you want the output coils to be as closely balanced as possible. And that's what would give you the maximum amount of efficiency in this type of system.
Awesome.
So,
okay.
So all that would really do is just increase the negative energy component being reflected back, because you want to get your input power as low as possible. But if your system is unbalanced, then of course you're going to have not as much negative energy coming back into your circuit, and that's why we end up with something that looks like this on your input power versus output power, because the input power, the input side should be as close to zero as possible. So your input current should be close to zero. Okay.
Oh, Bill, so let me go next. Let me see. Let me go next to Jean-Francois Genest. Jean-Francois, let me see. And he was asking, well, sir, do you want to ask yourself or? There we go.
Very quickly. So you said that you are positive in energy and that you have a kind of a creation of energy in your system, even when it is loaded. Did you try to loop it back in order to have kind of a perpetual motion?
What was the question again?
Oh, sorry. He's asking, have you ever tried to feed back the loop to create kind of perpetual motion? Basically have it feed itself.
Well, that's not the way these devices work. You have to have an input power source and then output power as a load. And the way that these things work is Okay, with this diagram here, let me put this on share. Okay, yeah, you see with this diagram here is that you're still inputting a kilowatt of power, okay, in your typical device, and you're driving a load with it. And so we're all familiar with these type of devices. And then of course you have some loss in your system. But with these PCM resonators devices, what I discovered was that you're still supplying a kilowatt coming in, all right? To drive a kilowatt load, you're still like a typical device. But then but then with this PCM resonator technology here, you have this reflected component that comes back on the input side to subtract what you're inputting into your resonator device. So if you're putting in a kilowatt of power, you might be getting back, let's say, maybe a negative 500 watts. And so when you add the two waves, okay, if you have a kilowatt coming in and 500 watts coming back out, you're still inputting 500 watts. And that's what you're going to read on your meters. Your meters are going to read 500 watts coming in and a kilowatt coming out, okay? But your reflected component's 500 watts.
Let me reformulate then my question. You get more energy output than input. Because
Yeah,
of
well,
your
that's what it looks like, okay? You're still inputting a kilowatt of power.
No, you input 1 kilowatt of power, but you get 500 watts less.
Right.
You're inputting 500 watts.
Yeah, you see that's how these PCMs work, is that you get a reflected component coming back of negative energy.
But what do you do with this negative energy?
It just comes back and subtracts from your input power. That's all it does.
Yes, so if I, to be sure that I understand, for example, if you have 500 watt backs of negative energy, you input 500 watts of positive energy, and your load is loaded as if it received one kilowatt.
Well, you see, if we didn't have this capacitor here and you were doing these measurements, you would not see numbers like this at all.
Yes,
you would still see a lot of power coming in and a little bit of power coming out.
Let me maybe reformulate this. Imagine that your load is a pure resistance and a heater. So if you load 100 kilowatts, 1 kilowatt, sorry, you will have some heat for 1 kilowatt in a specific chamber with no leaks and so on. And so you would input for some time 500 watts on your side, and then your load would dissipate 1 kilowatt of heat. Do I understand well or not?
Right.
Did you test this? For how long?
Well, we tested this as an RLC circuit as well. We put a load on this output. And we still see that we're still over unity when we put a load on this output right here.
Okay. All right. Thank you very much. Thank you. It's clear.
Wonderful. Thank you. Thank you, Jean-Francois. Let me see. Oh, there, Jeremiah has another. Jeremiah, do you have another question?
Yeah, I do.
Okay.
To elaborate on the last question, so there's this thing called effective power measurement, which is if we were to take up the voltage and the current at any given point going into or out of the circuit, and you were to just take that measurement of voltage and current and slice it up into tiny little segments, say 500,000 measurements per cycle, and you were to calculate out the actual power draw between voltage and current at every given point, then you would have your effective power measurement, which is going to be significantly different than your volt amps. You know, your watts and your volt amps are two very different things because one has phase involved in it and the other one does not. So the question is this really more of a way of tricking the meter, or does this device genuinely consume effective power-wise less than it's generating on the output?
Okay, well, let's go to see if we hooked up our meters to this, because our meters are just going to read RMS.
Well, right, but your meters can't read effective power,
voltage.
which is why, you know, anytime you read an RMS measurement with a system that is out of phase, you're going to get a really screwy number, especially with the standard power meter. So power meters will lie to you about all these types of measurements, which is why I'm asking, have you done anything beyond using a standard power meter to specifically take into account the phase difference between voltage and current and know that that your measurements are accurate?
Well, just that we hooked this up under a load. We put a load resistor on the output of this.
Right, but the trouble is that if you're using that type of equipment, you may be getting erroneous test measurements, and we've seen this all the time in the calibration industry. Your power meter may not be capable of taking the type of measurement spot for spot and splitting up into multiple different segments where voltage and current are compared to each other, not during the entirety of the cycle, but one measurement at a time, several thousand or several 100,000 times per cycle to guarantee you have effective power measurements correct, and that you're not just.
Jeremiah, it sounds like, and I think this is kind of building off kind of, you know, I think other folks have asked about the load. So it sounds like probably a next step then, you know, would just be increased testing, right? Test this on a variety of different loads. Well, what are some loads that you might suggest, recommend?
Was that to me?
Yeah.
Oh,
yeah.
It's more on the input side. It's not so much on the load. The load we can easily measure, as was stated, through a resistance that we measure the amount of dissipated power. Measuring the output power is the easy part. Measuring the actual input power where your voltage and current are out of phase is much more difficult. And for that, you need something like a DPO 5000 or a 6000 series oscilloscope, which has effective power measurements built into it. And then you need to monitor the voltage and current on two separate channels and have the scope do a mathematical calculation between those two, giving you a comparative analysis. But a regular watt meter is not going to have that kind of resolution, that kind of sampling capability. It's going to take average measurements over a longer period of time, and as a result, you're going to get erroneous readings on the display.
Okay. But I mean, and then obviously you'd be able to, like, I think Jean-Francois mentioned putting this on like a heater too, right? So
yeah. Resistive load is effectively a very good way to guarantee that your voltage and current into that load are never going to be out of phase because of inductance or capacitive effects. It just eliminates that out of the equation, which is a nice way to test the amount of power you're actually generating.
Okay. Yeah,
that's something I was bringing up before. If you're actually changing the waveform, then it's much more difficult to read the total watts input because with simple DC, it's amps times the voltage, but with AC, you're assuming that you have the same waveform on both sides in order to use that same equation. But if the waveform changed, that equation's out the window. You can't use it anymore to determine the watts.
Okay. Well, so I think, Bill, we're almost out of time. I want to thank you again very, very much for your presentation. Thank you for spending all the time for the Q&A session. So again, everyone, let's put our hands together for Bill and this incredibly detailed presentation. Thank you again, sir.
Thank you. Thank you for giving me the opportunity here.
Oh, absolutely. And thank you for joining us, Bill. Okay. So let me see. Let me go. Let me see if David Chester is with us. There he is. There, right in the nick of time, too. Okay, and David, let me find you on our list. I should apologize. This is quite a lot to scroll through.
Yeah, for real.
Hello.
No,
yeah,
like
David, perfect.
Hey, how's it going?
Wonderful.
Coming in on time.
Yes, thank you very much, sir. Okay, well, if you're ready to present, let me hand it over to you. And if you want to share screen for your PowerPoint, I think you should be able to do that. I'm going to mute myself out now.
Great. So can everyone see my screen?
We can see it.
Awesome. Awesome. Thanks for the feedback. All right. Awesome. Well, is this showing the main screen? I think I need to switch the display settings. There we go. Is that better for everyone? Does everyone look like they're seeing the right screen, the big one?
Yeah,
I see some nodding heads. All right,
Yep.
Great. So I'm gonna move this over here, and then I'll get started then. So thanks to Tim Ventura for giving the invite for this talk. Today I am going to discuss anti-gravity in the most general theory of relativity, and I'll talk about what I mean by that. And so I got a PhD in theoretical physics, and now I work at quantum gravity research. So I was asked to talk about anti-gravity and simplify it for the level of engineers. So I thought about what that meant, and I thought about it in this term. So if you think about what an engineer is, we have mechanical engineers. They often study Newtonian mechanics and have to learn a lot about stress and strain. We have electrical engineers. They learn about Maxwell's equations and circuit theory. Material science, they are engineers, and they need to learn some quantum physics. So aerospace engineers, they really need to learn all of the above. So they need to know mechanical, electrical, a little bit of material science, fluid dynamics, hydrodynamics, thermodynamics. So if we're talking about being serious about anti-gravity and we want to simplify it for engineers, what that means is we need to be able to teach quantum mechanics and general relativity to engineers. So that is what I'm going to try to do today. So just to provide a little bit of background about myself. So I mainly study quantum field theory and general relativity. And quantum field theory is the most successful theory for describing all of the forces of nature, quote unquote, besides gravity, but it's actually not as problematic as people say. So it's very successful for electromagnetism, quantum electrodynamics, and also for adding in special relativity. And some of the biggest experiments on the globe right now were the LHC, where they detected the Higgs boson. It obviously got a lot of news, a lot of money went into that. And then general relativity is the other big theory of gravity, and people are figuring out how to quantize it right now. And basically, LIGO is the other biggest experiment in the world, and they recently have detected gravitational waves. So I got a degree in undergrad in physics at MIT, and when I was applying to grad schools, I wanted to use Feynman diagrams from quantum field theory to calculate general relativity. That's what I said I wanted to do when I applied to grad schools, and everyone told me I was naive, but I got into one school because there was a professor there who had already computed these things, and I didn't even realize that people had already done this, but most people in the field didn't realize this, and he was able to calculate gravity from the other forces of nature, the strong force. So that's very curious. Basically, what is the most general theory of relativity? Well, we know that general relativity uses Riemann curvature for its framework to describe curved space-time, but the most general mathematics for general relativity or gravity in general, this differential geometry, there are more exotic types of geometry, and a lot of these are necessary for quantum gravity. And this includes concepts like torsion, coming from Cartan, and non-metricity, coming from Weil and others. And basically, spinors are used to describe matter. And in order to get angular momentum conservation, we need the torsion. And some of these unified field theories right now are using non-metricity. So it's pretty exotic stuff, but we don't need to know all the details of this, but I want to mention this because there are some interesting aspects of this theory that are contained, that have effects related to anti-gravity that are not in general relativity, that are related to some of the things that people in this area are discussing. So I figured it'd be worth mentioning that. So I want to take a very conservative approach to anti-gravity. I want to be serious about it. I want to bring some respect to this conversation. I mean, we have to be very serious when we're talking about doing this because it is very challenging. So if we're going to think about metric gravitational engineering, we have to understand gravitational theory, and we have to be able to work with it and understand how anti-gravity is coming out of it. realistically, we're going to use electromagnetic devices made out of materials, and we're probably going to want to induce some quantum behavior in those materials in order to get the effects we want. Therefore, we're going to have to understand how quantum materials interact with gravity. And I think the best way to do that is to understand how quantum gravity works. That way you understand unified field theory. And if we can understand unified field theory and can look at how Maxwell's equations and general relativity play with, if we know that we have a unified field theory that is decent enough, then we can at least have some confidence in the theoretical framework that we're working with. If we're not even sure what quantum gravity is and we're taking quantum electrodynamics and adding it into gravity and we don't know how those play together, we might run into problems. So my goal today is not to suggest the best way to do it necessarily. I just want to provide evidence to motivate further study of it from this perspective of unified field theory. And I just want to mention, for the sake of humanity, this analysis I'm going to present was only really possible by making friends of enemies. So I've been looking at a lot of different theories and a lot of different people's work. And a lot of times what I try to do is figure out, if there's two people that disagree, what is the underlying framework where everyone can agree and be happy? And so I'm going to show you that perspective today. So just to give you a little possible timeline about how maybe things could work, right? Maybe in the next decade, there's going to be significant progress in understanding quantum gravity and unification. Who knows? Maybe there could be some legitimate textbook that's actually written on how to combine quantum mechanics with gravity to do something like metric engineering for these types of applications. You know, who knows where that'll lead? Question mark. But maybe it'll lead to profit in the future. And I just want to mention that, you know, there's this idea of the Jetsons. They came out in the 60s and they had this 100-year projection in the future. So we're about halfway there. And so I just asked you guys, does it feel like we're halfway there with the technology? Something to keep in mind. So in nature, I guess I tried to pick the least controversial things that I could find that are helpful for trying to understand anti-gravity. One of them is dark energy, because we find that galaxies are pushed apart and it's a gravitational effect. So it seems like that is a natural type of anti-gravity. Obviously, that's not practical for engineering, but it's worth to try to understand that in the framework of general relativity, just to understand how something like this might work. Also, there's this notion of torsion and very high spin densities, creating essentially a finite size for particles. And there's also the connections here to topological field theory. And so it's sort of a type of anti-gravitic effect. And so I think there is also this sort of analogy that you can make between this and the metamaterial effects. It's a little vague analogy, but I figured it's worthwhile to mention just because it is deep physics that is important for trying to understand quantum gravity. So the third topic I'm going to mention at the end is this idea of pumped metamaterials. Mainly, I'm going to present ideas from Jack Sarfatti that I've just seen from email threads. And it just seems like he seems to be the only person I've seen that realistically is addressing the theoretical problems necessary to make something realistic. It's definitely a work in progress, and he's far away from having something realizable, but he is working with a theory that actually provides some hope for something to work out. So if we're going to get into this anti-gravity stuff, we need to know the basics of general relativity. So the first concept in special relativity is the unification of space and time in a space-time. So we have these Lorentzian 4 vectors where time is given this kind of, it's almost like an imaginary dimension, such that when we measure the distance in flat space-time, the time adds this negative effect where space is kind of has a positive length. And then in general, for general relativity, we have curved space-time. So there's this more general space-time metric, g mu nu. And here I just depicted kind of this idea of having foliations of space-time. You could imagine being a particle traveling along a path, let's say in the z direction. And at each moment in time, you kind of have 2 dimensions that are transverse to your direction of motion. So, and you can have curved space-time in general relativity. And that describes what gravity is. So basically what ends up happening is you have derivatives, there's calculus involved in obviously, and the derivative gets enhanced to what's known as a covariant derivative. And this also occurs in electromagnetism. So that's curious. And the covariant derivative involves this connection. And this connection affects geodesic motion and provides a fictitious force to describe acceleration. And this is the variable that goes into the curvature. I didn't even write down the exact formula for curvature, but the connection goes into the curvature. And so you can think of the connection as being sort of the potential and the curvature being a field strength. And so we have these different types of curvature. There's this 4 tensor because there's 4 space-time Lorentz indices here, but we can contract these indices. So we get this Ricci 2 tensor, and we can further contract to get this Ricci scalar. And Einstein's field equations combine the 2 tensor and the scalar with the metric into this field equation where we have the curvature on the left-hand side of the equation and energy, momentum, and stress and strain. The energy momentum tensor is on the right-hand side. So this is going to be all the sources of gravitation, whether it be matter, electromagnetism. And what we're going to focus on at the end of the talk is the coupling between energy, momentum, and curvature, this 8 pi g over c to the 4th. So keep that constant in mind because we really need to get over this barrier. That is the biggest problem, is understanding, let's say we had negative energy somehow. That's not even the biggest problem. The biggest problem is getting over this hurdle, which is what Jack Sarfatti has really been addressing. Sorry, I meant to add some drawings here, but I didn't have time to get there. So why is anti-gravity so hard? Well, basically, we can look at this coupling constant here between matter and curvature, and it's astronomically small. I mean, Newton's gravitational constant is pretty small. And then we have a speed of light, which is pretty big, but that's in the denominator. And then we have it to the 4th power. So we have this huge number in the denominator to the 4th power multiplied by this other small number, giving this extremely small number. So even if we can find negative energy, we're going to need a lot of it to curve space-time enough to have an actual effect. So if we're just tinkering around in our garage, or if we're an engineer without knowledge of general relativity, I mean, you can hope that maybe you're going to get maybe 3 orders of magnitude. I mean, that would be amazing. You know, getting an order of magnitude in increased strength is a big deal. So if we're going to have to get it over numbers like 10 to the minus 43, then we really need to know what we're doing. So what is meant by anti-gravity, this is also important to talk about. I don't mean something like magnetic levitation. What we mean is this anti-gravitic effect would affect light and heavy objects proportionally, because, you know, if you think about a rocket, you're going to use jet fuel. If you have more mass, you're going to need more rocket fuel. So the same sort of limitation occurs with magnetic levitation. So that's why it's not true anti-gravity. So we need to understand what types of matter lead to efficient solutions such that we can control the curvature of space-time itself to get these effects that we want. And metamaterials are probably the best candidate, because metamaterials is just a blank term for exotic materials that have bizarre properties. And to understand how to do this, we really need to understand how electrodynamics and gravity come together. So I'm briefly going to go through unified field theory and particle physics. Honestly, most engineers don't need to know the details of this, but I really do think that the people who are figuring out how to bridge the gap between the science and engineering are going to need to understand some deep stuff that are at this level of difficulty. But I'm going to try to dumb it down for everyone. So we can think of types of anti-gravitational fields just in general that might occur in our universe. And we can see that there's the creation of matter via extremal black holes in supergravity and string theory. And we're understanding how black holes are basically fundamental particles. And the particles, there's this notion of renormalization where the particles actually get an effective size. So we have these point particles, but really we have to realize that they have some finite volume. So you can think of that process as sort of being an anti-gravitic effect that pushes things away to give it that finite size. I find that a little bit helpful. Obviously, this isn't practical, but it's important to understand how this works, in my opinion. And also looking at cosmology, such as the expanding universe, this relates to the dark energy and how galaxies expand. So, I mean, if we have the theoretical understanding to address quantum gravity and these types of effect of, you know, extremal black holes and cosmology, if we have that theoretical framework and it's there and we can apply it to reality, then I think we might be ready to start opening the dialogue for how could we, get realistic anti-gravity effects. So at the end, I'm going to try to get more realistic and talk about this idea of pumped metamaterials. And so basically for a unified field theory, the idea is that matter is sort of made of the same stuff as space-time. You have this unified field where everything is the same object. And so as I was saying, you could think of point-like singularities actually occupying some volume after you consider everything that's going on. So even if you don't study torsion, the topological field theory community also finds the same effects, but these are actually two sides of the same coin. So I say this to say that there's differing opinions where people are studying different fields, but when you stand up above them all and see how they're connected, they're pointing in the same direction. So this is kind of what I'm talking about, where enemies, someone might study topological field theory, not care about torsion and not like that stuff, but they really actually do point to the same direction at the end of the day. So matter is creating these regions of isolation or these voids within space-time itself. And this actually is relevant for thinking about how string theory and extra dimensions work, because we actually think of the entire space-time as this type of brain world, which is essentially a material which is embedded in higher dimensions. So you can think of a fundamental particle as getting an excitation, and from our perspective, it's just a point, but really there's some volume. So you could kind of think of the extra dimensions as being the topological information that is filling that void. That's one way to think about it. So I'm going to spotlight a few respectable scientists in this talk. One of them is Joel Shirk, because he was the co-inventor of string theory and supergravity. And he was the one who realized that string theory was a theory of quantum gravity. So I also mention this because he wrote a paper on anti-gravity a few months before he died, based on a tragic accident. But basically, supergravity with this notion of extended supersymmetry has anti-gravity. It's a fact. And if supersymmetry does exist, you could be skeptical. Is this should we even care about supersymmetry? The point is, even in order for supersymmetry to work, we need extended supersymmetry. So extended supersymmetry is what has anti-gravity. So not all supergravity theories have anti-gravity, but the ones that are realistic have anti-gravity. So that is interesting and it's curious. So maybe we should listen to what these experts in the field are saying. So I'm going to briefly bring you through the evolution of string theory very quickly. So it started off with zero-dimensional points in 4 dimensions. They did some mathematics and realized that there were these nice superstrings that could exist in 10 dimensions. There were these one-dimensional objects. And so they changed the particles of strings. And then they changed their mind. And they said, well, actually, there's supergravity in 11 dimensions. And Ed Witten realized there's this M theory that unifies string theory and supergravity together. And there they use these 2-dimensional membranes that generalize the string. So they're getting away from the point, they're getting away from the string, and now they're going to these membranes. And the story doesn't end there. Really what happens is there's this larger theory above M theory. There's a few different ones, and these are making contact with this 3-dimensional brain membrane, same thing. And there are these notions of F theory, S theory, and recently A theory in 12, 13, and 14 dimensions. And what is a 3-brain? What are we talking about? What are all these complicated stuff? A fancy way to say it's a material. I mean, it's this 3-dimensional object that fills up a volume and it occupies 3 dimensions of space and it's lifted to extra dimensions. So these extra dimensions, it's very simply just internal spaces for charge and associated with other forces. So space-time is associated with gravity. We have other forces, and we need to describe the conservation laws for energy momentum as well as the other charges. And those extra dimensions are just there to allow for this unified conservation law. It's that simple. We don't have to get all mystical about what these extra dimensions are. So type 2b supergravity has this 3-brain, and M theory actually doesn't make contact with it. It's a little convoluted. It's claimed that M theory unifies all the supergravities, all the string theories, but when you actually study it, it's a little convoluted the way it's connected. There's these chains of dualities. So and the superalgebra of M theory doesn't actually contain all the supergravity superalgebras. And the physically realistic ones involve this 3-brain. And so really getting back to this idea of something like an ether, I mean, they're just saying that there's this material. And so it's not that new of a concept. So just to establish myself. So in 1997, this 14-dimensional idea was put out by Ishtak Bars, who's a very serious string theorist. And no one is really, this isn't really something you're going to hear from many people in mainstream media because no one's talking about it. I mean, it has a few citations, but in the past decade, really only me and my collaborators have cited this work. So not even the string theorists who are bad at communicating with the public are talking about this. So the chances of anyone hearing about this are very slim. But I'm going to make it really simple for you guys. So we're in 14 dimensions. How do we describe this if we're in kindergartner? So I'm just going to use addition, multiplication, and I'm going to divide by 2 at the end. So I hope the engineers can keep up with me here. So this theory has 11 spatial dimensions, space-like dimensions, and 3 time-like dimensions. And you follow through the symmetry breaking, and you realize that you can break off 8 spatial dimensions into 3 plus 8. And then the 3 time dimensions, it's not that mystical or complicated either. It's just 1 time dimension with rotation angles for mass flavor oscillations. So in the Standard Model and beyond the Standard Model, we know that there's 3 mass generations of particles, like the electron, muon, and tau families. And I figured out how this is related to the 3 time dimensions. And basically, the 8 dimensions here are related to the 8 charge configurations. And basically, if you're an electrical engineer, maybe you've heard of a Fourier transform. Momentum and energy is conjugate to space and time. And we know that E equals mc squared. So that helps understand why the extra time dimensions are related to 3 mass generations. And basically, charge is conjugate to this gauge degrees of freedom, these extra spatial dimensions, such that we see that really these extra dimensions are just for this unified conservation law of energy, momentum, and charge. So when we look at this theory and you study the spinors of it and you look what matter is involved, you get these 8 charges with 3 different mass states. Okay, 8 times 3 is 24. All right, we can do that math. And then if you look at the particle content, there's proportionally, there's 3 quarks for 1 lepton because you can have a red, green, and blue quark, but those red, green, and blue quarks have the same mass. So for 4 particles, there's 2 mass values, and the 24 divided by 12, 24 divided by 2 gives you 12, and there's 12 different masses associated with the Standard Model fermions depicted here. So see, this is string theory. Really, this is where it's going. It's connected to the Standard Model. I did not introduce any unphysical superparticles. This is reality and nothing more. So here we go, right? So now that we've established the unified field theory, we have quantum gravity, we can now talk about, we can get into the engineering a little bit, but really just remember that we want that simple picture. And basically what happened is Lisi's E8 theory, when appropriately formulated, is really essentially related to appropriate formulation of Witten's M theory, because Witten said M theory is an E8 gauge theory. So we had to make enemies friends here because Garrett Lisi was vague, but he was trying to get some simplicity, and string theorists use E8 a lot, but they missed the simplest picture. All right, so now to try to get into anti-gravity, we have these fundamental particles as extremal black holes. And basically, in order to get angular momentum conservation, they need to have torsion inside matter. No one can get away from this. Everyone tries to hide it. They try to get rid of the torsion, but it has to be there. It's undeniable. Even the supergravity people have it. Even the string theorists have it. And it is essentially an anti-gravitic field. And this is not a perfect analogy, but you can think of the high spin density that sources this anti-gravitic field as being somewhat analogous to this high frequency pumping in these metamaterials. It's a completely different effect, obviously, but just keep that in mind. Just something to bridge the gap. So, and just to remind you what these extremal black holes are, basically, if you have some black hole, it can Hawking radiate, but there are these low, after it radiates all its energy, it reaches some excited state that it can no longer radiate. And those are extremal. And these extremal black holes are essentially fundamental particles. So we have a decent understanding of this. I figured I would just spotlight another scientist. I meant to grab his picture, Nikodem Poplawski, because he figured out how to use torsional regularization and he applied it to QED. And this really helps provide the philosophy for quantum field theory making sense, because he showed that it only requires a finite amount of energy to create an electron. And this has been a problem for decades. So since he's in the gravitational community, not many people have seen this work yet, and it's very difficult mathematics, so he hasn't extended it to gravity, but if this was extended into gravity, it's conjectured that this would help provide UV finite quantum gravity. There's other things that would be needed as well, but there's progress in that direction. So think of this Cartan radius as being the minimal size that the particle gets gravitationally from its own spin that basically creates this anti-gravitic field that doesn't want anything to get close to it. Just it's a little analogous, but we want to have something somewhat similar to that with these metamaterials. I mean, we want to get this craft that creates this bubble around it so nothing wants to come in, and that way it's very easy for us to sort of bend around gravitational waves, because the waves themselves would just bend around this object, because to us it would almost look like we're a point particle, so everything would just flow right through. I mean, that might not be literally what is happening, but I think it's the best analogy that we can get for, some engineers today. So another person I want to just put on the spotlight is Hagen Kleinert, because he's done a lot of interesting work looking at Einstein-Cartan theory, which has this torsion, and he models space-time as a crystal just as an approximation, and he studies curvature as defects and as well as torsion. And so when you think about this perspective, I mean, it's once again suggesting that space-time itself is like a material, right? So to further motivate us to go into metamaterials, I'm trying to point out how, quantum gravity is pointing at this idea that space-time is sort of like a material. And also going beyond the torsion, there's this notion of conformal gravity. This relates to cosmology and to try to get around singularities. So you want this idea of the geodesic completeness. There are kind of mathematical issues with general relativity, and going to string theory doesn't solve them. You need to use conformal gravity. So the string theorist studied conformal gravity as well and figured this out. And this will help with a lot of issues with cosmology. But they also have discussed anti-gravity in this theory. And this theory makes it easier for types of anti-gravitic effects. And a lot of people thought that this would be problematic due to issues of unitarity and causality, but they fix those problems. Okay, and this theory also is magnificent because you may have heard that the Higgs particle is this God particle, but it's definitely not the God particle. If there was such a thing, the Higgs is a false God particle because nobody is describing the origin of the Higgs mass itself. But this conformal gravity theory does that. So what it ends up doing is it turns all of these mass parameters. In conformal gravity, everything is massless. It has to be that way. But you get these scalar fields. And when you study how this scalar field condenses, when you basically symmetry break to low energies, the scalar field takes a constant value and it sets a mass. So it's a gravitational Higgs mechanism. And this is very elegant physics. And so it unifies the Higgs mass, the cosmological constant that is causing the expansion of the universe, and Newton's gravitational constant, all into this dynamical scalar field. And this is very similar to what Jack Sarfatti is doing, because he's trying to add this scalar field to Newton's gravitational constant. So I say all this unified field theory stuff just to motivate Jack's work, because otherwise it might just seem like he's saying something crazy. So in this most general theory of relativity, we'll just go through a brief history. I wanted to mention Heaviside gravity just because a lot of these anti-gravity people, they like to talk about it, but they don't understand the mathematics of it, and they start saying dumb things. So basically, this Heaviside gravity used electrodynamics for gravitational theory, but it doesn't match experiment. Maybe there's a chance it'll work, but I don't think so. And people often point to Hefemenko as solving it. He implied he solved it. I bought his book, I read it, he did not solve it. So we can't just claim that Heaviside gravity is going to give us anti-gravity. We need to go to general relativity. But I want to point out that metric affine gravity contains general relativity with other forces that are equivalent to Heaviside gravity. So even if Heaviside gravity isn't the final gravitational theory, there is some partial truth to this, because it might turn out that this Heaviside gravity term is a gravitational field. However, it's realistically not feasible in experiment today because we still don't understand how it works. Maybe it's theoretical possible, but it's going to be a very weak effect, very, very weak. So we can't really rely on Heaviside gravity to get what we need. Just to talk about more legitimate scientists who have discussed interesting ideas such as space travel. Recently, there's a paper by Maldacena and collaborators where they're discussing this brain world idea, which is what I'm talking about, and they're embedding in higher dimensions. They're using this. He studies ADS CFT holography, and the CFT is conformal field theory. It ends up being related to this conformal gravity theory that I was talking about. And so he was able to get traversable wormholes, so he claims. And I mean, maybe it's a little interesting. I kind of looked at it very quickly and did some back of the envelope calculations. Maybe with what he was describing, maybe he could get like a half of a proton through this wormhole. It was going down 10 to the minus 18 meters is what it seemed like. And realistically, we can't even make experimental contact with that. So we're starting to get people who are thinking about these ideas and showing that it is legitimate, but we're still far away. Well, maybe not. Let's see that. Okay, so everyone talks about this Alcubierre drive because we can get this solution to Einstein's field equations that allows for high-speed travel. And the problem with it is it requires a lot of negative energy density, okay? It's one thing to get the negative energy density, but how do you get enough of it, right? That's the big problem. No one is talking about it. Anyone who, they'll talk about heaviside gravity or general relativity. I mean, you have to talk about general relativity to get here, but I mean, anyone who's talking about these solutions, they'll just make some vague statements and not do any of the mathematics to show how they're getting a strong enough effect. Okay, so we need to now talk about electrodynamics because we need to talk about materials. So Maxwell's treatise is prolific. Obviously, he introduced these electromagnetic fields. Well, he wasn't the one to introduce them, but he really fully understood them and how they all fit together. So he had this electric and magnetic field, and he also had this electromagnetic potential. He had 3 different variables that were all independent, and he had 3 types of energy. I read some of his work, from him himself, and he talks about these 3 types of energy. And today, this is called the macroscopic formulation. Shortly after, everyone was interpreting his work and simplified it, and they have the electric and magnetic field at this time. And then quantum mechanics came along, and then they said, no, the electric and magnetic fields aren't fundamental, it's the electromagnetic potential. So now today, we believe that the electric and magnetic fields are kind of this afterthought, and really this electromagnetic potential is fundamental. But I just want to remind you that Maxwell actually said that all 3 were fundamental. So maybe he was onto something. And so now when we get into macroscopic materials, I also want to mention that in Maxwell's treatise, he pretended the microscopic was like the macroscopic. And then everyone, after the fact, after they didn't have experimental data on cosmology yet, they assumed, Einstein and them, they just wanted this flat, very boring universe that's very static, but we're not finding that. And so since they were hoping for that static universe, they made everything microscopic, when in reality, we need to think about macroscopic materials. So when you do this, you can get this notion of an index of refraction, because the transverse electromagnetic waves, which is light, they can travel at different speeds. If you've ever put a straw in water, you see that the straw gets bent, and that is because of the index of refraction of water in comparison to air. And the light is traveling at a different speed, so it affects how we visualize that. And basically, there's different types of exotic electromagnetic effects that can happen. Some of them to note, far fields only contain these transverse electromagnetic waves, which contain these 2 polarization states. And but we also have to consider near fields. And plasma physics also looks into these sort of noisy, out of phase modes that might be longitudinal, and they don't get into the radiation zone, but they are there in the near zone. So there are these third modes that exist, and also superconductors provide an effective mass to the photon inside the material, which is it's turning on this third mode. So I don't know, maybe Maxwell was onto something when he said there's 3 types of electromagnetic energy. Anyway, so now when we look into the macroscopic electrodynamics of materials, I'm going to suppress all of the vectors. So really the electric field is a vector that points in 3 dimensions, but I'm going to simplify everything for this talk. So there's an electric field E and a magnetic field B. And in vacuum, they have these epsilon naught and mu naught, which are the permittivity and permeability of free space. And these constants relate to the speed of light, which is a constant in vacuum. But in materials, as I said, this speed can change. And what is happening is that there's actually more than the electric and magnetic field in this macroscopic formulation. there's this notion of dielectricity and magnetism, which you can think of the dielectricity as essentially the electric field with adding in this polarization effect. So if you've seen, certain types of metals can get polarized, and like iron filings and stuff like that. So you can see that you can have materials that get this polarization that is in addition to the electric field, but it's only inside the material. And so this dielectricity is important to characterize those effects. And so instead of this epsilon naught, you get this epsilon, which describes the proportionality of the dielectricity to the electric field. And a similar story happens for the magnetic field. You get this notion of H, this type of magnetism, which includes this magnetization M, and that goes into B. So in vacuum, we have epsilon equals epsilon naught and mu equals mu naught, which implies that P and M equals 0. And these quantities they're in the equation for the index of refraction. So the speed of light in materials ends up using these epsilon and mu instead of the epsilon naught and mu naught. And you basically take the ratio here of the speed of light in vacuum to the speed of light in material to get the index of refraction. And I have to say, for the metamaterial story, it's much more complicated than this. Really, these epsilon and mu's are tensors, 4 tensors, and they're relativistic. It gets a little complicated, but if you're already doing general relativity, it's not that bad. So basically, we have these different materials, and you can have different regions. So most materials, epsilon and mu, you can look at this ratio. So if you look at the ratio of epsilon over epsilon naught, we can define this dimensionless quantity epsilon r, and we can do the same thing for mu. So most materials, they're around 1 for this epsilon r and mu r, so they're going to be above 0. But there are these different phases that you can have, and when you have both below 0 or one or the other below 0, you get more exotic types of materials. So we're going to need to keep this in mind. So we have some very interesting materials to look at. We're trying to get anti-gravity, so we need some minus signs somewhere. So before we get into metamaterials, I thought of this very vague analogy. So imagine you live in the United States, you always drive on the right side of the road, right? You just assume everything always moves on the right side of the road. So you kind of build your framework of thinking based on that. Locally, everyone always moves in that direction. And so you can make up these things. It seems obvious. No one can ever drive on the left side of the road. Why would anyone do that, right? It's not the way the laws work, right? Well, you travel across the sea and you realize that in some small locations of the globe, some phase space of all possible materials that exist in the universe, right? You realize that, maybe in the UK or Australia, they actually drive on the left side of the road. And that's kind of what is happening with these metamaterials. You can kind of think of there being some region of space-time where everything kind of tends to flow backwards than the way you would traditionally think. And it's really not, I don't know, you can think of it as negative energy. It's not really negative energy. It's more effective negative energy. So these metamaterials, in general, metamaterials are designed to have specific engineering properties, for whatever application you're interested in. So this negative index of refraction is what we're going to be interested in. And basically, you can think of these different regions. So if you had vacuum and then you have this metamaterial, you can think of there being this energetic domain wall. And this picture matches nicely with some of the conformal gravity way of thinking. It's like you get these regions that are kind of separate, embedded in space-time, and the energy flows differently. So from the outside, it almost appears like it's a point, but really it's taking up a volume. And so it's not really negative energy, because when you're inside, to you, there's no negative energy. It's not like there's anti-gravity for you, right? In your world, in your bubble, there's no anti-gravity. Outside, there's no anti-gravity, but there's effective anti-gravity from the frustration of the boundary, from the transition, the boundary conditions going from the vacuum to the metamaterial. So that's why it's not as paradoxical as a lot of people might think. And you can kind of think about invisibility cloaking, because this stuff, metamaterials have been used for cloaking, and that bends light around. And, that's halfway there, maybe not even halfway there, but that's kind of the sort of idea, if you're cloaked, all the light just bends around. And what we want to do is that rather than for light alone, we want to do that for everything that has energy, for the entire gravitational sector, such that everything tends to want to bend around it. It would be energetically favored to do that. So rather than we don't want a rocket that's going to fight against wind resistance. We want to create something that prefers energetically for it to not participate in the gravitational fields. And so you can imagine inflating and shearing space-time in exotic ways such that energy would tend to want to flow around it. That's the way I think about it, at least. So my next spotlight is Jack Sarfatti, and David Kaiser, who's a physics historian, has called him one of the hippies who saved physics. So he's thought about some of these crazy ideas such as time travel, but he actually has some serious mathematics to back up a lot of what he says. So that's why I've focused on him. And he's been the one to really point out that the Alcubierre drive alone is not efficient. It requires too much of this negative energy. We need to do something to get over this problem. And we need to recognize that these metamaterials and looking at macroscopic electrodynamics allows for this variable speed of light. And he might not exactly describe it the way I'm about to describe it, but this is how I kind of made sense of it and internalized it for myself. Basically, the speed of gravitational waves is the same as the speed of light. Everything that is massless moves at the speed of light. So when we say the speed of light, it's technically a misnomer. It's really the speed of massless particles, which includes light and includes gravitons, which is gravitational waves, right? So if we affect the speed of light, we have to keep in mind that for macroscopic general relativity, that is going to affect gravitational waves as well, right? So think historically what happened, what I said, Maxwell wanted to have his macroscopic theory for everything, and everyone decided to do this microscopic formulation. That was formalized, and then general relativity was established based off inspiration off the microscopic formulation. But now we need to go to study macroscopic materials, so we need to revisit macroscopic electrodynamics and understand how to generalize general relativity into the macroscopic materials framework, because we understand that gravitational waves are just massless particles, just like photons. So basically, Jack's idea is that pumped metamaterials, there's this idea of Frohlich pumping, hope I pronounced his name right, could lead to these types of exotic effects. So I'm going to show just a brief progression of Jack's ideas. So we're going to start with Einstein's field equations. Once again, we have the curvature on the left-hand side of the equation. Think of this as being some coupling constant in between. We have the Newton's gravitational constant up here and the speed of light. And we have the energy momentum tensor. This is where all the matter is coming in and sourcing the curvature. And then the curvature then tells matter how to move as a fictitious force. And so now when we go into simple materials, you could imagine this c to the fourth getting some correction factor from the fact that it's really like a v to the fourth now, because we're not, all the gravitational waves inside the material do not move at the speed of light anymore if we had some material. And it doesn't even need to be too exotic, even just water, right? So it'd be interesting. What if we put LIGO in water? If we made an underwater LIGO, we could actually, the way they calculate those signals, they have to triangulate everything. They have to use the speed of light to calculate that. So we could actually build a LIGO in water and detect if this happens or not. So it's not some crazy idea. It's something that is connected to reality. And basically, we can take this a step further by, this is really Jack's area of expertise, but I've followed it enough where basically once we start getting these metamaterials, that's going to introduce more complications than just the scalar S. That's where we're going to have to really consider these tensor quantities that I was talking about for the permittivity and stuff like that. So what you can end up doing, obviously this is a little bit of a simplification because I'm not telling you what this phi variable is, but you can think about going into complex analysis. It's very common to think about Fourier analysis and embed things into a complex plane where I is an imaginary number that is the square root of -1. And then we relate all the physics to the real quantity. So we put this quantity in the complex plane, we have some E naught, and then we have some complex phase, where the real part is giving us some magnitude times some cosine, right? And so if you've done a little bit of electrical engineering, maybe you've seen stuff like this before. And this same type of thing is what Jack is doing here. So we get these absolute values going in here, because really what we have to do is recognize that this TAB it contains the source from the electromagnetic energy as well. So really this S and this C to the fourth and the V and the T, they're all integrated together, they're all related. So when you go into the details of it, you plug in what the actual energy momentum tensor is for electromagnetism is, you can eventually solve for these variables and put it in this simple form. And this way we can get this cosine that's going to oscillate, and that's going to give us the ability to have negative energy density. And then the idea is that you want to pump with the appropriate frequencies such that you can get basically the speed of light. It's too large, so you want to make it slower. Actually, it's ironic. You'd think that if you want to move really fast efficiently, you want to break over the speed of light. So maybe you want to make the speed of light bigger, but that actually makes the problem worse. You want to make the speed of light smaller, so then it makes your coupling to curvature becomes more manageable. So obviously there's still a lot of great progress that needs to be done with the theoretical analysis here, but this is at least a concrete, simple theoretical understanding of how to get realistic anti-gravity based on general relativity and simply thinking about material science. And so once again, I'll just go through how I think about this analogy. Basically, we can think about how light is bent in water. And in special relativity, all massless particles move at the speed of light. So gravitational waves move at this speed as well. It's really the speed of massless particles. Therefore, gravitational waves should travel slower or faster in materials, depending on the material properties. So really this c to the fourth, when we go to the macroscopic formulation, we want to think about v to the fourth. And then if v decreases, we can get more curvature for the same matter. And then if we can get some minus sign coming out somewhere through the effects of the metamaterials, then we can get the antigravitic effects. Really, we're going to need the pumping, so it's going to oscillate between positive and negative. And that's going to be how maybe we could get to increase efficiencies. But obviously, there's still a lot of work that needs to be done because it's a very difficult barrier to get over. So, I'm not going to go into details. This is almost the end of my talk. And basically, the metamaterials that we might be interested in are stuff that has very small scale structure, things that are nano engineered. And one idea is something like quantum dots, so you could design it to have some maybe like self-similar structure at different scales. There seems to be exotic effects happening there. And I want to point out that conformal gravity has this scale invariance associated with it. So that's why I was trying to relate the conformal gravity to the metamaterials, because some of these metamaterials have this scale invariance. So if you were to study the mathematics of unified field theory, you're immediately getting into potentially applications for anti-gravity there. So basically some tools that might be useful rather than Fourier analysis, there's this notion of scale-dependent wavelength analysis, and this is complicated mathematics. So if we had some engineers that were computationally adept, maybe that's something they could try to learn, or something like this. So I think that's pretty much the end of my talk. So if I went through a little fast, I can definitely take some questions and things of that nature. So I guess I'll pause at this point and ask if, first of all, thank everyone for attending. And second of all, if anyone has any questions, feel free to ask.
Well, David, it's Tim. So before we do anything, let me put it on gallery view. And again, I'm not going to unmute everybody, but I want to thank you. That was an absolutely tremendous presentation. And so thank you very, very, very much. That was amazing. That was absolutely amazing. And I'm glad that we recorded it. You did go through fast, but you covered an amazing amount of ground with it. So I promised Mr. Sarfatti that I would put him on first. So let me ask him to unmute now.
Hey, Jack, you're still muted, by the way. There we go.
Okay, can you hear me? Okay,
Yeah.
I must congratulate. I must congratulate you. And that was a really good talk, and I actually had some good ideas in there. And actually, I learned a few things from you here. That's right. About the connection between the metamaterials with scale invariance and conformal gravity. Yeah, that was good.
Right. So your idea of getting this scalar field, I was kind of getting an email debates with Jack, and I was like, hey, you're kind of claiming that this scalar field is going to give you some renormalizability. No, I call crap. That's not going to work. And so I started thinking about it more, and I realized I was like, well, these conformal gravity people, I was like, that's what we need to do. And then I thought about it more and I realized, well, they have this scalar field and it's very similar to what Jack's doing. So
Yeah. So I see that now. That's very good. Let me just make a couple of comments on the earlier parts of your talk. As it turns out, I first suggested elementary particles as extremal black holes back in the late 1960s, early 70s. When I was working with David Bohm at Birkbeck College, University of London, I actually published a little paper in Nature Physics at the time, Nature Physical Science, a little letter on that. So, and what I want to point out is the only way, and that's good about the Cartan radius. I have to learn. I don't know that math as much as well as you do. We'll have to discuss that. But the point is that all this requires the Bohm interpretation of quantum theory, not the Copenhagen, because with the Bohm, you actually have particles, whether they're strings or they're extended, the torsion, all that stuff. And then you had something with about the 14-dimensional thing. I have to see that in more detail. You send me your PowerPoint, okay? I want to see the whole thing.
for sure.
But then you talk about the two rotational angles.
Mhm.
Yeah, with this 14.
And this isn't my idea. I mean, this is coming from Wilczek and Z.
Okay, well,
because they-
turns out
yeah.
that's what's his name? The Russian guy has the two angles. Shipov, Gennady Shipov's torsion theory.
Oh, interesting.
Yeah, he has it. So it's okay.
A
So
lot of people have studied similar things. That's the cool thing. There's a lot of different ways to interpret the mathematics. So a lot of people miss some of the effects, but then study the right mathematics.
yeah, okay,
So
okay.
it's very interesting to
Yeah.
look at it all.
Okay, another point where you're talking about the gravitons inside the metamaterials, same speed of light, same as the speed of light and all that. One important thing, which I think, is happening, what the Frohlich effect does, it's a kind of Higgs mechanism, and actually it's like a gravitational superconductor. Just like,
Right.
as you mentioned, the photon gets mass in a superconductor, but because of Frohlich pumping, it turns out that the graviton also gets a mass inside the metamaterial from the
Right.
pump.
And this,
But you see, let me just say, what that explains why the Tic Tac does not have a big atmospheric disturbance outside it. See, because all the exotic gravity effects are localized inside the fuselage of the Tic Tac because of the finite effective mass of the graviton from the Frohlich pumping effect. So it all makes sense. It all fits together.
yeah, definitely. And I mean, I think that's the important thing to stress. We're not going into some exotic theories. We're sticking to the mainstream conventional, theory.
Conventional stuff, and of course now I do see. I was kind of resisting your, going into the exotic conformal field theory, but I think I think that's a good idea now. Now I see what you're talking about. That's good.
Well, and if I could jump in, so now, Jack, now that you finally made it to our conference, of course, I would love you to present. And I think that you've said that you may be open to that in like late February, perhaps March.
Yeah,
or
with
something.
Keith Wanza, but
Yeah, that would be wonderful.
We should probably have Chester in on that also, because he has a good knack of explaining these complicated things in a pretty clear, simple way. I was very impressed.
Wonderful. Well, and again, David, thank you. And Jack, thank you for joining us and contributing. So let me go to Jeremy Reese now. He has his hand up. Jeremy?
Oh, first I'd like to thank you for joining us. You covered a ton of ground, and people were saying you were talking so fast they couldn't. Some people were having trouble keeping up at some points. But that was great. You have to speak fast when you're unloading that much information. That was just. It was like some people were commenting that I feel like I just had 6 months of schooling.
Well, good. Yeah. And it is recorded. So hopefully people can listen again.
Yeah, and they can go back. And first off, I want to know if you can make a copy of your slides available in PDF for our audience, and I could link to that. That would be great.
But yeah, I can do that.
Going way back, I suppose, to Einstein and some of his colleagues like Wheeler, and Wheeler, of course, worked with Bryce DeWitt, were two names you didn't that I was hoping you could comment on some of their work and some of their research. I noticed a paper that I found in some of my research, 1966, on rotating superconductors and gravitational drag by Dewitt. And so it looks like they were, in fact, researching this stuff as early as the mid-1960s.
Yeah, yeah, definitely. So I can make contact with that. I mean, there's this Wheeler-DeWitt equation that's studied in quantum gravity, and obviously Wheeler was interested in this geometric dynamics and really introduced this wormhole concept. So yeah, when I briefly sketched the ideas from Maldacena, that was building off that work. And to me, geometric dynamics is the same thing as unified field theory or like gauge gravity, unified quantum gravity. I mean, there's so many different ways you can say it. It's like you can call it twister theory, you could call it string theory, you can call it supergravity. I mean, broken, maybe the supersymmetry is broken. We don't have to get into that. There's all these different names. So, at the end of the day, Wheeler had this idea that everything is sort of made of the same stuff, right? And that is the idea of Einstein, to unify everything. So I definitely believe. Yeah, and then getting into the quantum mechanical interpretation, focusing on the information. So then we can get into arguments, what's more fundamental, so the information perspective versus the physical stuff itself. But it's definitely related here for sure.
Another thing I wanted to point out, Sabine Hosefield. She's got a real popular channel. She's a quantum gravity theorist on YouTube. I don't know if you're familiar with her. She did a recent video talking about warp drive, and she mentioned a paper by Alexei Bobrik. I don't know if you've ever heard of them or heard of any of these people.
Okay. Yeah, I mean, I've heard of, was it Hossenfelder? But yeah, I mean, I know she looks into superfluidic dark gravity, which actually might be vaguely relevant for some of this stuff. So that might be why she's interested in those types of things. But I haven't looked into those details. So yeah, I mean, I'd be interested in looking into more. I have to admit, obviously, I don't mainly look into anti-gravity effects, but I've just kind of been following the story enough where, I saw what Jack was doing and figured I could explain it. So yeah, I'm interested to look at a little deeper. There's definitely more stuff out there that I haven't seen.
Right. And then I have another thing. My final question was about entanglement theories of gravity and kind of how some of these guys relate. I noticed you mentioned Polyakov. There's another physicist who posted on some of these forums named David Waite, who's contacted me, and he's got a channel as well. I don't know if you've ever heard of him, but he's got some interesting tensor transformations and has done some work in C-tensor on some of this that I thought was interesting and relevant. I was wondering if you had heard of him either.
I feel like I might have heard the name, but I don't remember right now what he's worked on, so I can't really comment. I just thought of another thing in terms of my perspective on the Wheeler-DeWitt equation. They have this idea that there is no time.
Right.
And that is sort of this quantum mechanical thing. So in terms of my investigations,
or space, it's called quantum non-locality too, right?
Yeah. So I mean, some people, like some string theorists, compactify everything to a point, and then so it's like there's no space. They're trying to get this information theoretic thing, and you get this idea that there's the quantum wave function, and then there's this universal wave function. And really, if you zoom out to everything, it's just this pure state that isn't evolving. It's very similar in thermodynamics. When you have a steady state solution, it doesn't evolve over time. It just stays in the same state. So then it's kind of like there's no time evolution. There's no time because it just stays the same. And so that idea has gotten into the Wheeler-DeWitt equation. I mean, it's because they get this Hamiltonian where it's just equals zero. And so it's kind of a joke. Well, not a joke. I mean, people take it seriously, but it's like this theory where it's like, okay, the answer, it's like, what's the theory? It's like H is zero. It's like, what? Okay. So that's why people like talking about it too, because it sounds a little curious. But I think with the multiple time dimensions, it changes the story a little bit. And there's some, I haven't published it yet, but there's some math I'm working on where basically the Wheeler, when you go into extra dimensions, it gives you extra terms. And so the time dimensions gives me like I get 3 mass eigenstates for the different masses. So those end up coming into my Hamiltonian. So when you basically study multiple time dimensions and embed one time in multiple times and then reconcile causality, the Wheeler-DeWitt equation can be modified so it actually isn't zero anymore. So, I mean, this is obviously not published yet and something I'm just starting to look into, but small comment.
Awesome job. Thank you again, and everyone now watching, smash that like button and share this. This was the best one yet. I swear, this is great.
Yes, this is wonderful. And Jeremy, thank you for the question. So let me go to Mark Fiorentino next. Mark, there you are, sir.
Can't wait for
Yes, hello. Yeah, I had a question. If Einstein was alive today, would he agree with this statement, gravity is equal to a contraction of space?
I mean, I guess he would just have, I mean, he had the curvature. I think Einstein would really be interested in the fact that in metric affine gravity, there are 3 different equivalent theories of general relativity that have completely different perspectives, and they give you the same math. So what we're finding in quantum field theory is there's all these different theories. The concepts look completely different, but in rare cases, you can get them to predict the same thing. So that really makes you start to think about how much does our conceptualization actually even matter? You know, these people will cling on, it's like, I have the right concept, I'm thinking about it the right way, but it could turn out there's multiple ways to think about it that get to the same result. So, and I think this is really at the notion, generalizing the notion of coordinate independence and unifying it with gauge theory. Einstein really almost invented gauge theory with teleparallelism because it turned out to be a gauge theory. So I think he would realize that he would look at the other forces of nature and be amazed by how many different ways there are to describe it, and hopefully be open-minded enough to consider multiple explanations. That's kind of my cop-out answer.
Well, are you familiar with his happiest thought concerning general relativity?
Let's see, what was his happiest again?
Einstein followed a line of reasoning that began with his happiest thought of his life. Still at the Swiss Patent Office, he conducted one of his famous thought experiments. Einstein imagined a circle spinning in space. The center of the circle did not move, but its circumference was moving quickly in a circular direction. Einstein compared what happens in several reference frames, which is a standard tool he had used in developing the special relativity theory. He concluded, using his special relativity, that the boundary of the disk contracted as it spun. There was a force acting on the circle at the boundary, the centrifugal force, and its action was analogous to that of the gravitational force, but the same contraction that affected the outer circle left the diameter unchanged. Thus, Einstein concluded in a way that surprised even him, the ratio of the circle to the diameter was no longer pi. He deduced that in the presence of a gravitational force field, the geometry of space was non-Euclidean. So he got the idea of how to bend space mechanically, physically. So that's what was inspiring him to confirm that in his mind, it was a contraction of space, and he had a definite mechanical mechanism to do that. So that's why I think it was
okay, Mark, you said it enough already. We don't need a lecture in elementary. You know, let's. This is off topic. It's okay, but you know,
I don't think it's off topic.
Yeah, no, it's an interesting point. There is actually a lot of interesting controversial ideas where you even think about material, you know, these types of materials, and you rotate them very fast. To actually go through calculating all that is kind of interesting to look at, and I think that is intimately related to you're actually hitting on the point. Some of the things related to the torsion aspects, because if you have a really high spin density,
I'm glad you brought that up. Excellent.
So, I mean, at the end of the day, you have to look at the most general mathematics for differential geometry, and Cartan helped bring some of that, and that might be relevant for reconciling angular momentum conservation, especially if we have quantum spin. So yeah, I mean, I think, yeah, that sounded great.
So yeah, that is basically the angle I'm working, and I use the moment of inertia equation to work out the problem of gravity.
Yeah, well, I think I think that's wrong. Let's.
I think a lot of physicists would say that, yes, but I don't believe.
Also, by the way, Einstein's happiest thought Einstein's happiest thought in the literature has to do with the equivalence principle.
It was
Not
another
what you were
happiest
talking
thought.
about. Not with what you were talking about, although what you're talking about is also important. But
Yeah.
it was not generally called Einstein's happiest thought. It was
I
when
just quoted it from Amir Excel's book
from who?
entitled
From which?
God's Equation.
From who? You quoted from where?
Amir D. Excel.
Say it
He's
again.
a physicist. He wrote the book God's Equation.
Oh, okay.
Yeah,
Okay.
yeah. Well, then he got it wrong. He got it. It's not quite accurate. The happiest thought was when the guy fell off the ladder in the tower. He was painting the tower in Zurich, and the painter said he felt weightless when he was falling, and that's what inspired Einstein with the equivalence principle, which was one of the several important ideas leading to the general theory of relativity.
Wow.
And so to connect those ideas, I just want to say that studying the equivalence principle in the most general differential geometry is very interesting. And that's what gets into these equivalent theories. And yeah.
Well, doesn't the equivalence principle connect acceleration to gravity?
Sure. Yes.
Sure.
Yeah.
Well, let me. Sorry about that. I've got a bunch of different messages kind of conflicting with each other here.
Just keep it coming.
Yeah. Well, so one person, and I'm not sure where it went. Oh, Rob Chambers had asked about Einstein-Cartan-Evans theory. Ron, do you want to unmute yourself, Rob? There we go.
Evans, is that
Rob Chambers?
Hello?
Sorry. Yeah, Rob, you there?
Hello, can you hear me?
Yep.
Yep. Okay. No, it's just something that I remember from someone who's tried to apply Cartan theory, although I think it's still quite a classical theory, and it's not well. I don't think it's very well known or well supported necessarily. I don't know if it.
Right. So the Einstein-Cartan-Evans theory. Yeah. So I actually have looked into this a fair amount. So this is, I would say, inconclusive, because it gets to a point where it's clear that there's a lot of work written, and let's just take a bet there is a typo somewhere in this work, because even the best textbooks have sometimes hundreds of typos. It gets to a point when you read their work, it's honestly very difficult to tell what they're talking about, because there's so many subtleties, and they have to really carefully define their notation. That is one of the biggest problems I find with their work, because there's so many bold claims, and they're discussing maybe interesting mathematics, but they definitely get some things wrong, like very basic like ideas about what gauge symmetries are. They're thinking of interesting ideas. I mean, I looked into that stuff, and it honestly motivated me to revisit Maxwell's treatise. If I didn't hear about Tom Bearden, for instance, I probably would not have read Maxwell's treatise. So I want to say that to say I'm open-minded, and maybe it's slightly inspirational, but obviously it's a very controversial theory, and it has too many bold claims. It's not very productive for most scientists, because it's taking too many leaps, and there might be some good ideas in there maybe, but it's hard to tell how to really get to simplify what's going on there. And there seems to be a little shady, I don't know, the way they co-authored papers was a little bizarre at times. It's hard to know. I don't know, there could be some dishonesty there, but then Tom Bearden got this patent in the US, and it's very difficult to get the patent that he got. You need someone to confirm an experiment, but it's very mysterious to me. So I don't really know what to make of it, to be honest.
Yeah, same here.
And I don't think it's productive to try to, honestly, it's more productive to do it right. And, if you want to read that stuff, great, and try to figure out how to do it right, I would say.
But the Evans is a waste of time. What's his name? De Hooft, Jared De Hooft really knocked it down. At least his electrodynamics. I didn't realize he had a gravity theory too. But that whole alpha. You talk about the alpha group in Budapest.
Yes.
No, they're just forget that. They're very. There's something very strange about that whole thing. Because they also Vigier. Jean-Pierre Vigier was part of our group with Joe Firmage at the ISSO back 20 years ago, and they used Vizier's name in a paper, which Vizier didn't even know they did it. So there was a lot of dishonesty there. It's a waste of time, unnecessary.
Yeah. Okay. Thanks. Thanks.
Okay, and so let me go to Eric Hermanson next, sir.
Hi. Yeah, so I like to think about this physically. So we have this EM field being pumped into the metamaterial, and so there's photons being pumped in with a certain frequency, and then they have a spin of h bar. And one of the reasons why neutrinos don't interact with matter very well is because their spin is h bar over 2. And so the atomic and
that's not
it's regardless of all that.
Yeah.
So spin momentum.
Yeah, go for it.
Has to be,
Electrons have spin 1/2. They interact fine with matter. So what you said is false.
Well, guys, hold on. Let me let Eric finish his question.
Let's just finish, and then I have some comments
so
too.
they won't interact. So atomic and molecular orbitals have they have a spin of h bar. That's why photons are able to conserve their spin when they excite these orbitals into a higher energy state. And so what's happening is there's these photons. So the metamaterial has a permittivity, a permeability, and an index of refraction, and that's all fine. But the photons still come in, and they still have to interact electromagnetically with the orbitals of the material. And so I would like you to maybe explain very briefly how this affects. And I'm not saying it doesn't work. I'm just can you connect the physical interactions to how this will cause the warp effect, if you will?
Yes, the answer is yes, and I've done that in the mathematics. And if you understood the mathematics, which you clearly don't, you wouldn't be asking stupid questions.
I asked Charles.
Okay.
You're such an asshole.
Of course.
No.
Eric, you don't know enough physics. You're not even asking.
You don't know what you do not know how much physics I know. So shut
I know.
Guys,
you asked.
Let's get it together here.
Sorry.
All right, so let me just pause and say, regardless of anything about the spin and h bar over 2, study some material science or condensed matter theory and realize that the materials have fractional statistics as well. So when you're pumping these photons in, the physics completely changes. You really need to study a lot of complicated mathematics, and it's not just like the spin 1/2 story anymore. It's way different. There are things called anyons, for example, that they've experimentally detected that are occurring as fractional statistics. So there's like all this mathematics for new phenomena that there's a lot of exotic effects. So there's just a lot of different things out there that I don't know, based on like the opening statement you made, I'm just saying that look into like anyons, for example, just to understand that type of thinking, and look into some condensed matter theory, and maybe that'll like help open your mind for at least seeing different types of effects, and then maybe start to think about the negative refractive index stuff, and just follow it through. I mean, I'll trust you if you know all physics. Look into it.
I'm asking how momentum is conserved, and I'm asking how that is that conservation of momentum involved in this interaction.
Of course, all the symmetries are obeyed.
Well, Jack.
Okay, so I mean, it's pretty standard stuff. It's just everything's conserved nicely. It's very benign anti-gravity, actually, right? Like I was saying, when you're in the region, it's not a repulsive force. First of all, gravity isn't even a real force. It's a fictitious force. So when you're in the vessel, you're not going to feel any antigravitic effects. When you're outside the vessel, you're not going to feel any antigravitic effects. The best way I can describe it is effectively when you're outside, it almost appears as if this finite volume is more like a point. So everything just all the energy just bypasses it. That's, I would say, a toy model explanation that might not even be exactly correct, but for a talk, I think that's a decent enough picture.
Now, let me see. I had another question here, and I'm not sure who was asking it, but he was asking if you had seen the Hutchison effect videos. And
Yeah.
Yeah, if you had any thoughts on those. And I believe he was probably talking about the gravity part of it.
Yeah, I mean, once again, I think there's a lot of interesting tinkering going on there. I mean, I am willing to believe that some exotic effects are occurring in his laboratory. But, once again, I just haven't really looked into the details enough to really understand, okay, what precise effects, because a lot of that stuff, it's just like you see levitation of some very light object. So it's very difficult to identify what is actually happening there. Is this just some electromagnetic effect, or is it actually a gravitational effect? I suspect a lot of his stuff is just, exotic electromagnetism and doesn't really make contact with gravity, but I don't know. So, yeah.
Okay.
If it's uncontrolled, we can't do anything with Hutchison. It's too uncontrolled.
Yeah.
We don't need it. We don't need it anymore. We have a pretty precise path now to understanding the Tic Tac. By the way, Frank Milburn is here, I think. I see.
He is. And
he's on video.
I am here, guys.
Now, would you guys like to go, because we're kind of invading David's Q&A time, and so I don't want to drive everybody nuts, but then I also appreciate your being here, and as well as Frank.
Fine with me. Whatever you guys think is best.
Here's the thing Tim Ventura and Frank did a video last night, I think it was, on the military threat, because we are interested now in the Tic Tac, right? We're interested in the U.S. Navy close encounters with these objects and how to understand them, okay? So, and here, Frank is here. He's the military, Frank, were you British Army or British Air Force?
I was in the British Army. Is the sound okay, guys?
Yeah, you're
decent enough.
Yeah, I was in the British Army, but I served basically across tri-service, so with Navy, Royal Air Force, Army.
Yeah, okay. So yes, and the thing is this: I think we should take advantage of Frank being here, because really, a military problem, isn't it? And we're talking about the military threat of this advanced technology.
Well, and so I guess what I'm wondering is maybe we should schedule that in. What we had coming up next, now, I mean, we are ahead of time.
And so I guess I should square this with the conference to see how everybody feels about it. But I would be open to it. I mean, David ran fast, and then I think we went through the Q&A pretty fast as well. So.
Just to make a comment on that, I would say that let's not get into fear mongering. Honestly, me personally, I'm more interested in, using this technology to solve problems for humanity. I think one of the biggest problems is transportation, right? Like, think about it. We're like, we have hunger issues. We have enough food. It's about getting it places. I don't think we should do this. I mean, okay, if we want to protect from an interplanetary threat, sure. But what's the probability of that, realistically? I think there's more short-term benefit for humanity for other reasons that we should be focusing on.
It's not a zero-sum game there. They're both connected. I mean, yes, of course, if we have the Tic Tac provides a transport mechanism. With Tic Tacs, with low energy warp drive, we don't need jet engines. We don't need gasoline engines. That's pretty obvious. We don't need rockets. We have we have warp drive. You see what the Tic Tac can do.
Well, yeah, the other problem is this, that sorry guys, you can't it's good to benefit mankind, absolutely, and I wholesale agree with that, but also as well, you can't afford to stand still while China and Russia go ahead with this technology and then leave the US behind, because that's going to have a very, very bad outcome.
Exactly. Don't get me wrong, I think we should push forward with this for economic reasons, for sure.
Yeah, okay. So I think we're all in agreement on the peaceful uses. We're all in agreement. The only thing I would like to say about last night, it was really good on the military. I agree with everything you said about the military part of it. I think you gave a little too much coverage to John Alexander and Eric Davis, and not enough because you gave the impression, or Tim gave the impression, that the physics of the Tic Tacs is beyond comprehension, which is not, as we saw even today from David's summary. The physics is pretty well understood. It's pretty mainstream. We understand how these things work in principle. Making the metamaterial, the engineering, that's going to be difficult. In the same way with nuclear physics, in the same way at the beginning of World War II, when the physicists theoretically knew about nuclear fission, but to actually make a a nuclear bomb with requiring the refinement of the uranium isotopes, that was the big hurdle. And also, I guess the trigger mechanism for the bomb. So, but we're in the same situation today. We understand pretty well the essential conceptual physics, how flying saucers work. I'm talking about the whole flying saucer thing now, not just the Close Encounters with Tic Tac that Mike Turber, you mentioned Mike Turber, Frank, that Mike Turber thinks is fake, but I did agree with what Eric Davis said about Mike Turber's thing. I mean, I don't think it is fake, but in any case, that's my point, that from now on, whenever you're talking about the phenomenon, don't give people the false impression we don't understand the physics. We do understand the physics. We basically understand the physics. Okay, it's not a mystery. It's not a mystery. Now, also where they come from. Oh yeah, one other final point. Then I'm going to shut up. Okay. Well, you asked, what's the motivations? Tim Ventura really wants to. What's the motivations? Well, we have a point of observation. I actually had contact with these Tic Tacs when I was a kid. They told me they were from the future, and they said, "What we're doing now, we're creating them." It's a loop in time. Now, Frank did mention, or was it Tim mentioned, is it Michael Masters, the guy, the anthropologist who's giving empirical evidence of why they're coming from the future? Yes, and that I've been saying that also for many years because that's what they told me. And and I know that sounds a little.
Zach, how do you know? Did you saw something or someone called you on the phone? I remember you having a story where some robot called you on a phone.
The phone.
How do you, what? All right, so that you had this career where you got some black budget money from some.
I'm always getting black, but how do you think I lived the last?
But like, why? What's the probability that someone in the military contacted you? Why do you trust that?
Because yes, okay, good question, good question. Because in 1953 they told me things that are going to happen in 1973, which happened. Like when I met Hal Puthoff, when I met Russell Todd.
Oh, so like you're saying it's more likely that someone contacted you from the future than someone here now.
How in first of all, you were not alive in 1953. Just as this, you were not alive in 1950. 1953 was a very primitive time compared to now. Okay, so I don't think any of the military officers back in 1953 would be able to predict, I'm going to meet Hal Puthoff and other scientists working on UFOs and consciousness and paranormal back in 20 years from then, in 1973, which actually happened. This is all in David Kaiser's book, How the Hippies Saved Physics, right? So it's not just, and also.
What about remote viewing?
Wait, let me finish now, because I'm talking about facts, empirical facts. Because now if you go to the website SoundCloud, there's actually a recording from 1973 of the actual meeting, a Central Intelligence Agency recording of me back in 1973 talking about the phone call I got in 1953 with Russell Targ and Brendan Reagan. And then Brendan Reagan says, oh yeah, we have all kinds of evidence. We have other kids who have had the same experience. So what the hell's going on here, right? This cannot.
All I got out of that is the military is talking about getting in contact with you. I didn't listen as well.
Okay, well, you're missing the whole thing.
I'm being playful.
The point is, there's evidence here. There's recorded evidence. The actual CIA recorded conversation is on the internet. You can hear it yourself. You can hear Jack Sarfatti in 1973 talking about the phone call from the computer on board the spacecraft from the future. And you can hear guys like Russell Targ, these are guys working with Edgar Mitchell in the CIA remote viewing project, talking about, oh yes, we know that they're coming from the future. We have all kinds of other evidence,
Okay, and Jack, if I could jump in, I put a link up to that in chat, and I will put that on the website as well when we publish this.
Yeah, so what I'm saying is we have actual, it's like, think like you're a cop, you're a policeman, you're Inspector McGray, studying a murder. You're trying to solve a mystery here. You have to look at every piece of evidence. It doesn't have to be like, straight scientific stuff. You follow your clues. So here we have some, what is called high strangeness that really happened. There's the paper by Jacques Vallée and Eric Davis on high strangeness having to do with the Skinwalker Ranch and all that spooky stuff. Well, here's real spooky stuff. I said I got a goddamn phone call when I was a kid. Now, it turns out there were many phone calls, okay, which I had forgotten a bunch of them. That's another thing. And that's all been corroborated by the actual evidence of what happened. So the point is, what the phone call said, the basic idea is that I with you guys, other people like Hal Puthoff, that we are creating the time travel Tic Tac technology. It's all a self-consistent, what's called a loop in time, which is a well-known concept, from Novikov, self-consistent loops in time, and CTPs, closed time like curves, hypercomputation. Okay, so and then
the conformal gravity fits into that as well, because
I know, of course, everything is fitting together. It's all making sense. And the thing is this: see, what I have, which most of you don't have, I'm 81 years old, so I have an institutional memory from the late 1940s to now, which you guys don't have. I see the big picture that you guys don't see, like a detective. You have little pieces of the puzzle. You don't have all the pieces. You don't have the long view, which I have. And now let me say something else. When the CIA, basically started being open with me back in the 1970s, this guy George Koopman, who was a military intelligence guy who was funding us at the time. This is all in the hippie say physics. You could all you could all check this out. David Kaiser's MIT book. They said, okay, what CIA wants to know, how does consciousness work and how do flying saucers fly? That's what they want to know in terms of physics. That was our mission. Okay, that's why I've been getting paid all these 50 years, basically. Okay, and now in the last couple of years, we've actually solved the problem that we've been paid to solve. We've solved, conceptually, there's a lot of engineering, as you pointed out, the metamaterials. But we were tasked by the intelligence services back in the 1970s to work on this problem. And now I claim we've solved it. So that's why it's very important, politically speaking, right now, that when you have Senator Rubio and you have the UAP task force at the Pentagon, that these young schmucks who are in the Pentagon now, who don't know what the hell happened 50 years ago, which I do know, that they should be talking to me to find out about this and not just depend on what Eric Davis and what John Alexander, who doesn't know anything about physics, what those guys, or Christopher Mellon, what they say. They shouldn't depend on that. They should find out what the hell I'm talking about. Okay.
Jack, if I could jump in.
Yes.
Now, you were talking about Frank's stuff. How could you connect your experience to what Frank was writing about in terms of threat potential, I guess? Because I know that you've talked about threat potential also, right?
Well, the threat is obvious. I mean, the threat, okay. And Frank actually said, you were Frank last night. It's a big universe. There are many intelligences out there with this kind of technology. It's elementary technology. It's not that it's that complicated. Any civilization that learns physics at a certain level is going to get this time travel tic-tac tech. So there could be, and in fact there probably are, there are hostile forces with tic-tac tech out there, as well as our guys from the future. So I mean, it's not just one intelligence out there. I mean, Frank actually made that point last night, which I agree with. Does that answer your question?
Yeah, no, yeah, absolutely.
Are there any other questions, by the way? Yeah, let's try to hear some of those. I'll let Tim kind of direct the questions. I don't know who's muted or unmuted.
I'm just
I'm still unmuted. Let me go back to Jeremy, if that's okay.
Yeah, I wanted to ask a couple different questions. Back to, this is an engineering conference, so my main interest in this is of course the physics and the engineering. So I want to get back to that and talk about the specifically the type of material. So I have a material scientist that I'm working with, and also we have a team of engineers and stuff. So we're trying to design the material that has these properties. And I know you showed some of those graphs with the different, the different where you sit on that which quadrant you sit on with respect to permeability and permittivity variables. in two different materials and how they interact. And so I'm kind of like have questions about the material end of this, and I've been looking at candidates since reading about this in Eric Davis's work on warp drives and feasibility mechanisms for producing negative energy states, and he had referenced Jack Sarfatti's work, so that's how I found Jack's great work on squeeze states. And I noticed that also Wheeler published a 1985 paper on squeezed coherent states and something called the Frank-Condon effect. I was wondering if you had ever heard of the Frank-Condon effect, because it's sort of that's where I'm looking in the future for the types of materials that I want to design and engineer to, as far as these metamaterials that we're talking about, and talking about building and really building an experiment that we can test these theories with. So I kind of wanted to hear Jack and also or David's thoughts on the materials side of this, and what they have to say about it.
Yeah, that's definitely a good question. So I don't know specifically what this Frank Condon effect, but I do know that in my investigation of these multiple time dimensions, it actually relates to the squeeze states of light. So there's some other work that looked into the same the same Lie algebras that were used for discussing squeeze states of photons are related to the kind of three mass generations I was talking about in this unified field theory model that I'm looking at. So that's the closest connection I personally have as kind of like a particle physicist right now. I haven't really exhaustively looked into the details of these metamaterials, and not even as much as Jack. So, we've actually stayed in brief email contact. I've reached out to you in the past. So yeah, we should stay in contact, and I'll try to look into it more. But I don't really have very specific details to elaborate on.
Okay, do you want me to comment on that too?
Yes.
That's a good question, and that's where the research has to be done. That's okay. That's analogous to saying it's 1941, 42. They're starting the Manhattan Project, and at Oak Ridge they have to. Actually, it was John Wheeler who directed the Oak Ridge thing, where they have to try to find refining and getting the right isotopes for the bomb. Okay. And getting the right metamaterial is like that. It's going to be a major project. It's going to involve at least dozens, if not hundreds, maybe thousands of scientists and engineers, and that's the big project. I don't have answers, and neither does David. Because it's a major thing. It's like asking Einstein in 1916 to build a lot to calculate black hole collisions that Kip Thorne did like 100 years later. It's a major project. That's the big project.
Well, I don't think we need Einstein. What we need is a Richard Feynman and a von Neumann, if anyone. But I wanted to know if you could comment specifically, Jack, on the coupling and the need for this Frohlich condensates, because I know that was a big part of your whole theory on this. Is that Frohlich condensates?
The Frohlich. Okay.
Talk more about those.
The Frohlich condensate. Basically, the Frohlich effect. Let's say the Frohlich effect. It's a non-equilibrium open system. The system's being pumped off thermodynamic equilibrium, and then you get different kinds of condensates, like superconducting states of different kinds of elementary excitations in the material. Like David was also talking about anions in the edge states, in the boundary states of these exotic materials. What I think happens there is that the coupling, the G over C to the fourth coupling between stress energy sources and the induced gravitational field, that gets amplified exponentially by an exponent e to the Frohlich order parameter. See, and that gives like a super amplification to the strength of the effective coupling above and beyond the ordinary metamaterial negative refraction resonance types effects. There are two separate things going on here. You can get some amplification just using a metamaterial at thermodynamic equilibrium, but when you pump it into the Frohlich state, I think what's happening is that you're going to get even a super amplification, so you could really get warp drive, the Tic Tac propulsion system with very small amounts of applied energy, which is what we're seeing. It's because that we actually see that in the observations. Am I making sense? Are there questions about what I just said? Do you understand what I'm talking about?
Yeah.
Yeah?
Yes.
No?
That's a decent answer. Anyone?
I was gonna elaborate. So Jack, why did you calculate that you needed terahertz frequency electromagnetic waves? Why did that? What was special about that
No.
frequency
Okay,
range?
okay, that's a good question. No, the terahertz. Look, what we're doing. This is like a detective story, right? It's not only scientific deduction. We have clues. The terahertz stuff comes from Hal Puthoff's lecture. Hal Puthoff has access to classified material, right? And Hal Puthoff, you were there in Italy. Remember the talk I gave, the Puthoff talk? It's online. And Hal has a slide of what are allegedly recovered materials from like a flying saucer or Tic Tac. And it says it's a metamaterial and it has it like resonates with terahertz waves from from just the structure of it. That's where I got terahertz. But also, yeah, I have clues. I'm like Sherlock Holmes here, right? Or also I'm like Paul Hill. Paul Hill, very important. What did Paul Hill do? Paul Hill was not a theoretical guy. He was an aeronautical engineer, and he took evidence from the flying saucer observations, and he tried to build a picture of how one might understand the evidence. This is back in around 1953, about the time I got my phone calls, right? Back in 19. I'm doing the same thing here, saying, look at what the Tic Tac, what they're saying, what Commander Fravor and all these guys are saying it's doing. How can we understand how it works? Now, the other thing is that Stuart Hameroff and people like that, the people working on the consciousness, seem to think that with the microtubules, that terahertz signals in our microtubules in our nerve systems is somehow connected with consciousness, which may be correct. Okay, and remember, when I was the kid, I got the phone call from the computer from the future, it said it was a conscious computer on board a spacecraft from the future. That's what it said. Okay, so the point is that these Tic Tacs are conscious machines. I think, I don't think there's any biological creatures living inside them, but they have conscious AI. And in order to have a flying saucer or a Tic Tac maneuver, like for example, it's in a dogfight with the F-18, right? It's having you have to be able to compute very quickly. You have to be able to compute how much gravity, how much anti-gravity you need induced in different parts of the fuselage. That's the whole idea of the Alcubierre warp drive. In the Alcubierre warp drive, you have gravity, induced gravity at the nose of the craft and induced anti-gravity, expanding space at the tail of the craft. Well, you have to be able to, in real time, dynamically change the distribution of gravity and anti-gravity over different parts of the fuselage. You have to do that very quickly. And we're talking about that's like a hypercomputer. That's like one of these, the closed time, like the CTC computers, hypercomputers.
I don't understand. My question to that is, why can't that be done instantaneously, optically, using optical materials that effectively work as.
Yeah, I don't think we're communicating. I'm talking about the computations to know how much electromagnetic field to put at different parts of the fuselage in, say, nanoseconds or let's say even the milliseconds, to keep changing the configuration of the pumping electromagnetic field over the fuselage, to keep changing that in real time because you want to make it, okay, suppose.
Isn't that field, though, an optical field? Isn't it kind of like optical information?
No, I'm talking about how to compute. No, we're not talking, you're not following me. What happened? First of all, we're not talking about waves. We're talking about inside the metamaterial fuselage. It's basically what near fields, right? It's like the scalar. It's like what they're near fields. Like it's like
they're not transverse waves.
They're not transverse waves.
They're out of phase.
Yeah. what it's like electrostatic fields or magnetostatic fields, but they're changing in time. We're not talking about radiation. We don't want radiation fields inside the metamaterial because that's like oil leaking out of the engine. Okay,
Right.
we want to have confined fields. The gravitational field of the Earth is basically a static field. It's not gravity waves. They're static. You know, they're zero frequency.
I guess
so
the way I'm interpreting this is as a sort of a physical lens that I can build that warps this or changes
that may
this
be,
refractive
but you have
index.
to know how to shape. Okay, use your analogy. You have to know how to keep changing the shape of different parts of the lens in time dynamically in order to.
So I think there's a work in progress that could be done. I think Jack might be putting a little bit of the car. We don't need to get precise control of everything down to the micrometer for gravitation. I mean, the first thing to do is just make sure we can get something where it's stable and it's stationary
Okay,
and
wait.
it's there. No,
Yeah.
just let me finish, right? So we need to figure out how to do that. Obviously, Jack is also talking about the computations needed just to figure out what materials are needed to get here, right? That's a big part of what he's focused on. That's a little bit part of the gap. But I mean, in terms of understanding these effects, first you just need to figure out how am I going to get this thing stationary? Then we can figure out how to get something moving.
Yeah, that's all
we
true.
might not need too much fine precision of, fine tuning of the gravitational field coming out of it, but we do need a lot of work to figure out, okay, how do we compute? We need to figure out how to actually compute these refractive index properties, right? Like you can ask me like, well, what about this effect? What about that effect? What about this effect? I mean, it's hard to have an answer unless you just sit down and do all these calculations. So we need to have more people that are directing their thought to understand, okay, there's all these different exotic effects. Maybe, pulsed metamaterials with Frohlich pumping, maybe that's one way to do it. Maybe there's other ways too, right?
No, there aren't any other ways. I don't think
I have no idea, right?
Yeah,
So,
but I do have an idea. Okay, but there are two separate problems. What Dave you were talking about right now in the laboratory to actually start designing, doing experiments. Yeah, everything you said is true. I was talking about something else. I was talking about the actual advanced intelligence out there that's contacting the Navy, in these close encounters, what they have on board. This I'm getting back to Frank Milburn's best, his Sadat position paper. What they have on board is a very powerful conscious computer that is computing in real time, dynamically, how to configure the warp field so it flies in the direction they want it to fly. See
but that might not be the thing that we should focus on because that might not be the first thing. Well, I mean,
right, there might be a more preliminary step
there
that
could
we
be some
can test.
stepping stone.
No, I'm talking about right now. I'm talking about for the Pentagon to know what the hell is needed. Okay.
And also, when you say a conscious computer, I think of this entity as being conscious, but we only see with our two eyes. This thing would have to see in all directions, all around it.
Well, yeah, it has senses all around. Of course, that's correct. That's absolutely correct.
If I could jump in really quick, Sean had a question, I think also. Sean, if I could squeeze you in.
Yeah, I was just my question is for David. I was wondering if you ever heard of Frank Zadarsik.
I haven't. Sorry. Do you want to briefly mention anything about what he did?
Actually, I'll ask him. I'll ask that later. But anyways, have you ever heard of Eric Dollard?
Oh yeah. He did some interesting electromagnetic experiments looking at Tesla patents. Yeah. So that's kind of getting into some of the near field effects. He claims to have some faster than light measurements. I know that.
And not just that.
Also did in the 1800s.
Yeah, not just that, but he has. He claims he just completed Heaviside equations. So I suggest you take that up and maybe you could play with that for a bit. And
yeah. I mean, I there's something that I've looked into a lot. Actually, I've looked into so many claims of people claiming they've gotten Heaviside gravity to work, and I just haven't found anything yet. So
not gravity. Yeah, I don't think it was just gravity. I believe it was just like he completed his math that no one else could. He claims, but anyways, that's just food for thought. But Frank Zadarsik, I believe he has some awesome math on being able to figure out the what was called the quantum transition, where the electron moves from one orbital to another. He claims he has the math to that, and he put the I believe it was the spring constant into the Coulomb's equation. I'm not too sure if that's exactly
Yeah,
how it
this
went, but
this is really not.
Well,
yeah, anyways,
quantum fields
I
are
just,
based off springs, so
yeah, anyways, that's just it's just for food for thought. Anyways, take care.
okay, thanks,
thank you,
Sean.
appreciate it.
Yep.
Let me go to Jeremiah next. Jeremiah is waiting.
I've got a question for David. Sorry, Jack, but David's the young guy that's gonna have to live on to carry on these ideas. So I got a question for him and get his mind going on all these metamaterials.
That's true.
Yeah, you did bring it up, David, about metamaterials. So I have to ask on the engineering and practical side. Let's take a look at one of the earliest metamaterials ever made, right? The split ring resonator array.
Right.
And so the interesting thing that you mentioned about near fields, and if you take a look at the negative refractive index of split ring resonator arrays and how they can appear transparent to certain frequencies, it's kind of odd, right? Because in order for those materials that are physical and dimensional to appear transparent, they would have to theoretically have a velocity of light going through them, or have the electromagnetic wave entering them travel faster at one point of its transition and travel slower than light at another, in order to exit the opposite side undistorted, so that that material would effectively disappear to the EM wave. Which makes me think about the interesting phenomena of what happens in the near field right at the surface of a split ring resonator, or even a Churro split ring resonator, where you have a ring inside of a ring, the two being at slightly different frequencies, but having a very sharp spike harmonic that occurs at the node between the two frequencies. So if we have other materials that maybe have interesting properties, interesting atomic properties or molecular properties, and we place them in the near field of that resonator, could we not entrain those materials and really electromagnetically move them around, screw with them, change their precession atomically, or do things like that by using the near field effects of these nanomaterials, or of these nanoresonators?
Yeah, I mean, honestly, I would have to look into the more of the details of what you described and try to get down and dirty and do calculations. It's difficult for me to just give like quick yes or no answers, but no, I mean, that sound very interesting. And I think you're kind of thinking about the right things. I mean,
I agree, by the way.
I agree.
I agree with that. Yeah, these are the kinds
we're attempting to play with the concept. It's complicated, but we're attempting to design something now, and we're going to take some measurements and see what we get. Honestly, I think that we're flying in the dark. I'll be the first to tell you I have no idea what I'm doing, but I am reading papers and attempting to understand it.
Okay, let me give you
Definitely, that sounds interesting.
let me give you a general idea here, because this is important. That hasn't been mentioned yet. Well, no, actually, David, you mentioned very briefly. In order to get anti-gravity, I'm talking about now at the practical, the practical Tic Tac level. What matters is the dissipation. It's the phase shift. Dissipation in the metamaterial determines the relative phase shift when you have if you apply an electromagnetic field in the metamaterial as the pump, and it induces a gravitational field as the output. So electromagnetic field input into the metamaterial as the transducer with a gravitational field output. The dissipation changes the phase relationship between the input electromagnetic field and the output gravitational field. That's that cosine theta in the equation, in my equation that David wrote down. When that cosine factor, when the phase factor goes from a positive cosine to a negative cosine at a little place in the fuselage, it switches from an attractive gravity field to an anti-gravity, to repulsive gravity field. So in order to make anti-gravity, it's just a matter of dissipative phase shifting. Electrical engineers, we're talking about phase modulation. Just think of the flying saucer fuselage as a kind of lattice work, as a kind of tiled lattice work, and each little spot on the lattice can either be a attractive gravity field, I'm talking about near fields, attractive gravity field or repulsive gravity field, depending upon the relative phase of the electromagnetic field at that spot compared to the output gravity it's generating. Okay, and that depends on how much dissipation there is compared to non-dissipation. Okay, dissipation in materials from inelastic scatterings. Okay, and in terms of electricity, it's like resistance versus reactance. Okay, see what I'm saying? It's the ratio of resistance to reactance, and so that's what you want to control on a micro scale. You want to control that okay, are you getting what I'm trying to tell you?
Yeah. I mean, it gives me this idea about a phase conjugate mirror type system where you actually reflect a wave out in both directions, but one of those sides is interacted with. You perfectly bounce back your wave because this metamaterial has the ability to absorb it and reflect it back at the same angle it came out. And then you could effectively push back against the field that you just created within unenclosed space and create a force that would not be equal and opposite because it's time delayed.
No, that's not quite what I mean. But see, I think in terms of the actual equations, and you're thinking in terms of physical pictures.
Engineers, I'll admit I'm an engineer all the way, you know, through and through.
Okay,
so.
but don't think of waves. I'm thinking even of like applying voltages. I'm talking about induction fields, near fields. Okay, just think of a capacitor. Just think of a capacitor, you know, LCR network. Okay, a capacitor with a coil wrapped around it, that sort of thing.
Fields.
And it's just by changing the voltage, by changing the input voltage, you can change the input. Okay, just think of a simple capacitor, an electrostatic field between the parallel plates of the capacitor, right? And that electrostatic field will generate a gravitational field according to Einstein's field equation. Let's just think of that.
That's interesting. That makes a lot more sense about the high frequency gravitational wave detector that we were talking about last time.
Okay, right now I'm just thinking almost DC. Let's forget waves. Let's just think that I have a voltage across a capacitor and I'm slowly changing the voltage in time. That's going to, okay, and that will generate a gravitational field. But if—
So is it the rate change that creates the gravitational field, the actual change in potential is it the change in potential between the plates that creates the field, or just the static potential between the plates?
No, the static potential is the electric field, right? The gradient of the voltage, okay? The electric field in the capacitor is going to generate a gravitational field according to Einstein's field equation. Now, the problem is—
catch that. That's interesting.
All energy sources gravitational fields, and this is neglected. This is always neglected, right? So in quantum field theory, you just study everything in flat space-time and you put all the matter in, but really gravity, right? Any energetic thing is going to warp space-time. So
yeah. So here's the thing. So now let's be very specific. We're just going to talk about a battery connected to a condenser. Okay, but that condenser is filled with a special kind of metamaterial. All right. That's the picture. Let's make it as simple as like the hydrogen atom, as simple as possible situation. Okay, so we apply a voltage to that system. Applying the voltage is like pumping the system. We apply a voltage. That voltage generates a gravitational field inside, in the material between the plates of the capacitor.
E equals mc squared.
That equals, yeah, well, that's true, but that's not.
But it's like it's the C in it is you're just pumping light into the system in electromagnetic fields.
Okay, wait. I'll give you a simple way for engineers. Einstein's field equation is just like Ohm's law. We all know Ohm's law, right? Ohm's law, the output current is the applied voltage divided by the resistance, okay? You can think of Einstein's field equation that way. The voltage is the stress energy tensor. 1 over the resistance is the coupling constant, G over C to the 4. And the current is like the gravitational field. This is an analogy, okay? This is an analogy. So the point is this. What you want to do, what the metamaterial does, it makes a very small resistance. For a fixed voltage, for a fixed voltage across the capacitor, if you're somehow able to control the resistance and make the resistance go to 0, like in a superconductor, so to speak, you get a very big current output. The current output is like the gravitational warp field. So that's the basic idea. So the metamaterial is a way of getting, in this analogy, very small resistance. That's low power warp drive. That's what we're aiming for. Okay? Does that make sense?
Yeah, I did have another question for you on the experimental side of just this capacitor, though. If you had, let's say, a theoretical 1 million K factor in possible dielectric, that you could put, a few 100,000 volts in 1 millimeter, and you were to measure, say, gravity distortion around that capacitor, would you be able to measure it?
Well, okay, that's a good question.
Because I guess what I'm asking is, you're taking electrons from one plane and you're putting them on the other. You're just moving them from point A to point B, but they're technically still within the same device. So you have the same amount of total energy in the system. I guess I'm confused by why the separation of the positive and negative charges equals a gravitational field.
I don't think all I'm doing is look at the mathematics of Einstein's field equations. Okay. And now you did say the thing is this. Now, so you said if the K factor is what, 10,000?
But let's say it's a million, because we already have 200,000.
Yeah, right.
K
If it's a million, yeah. If it's a million, let's see, and I think that I think that will increase the efficiency by a million times by 10 to the 12. I think goes as the square. Does it? Let's see. Yeah, because c squared is 1 over the dielectric constant. C squared is 1 over epsilon 0 mu 0. So if your epsilon is increased by a million, and the coupling though goes as the 4th power of the speed of light. So okay, if you give me a dielectric constant of a million, the gravitational effect is amplified by a trillion, by the basic square of that.
Wow. Okay. Did not expect that.
According to Einstein.
Okay. So let me jump in really quick. Let me go to Todd next. Todd, you there?
Smash that like button and subscribe.
This time.
There we go. I just
there he is.
Okay, hit the wrong button. Hey, so on this metamaterial stuff, I'm working from the engineering side. I don't know if you're familiar with any of my work. Todd Desiato. No?
Sorry.
The name is, yeah, we know your name, but no, I don't know what.
All right. I published a paper 2016 and in 2018 about an engineering model of quantum gravity. And in that model, it's not at all really different from what you've been presenting. What you call spin density, I just look at QED and at the Compton frequency, the Compton wavelength. You have breakdown and you have exchange scattering with the vacuum. So that becomes your finite radius. Basically, have you considered that the scalar magnetic field is the scalar field you're looking for? Because in your Jack's equations, you want a strong magnetization, and you want a low speed of light, which you're going to get with a material that's got a high magnetization like ferrous materials. And then you have, you can induce in such a material Larmor precessions. And you can do this, say you have a sphere as your bubble or your hull, your metamaterial is this material that then you project onto this material a magnetic field that varies from point to point on the material, so that over here in front you have a strong magnetic field and in the back you have a weak magnetic field.
Yeah, something like that could work.
RF signal that causes that area of the hull to resonate.
Yeah. It's something like that, roughly speaking. Roughly speaking, yes. Okay.
Yeah, and to elaborate, so there, you talked of the Cartan radius that I discussed is actually slightly different than the radius you were discussing. So Poplawski actually has a torus for his model for the electron because it actually has 2 radii. So it's something similar, but it's a different radius for the gravitational aspect. So I'm just pointing that out. So there's kind of like this electromagnetic radius and then a gravitational radius. So what you're describing may be somewhat similar, but there's just that small difference there. To really answer your question, though, you mentioned this magnetic scalar. I don't know exactly what you're referring to, but I have looked into, people talk about scalar waves and longitudinal modes and things like that. There is, for example, below the electromagnetic potential, there are these Whittaker potentials or Hertz potentials. I've studied these a lot. There is this scalar field that's related to the Lorentz gauge condition that is more an electromagnetic scalar. And typically the mathematics, you could imagine such a magnetic scalar. I don't even know if this is exactly what you mean, but the mathematics typically forces that to 0. But if you had magnetic monopoles, you could cook something else to get it. So that's the closest guess I can get at what you might be referring to, but I'm not sure the precise details of what you're referring to.
Let me say one thing. Keith Wanzer, I don't think he's here. Keith Wanzer actually did a computation of my equation there for just a simple material, a homogeneous material, and it turns out that the magnetic permeability appears in the effective coupling between stress energy and induced gravity has the magnetic permeability in the denominator, so that diamagnetic materials like superconductors, see, this should actually give a strong induced gravity field. So that would tie in a little bit with the Modenese work in the Podklinov, whatever.
Yeah.
Yeah, and it would do the same thing as a hull. Because
we're talking about the hull. We're talking about a hull, a metamaterial hull, where it goes diamagnetic, and so if you have a diamagnetic fuselage of the Tic Tac, then that would have the effect. And then you just, in order to get gravity versus anti-gravity in different parts of the hull, that's just a matter of changing the amount of dissipation compared to reactance. Just the phase shift, the cosine theta in my equation. It's phase modulation. It's the cosine. Okay.
Sorry, can you repeat that, Todd?
You said as long as you don't go negative. If the cosine theta goes negative, then that equation violates the strong energy condition.
Forget that strong energy. Strong doesn't mean shit. I don't care about this.
In every general relativity textbook.
No, you don't understand. What the strong energy condition, it's just strong energy condition means that there's nothing that says you can't violate the strong energy condition. It's not a law of nature. It's just that in order to get a warp drive, you have to violate it. So okay, but we're seeing the warp drive. The warp drive is a fact.
You don't.
There's nothing sacred. There's nothing important about the weekend. It's just a condition, okay? It's just a constraint, but it's not a law. It's not, nature doesn't have to obey the strong energy condition. God did not say that. It's a matter of empirical observation. Here's the general point.
I've never observed any.
What? Yeah, well, no, but we have. Well, you got your.
That's what you ask, I guess.
That's what flying saucers are. They're violating the weak energy condition.
I think an important key is to study the more exotic theories than general relativity and to look to see what happens to that strong energy condition in metric affine gravity, and things will change a little bit. So if you stick to pure GR and you stick to Einstein's field equations exactly how it's written, and you really stay closed-minded and don't think about what's going on, it's easy to get caught in that paradigm. So that's why I mentioned the metric affine stuff, because it has that scalar field that is somewhat similar to what Jack is talking about. And I know it does change a lot of the energetic stuff that's going on in comparison to GR. So something to consider.
Yeah. And the point is the cosine going negative is exactly what you need in order to explain the observations.
Yeah, otherwise, like if what you're claiming is true, then the whole thing breaks down. It's impossible, as Jack is saying. So yeah.
So here's the point. Let me get this very clear. If you see a Tic Tac or a UAV going at, say, 10,000 miles an hour, and then it makes a sharp U-turn where it looks like there are thousands of G's involved, that's warp drive. The only way to explain that is what we're talking about. Because what happens inside the Tic Tac, it's 0 G. The actual, they don't feel any G forces. It looks like, to the outside observer, it looks like there are G forces, but they aren't there. That's an optical illusion. That's part of warping space-time. That's what warp drive's all about. So everything that Commander Fravor and Kevin Day and all these guys reported in the 2004 encounters and the 2015 encounters with the battle groups, that all, unless it's something like what Mike Turber's talking about, where he says that that's just spoofing electronically, they're somehow tricking the electronics. But if it really is what it appears to be, that's definitive proof that it's a warp drive. Has nothing to do with conventional propulsion. There's no thrust. It's zero thrust.
Jack, let me jump in with a question really quick. Now, so with the model that you've come up with for the Tic Tac propulsion, from what I understand, they are transitioning between ocean, atmosphere, and presumably space, right?
Yeah.
So how do you think that this would work? I mean, would you expect any drive issues or anything like that during a transition when they're going into or coming out of the water?
well, it doesn't matter what I expect. It's what we see. These things are doing it. And we don't know enough of the details without working on it, like a Manhattan Project scale to answer a detailed question. But clearly, let's just assume that the observations are true, okay? So these Tic Tacs, they go 500 miles an hour under the water, right? And then they just pop out. And Hal Puthoff even reports that they may be able to go through solid matter. Right? That's how, I'm not saying that, but Hal Puthoff and Eric Davis, they're talking about that kind of stuff. All that stuff, though, can be understood in principle on the basis of the equation, my equation with the cosine theta that that Dave put in that slide. That equation, essentially, qualitatively speaking, explains everything, even time travel. Even allows time travel through closed time-like curves.
Well, now I guess this goes back to the idea of the threat. And I'm probably going to get myself in trouble by asking, but with these kind of capabilities, what would you propose for some kind of defense against these? How would you circumvent that drive, or how would you shoot one down, basically?
No, that's a good question. It may not be possible. See, one of the things that's where I'm working with the Italian. I'm working with a guy in the Italian Air Force back in Cortona, in Tuscany. This guy Saro. He's Italian Air Force military intelligence, and it may not be possible to defend against, because it may be possible to create what's called like an artificial white hole, like a defensive shield. It's like the event horizon of a white hole, so that any object that tries to get close to it is infinitely repelled, can never even reach it. So in other words, you could have the old science fiction force shield. It's possible with the equations that David, my equations that David has simplified and wrote down there with that cosine thing. Okay, all kinds of weapons systems, both offensive and defensive, are possible. Now the thing is this. Before the Russians have interviewed me on all this. Let me tell you a little background as to what's going on here. I first gave these ideas in a very primitive, rough form in 2011 at a DARPA NASA 100-year Starship meeting. Eric Davis was there. Eric Davis didn't understand it. He sort of poo-pooed it at the time. But I gave this basic talk with metamaterials and low-power warp drive. This way before Tic Tac. This is in 2011. And of course, the Russians were there. The Russians are not stupid like our guys. Our guys are kind of stupid compared to the goddamn Russians. They're smarter. So the Russians were there at this meeting that I gave an invited talk. The talk was paid for by NASA. General Pete Worden, who was formerly head of the U.S. Space Command. He was heading NASA Ames, and I was working with guys at NASA. So they paid my way to Orlando, Florida. I gave the damn talk. I started talking about UFOs, and they didn't like it there. And in fact, Sharon Weinberger, who's a defense journalist, actually wrote an article in BBC about this meeting where I pissed everybody off. I got people screaming and yelling because they started talking about UFOs. Okay, so in any case, the Russians were there. The Russians take me seriously. So around 2014, I get a phone call from Vladimir. He says, Vladimir, we are from St. Petersburg Channel 5, and we would like to make a video of you. Okay. So I said, okay, this is San Francisco. So Vladimir and another guy, I have this all photographs of them. They come and we spend a couple of hours videoing me, talking about all this stuff, all my crazy physics ideas, UFOs, the whole thing, right? So this was like 2014, 2015. And they said they would send me the video of it. They would send me the program. I never got the program, never saw the program. But a few months later, Vladimir Putin comes out with this whole big thing that how Russia's going to get teleportation, all these advanced quantum technology weapons, just this kind of stuff that I was talking about to the Russians. Okay. All right.
So Jack, there's a couple other ways that the Tic Tac could be doing those 90-degree turns at like 10,000 miles an hour. Have you ever considered the possibility that they can control the inertial mass of the craft, make it?
No, that's bullshit. Okay, I'm glad you said that. Right away, that's bullshit. As soon as I hear that, that shows you don't understand basic general relativity.
And you say that to everyone.
You cannot change the inertial mass. It doesn't do anything. You don't understand the
Where
equivalence.
does the inertial mass come from in the first place? If you can't answer that question, you can't remove it.
Okay, first of all, there's a little book called Just Six Numbers by Sir Martin Rees, British astronomer, master, Stephen Hawking's boss. And he talks about if you try to change the inertial mass by even a small percentage, you blow up the fucking universe. Okay, so that's the stupidest idea I ever heard. Now, unfortunately, even Hal Puthoff has pushed that idea a little bit, and it's really stupid. It violates elementary physics, okay? There's no way to change it.
It doesn't violate quantum field theory.
Let me finish. Even if this is an elementary physics 101 lecture, okay?
The next lecture is actually about...
Shut up and let me talk. Okay? Shut up. Let me talk. Respect your elders, young man. Okay, listen.
Well, elders in age, not in intelligence.
Wait a minute. Shut up. If you change the inertial mass, that means you make it like a photon.
Hey, Jack, what are all the masses of the particles in conformal gravity?
Pardon me?
What are all the masses of all the particles in conformal gravity at high energy?
Is it but zero?
Oh, wait, how did it go to zero?
No, but that's just a mathematical thing. The point is...
No, it's just a mathematical thing connected to a scalar field. You're right.
No, yeah, but you don't change... If you change the scale of that, Lenny Susskind, read Lenny Suskind's book. He said, if you try to change that scalar field, you're going to blow up the universe.
You have mass renormalization in quantum field theory. It looks like we need to figure out renormalizability of gravity, and maybe inertial mass is related to that. I don't know, though.
Yeah, but just a minute.
Just a thought.
First of all, you don't change the mass of the ship. That's impossible. You don't change the mass. And even if you could change, it wouldn't help. It wouldn't change anything.
Impossible is a very dangerous word.
No, you don't see. You don't understand. Look, I understand. You understand certain engineering. You understand parts of physics, but you do not understand the part of physics relevant to that question, because it's a totally crazy, stupid thing to even suggest. And even if you could do it, it wouldn't help.
If it's okay, let me jump back in. Then you were talking about the white holes, and I'm going back to the weapons part of it. So if you have a metamaterial covered hull, if you were able to ablate part of that hull, or perhaps even just darken it, damage the metamaterials, would that create kind of like a pinhole leak that would cause the vehicle to destruct?
Oh, sure, of course. Yeah. Yes. But the thing is, I see what you're saying. Can we shoot down a Tic Tac? Yeah. Well, maybe that happened at Roswell in a few cases where they shut down flying saucers just with BB guns. No, that's possible. But the thing is this. If they want to, if you have a Tic Tac with that kind of technology, you can create a white hole kind of shield around it so that couldn't happen. If it's switched off, of course, you could destroy it. It's delicate. See what I mean? Yeah, so it just depends on, maybe they switched off their cloak field. They switched off their, it's just like Star Trek. They switched off the shield. If you switch off the shield, yes, you could destroy it.
Well, and the reason I asked was, and again, I'm very ignorant on this, but my thought was, everything that I've seen so far, like when I interviewed Frank, he had talked about soldiers popping off rounds with their rifles and stuff like that. It seems like a kinetic weapon would be too slow. And if this thing is able to go through water, maybe even land, like Hal has said, kinetic weapons probably wouldn't be the way to go. But
we
some
don't know
kind of
that.
a beam weapon.
It depends on the precise details of how that craft is operating. I mean, if it's perfect and it's doing perfect anti-gravity, then that really implies that no energy can get in. So I think you would basically have to be able to figure out how to do like quantum cryptography on space-time at that point to figure out how to make a weapon to like penetrate that, because you can't even use classical energy to like get in there. But
you can't put photons on it. You're saying the photons would just go around because it's like a point particle.
I mean, if the thing is literally cloaked and invisible, it depends on the details of the field profile around it, right?
Let's put it this way. What's clear is that if with our conventional forces, if there's a hostile force with Tic Tac tech, they're going to kick our asses and we can't do a fucking thing unless we're lucky.
Yeah, but there has to be a road. There has to be a road also to some kind of deterrent, right? At some point.
Yeah, that's the road. But let me tell you something. Right now, the Americans are so goddamn stupid about this that they're not going about it in the right way. The Russians, I think, are, because the Russians take my work seriously. The Russians are working on all this stuff. And I don't know, that'll go for. Oh, and let me also mention another thing. Guess what? Guess who else follows my work? over 300 Iranian physicists in Tehran track my work on LinkedIn. That's easily checked. Frank, you use your intelligence connectors. Just go on LinkedIn. So look at all the Iranian scientists and intelligence operatives that are part of my.
Jack, they're watching all of this communication. Both mine, Jeremy's, Todd's. They watch everything. The Chinese, the Russians. I've had people checking my emails because I was getting spam emails coming from China. It's coming from Russia.
Yes.
You're not the only one.
I know that. Yes, I know. But I'm the only. Yes, I'm not the only. But I'm the only one that has stuff that really works. You guys are just fucking around.
Well,
what the fuck
okay.
you doing?
Let me.
That's the difference.
Right.
Guys, let me go to Frank. Let me go to Frank because he has his hand raised. So. Okay.
Yeah, thanks, guys. I just want to ask a quick question. So if we were trying to disable the field of this imaginary Tic Tac, or this theoretical Tic Tac, presumably to do that, it's going to take, and to have a weapon capable of penetrating it. So presumably that's going to take like a huge Manhattan-style project, loads of money, loads of resources, loads of physicists, loads of engineers.
Yes, of course. It's like the atomic bomb. You don't get anything for nothing. I mean, what, you're going to get gold, you're going to get bricks without straw. You have to put in money. But the point is, our guys are so goddamn stupid, because and the reason they're stupid, in my opinion, because they're depending on John Alexander. There's no shit from all about physics. They go to John Alexander, ask his opinion. They don't come to me to ask my opinion. And Eric Davis is okay, but even he's got issues. He's got
Jack, where's your flying saucer? If you got all the answers, who's building it?
Oh, don't be you stupid asshole, Sokol. What are you asking? What kind of idiot?
Guys, let's try and rein this back in, because
I'm a theoretical physicist. I make equations. It's like asking Einstein to build a nuclear reactor, and when he comes out with equals MC squared. That's not my job.
Yeah, and I'll probably have to do a slight editing here for
it makes it more entertaining.
They definitely made it more entertaining, Jack. Thank you.
Yeah.
Okay. Well, so I guess I should ask Mark. You guys were going to do a presentation also, right? Should we?
Oh yeah, we're going to show some real technology.
Okay. Do you want to go to that now?
I'm going to take a piss because I got a prostate issue here.
Okay.
Thanks for letting us know.
Thanks. Okay. Well, David, thank you again. Thank you very much, and thank you doubly for your patience.
I had one more question for David. How do you get your hair to go up like that?
No, Mark. Well,
it just does it on its own, you know.
Mark, you almost have that hair, so.
I agree with that, dude. David's hair is pretty awesome. I mean, that's got to be a hard look to pull off. It definitely stands out, and it demands attention, which is great for the younger generation who's watching these videos and going to create the future.
I also think it's kind of cool, but I still have to edit this whole section out now. So.
Oh, I imagine so, but live stream still showed it all. It is what it is. It's out there.
I know.
Jack wants to say what Jack wants to say. That's his prerogative to refine his own image for the rest of the world. I mean.
Well, and Mark has already said that my face has been bright red for the better part of an hour. So.
Yeah, man.
Yeah, mine too, man. Probably because I was laughing so darn hard listening to this controversy here. Very not what we would expect from an engineering conference at all, and probably not quite appropriate at all for the future. But we have a lot of room to improve.
Well, and you know what? I do appreciate Jack coming on, and behind the scenes, I've been asking different folks, and they said, "Well, let it go. We're doing great," and so I do appreciate it. But yeah, let's say thank you again to David, and then let's go to Mark, and Mark will do Mark and Jeremiah.
Thanks for the invite.
Thank you again, sir, very much.
Okay. Todd wanted to start to kick this off with his presentation. Me, Todd, and Wayne are all working on a similar experiment that has to do with dynamic nuclear orientation, or NMR, EPR, basically hitting samples with a laminar magnetic field, and then hitting it either with microwave energy or megahertz range energy, depending on the Larmor precession of either the nucleus or the electron, the valence bands. So Todd, if you can unmute yourself, you can start this presentation by sharing your screen, and we can get going. I'm going to mute myself now.
right, can you see it?
We can see it, Todd. Thank you.
All right. Okay, so like I was saying, I came out with a model of quantum gravity that is intended for engineering purposes. And I've been working on an experiment. And so I did a write-up here that'll explain what the experiment's about and why I'm doing it. So it's proposed that the gravitational fields may be interpreted as a reduction of the relative available driving power, the watts, of the electromagnetic zero-point field. Gravitational time dilation and length contraction may then be interpreted as a loss of power in the interaction between matter and the zero-point field. It is hypothesized that the loss of power is due to increased radiative damping within matter due to Larmor radiation at the Compton frequency. The relative damping factor affects the relative ground state energy of the quantum mechanical harmonic oscillators such that the mean square fluctuations of matter reproduce the behavior attributed to and resulting from the space-time metric of general relativity. From this principle, the phenomenon observed by a distant observer that are attributed to gravity may be reproduced using a variable relative damping factor acting on the harmonic oscillators of matter. Using nuclear magnetic resonance to stimulate Larmor radiation, experiments may be conducted which demonstrate gravity and anti-gravity accelerations without the need of planetary size masses and energies. Okay. So just really quick, because this is from my presentation before for those who didn't see it. I use scalar magnetic flux, quantized scalar magnetic flux. This is the basis of resistance because ohms is basically flux per unit charge. And the scalar field is here, and it's the variable that is used to change the gauge in the Lorentz gauge. And this variable has units of magnetic flux. So when you take the derivatives, you get your electromagnetic gauge potentials, but this scalar field has no effect on electric and magnetic fields, for example, because you take the gradient, curl of the gradient, 0. So, but this is the seat of the behaviors that I'm about to discuss. So, assuming, and this is part of the hypothesis, that the Larmor precession frequency is also the Compton frequency at that scale of an electron, just as an example. And that the rest energy of the fermion or electron could be written as mc squared is Planck's constant times the frequency. So, and that frequency would then be the Compton frequency. So we assume that the frequency is the Larmor precession frequency, and then the gyromagnetic ratio times a scalar magnetic flux value gives us this frequency. And that gyromagnetic ratio is given to us as 28 gigahertz per Tesla. And so you back calculate to get the scalar magnetic flux density, which is about 4.5 billion Tesla at the scale of an electron. So that's where your G over C to the fourth comes from. It's a huge number. And that's the energy density in the zero-point field at that scale. But because this is a scalar field, it has no direction. And so the statistical average is 0. Okay, so when you have Larmor precession, you have a radiated power, and the fluctuation, the mean square fluctuation in radiated power is this equation. And from the zero-point field, proportional to omega cubed, you get a power fluctuation that is this equation. And when these two are equal, for that particle in that region, space-time is flat. There's no motion in that. There's no curvature or gravitational field. It could be different power values, But as long as these two are equal, then the particle is in equilibrium with the vacuum. And now you introduce a damping factor from the Earth, for example, and it's a very small damping factor. But with this damping factor, the power, with the square root of this basically, is losing power. The particle is losing power at a rate of 8.76 times 10 to the minus 29 watts per second from its Compton frequency. And that leads to time dilation and length contraction. The proton would be slightly slower, faster. And the good news is that regardless of that 4.5 billion Teslas, a 1 kilogram is losing about 100 watts a second. So that's not an unreasonable number, 100 watts per kilogram per second. So my experiment that I'm working on, and I've been working on this for the better part of 2.5 months now, putting everything together, is to demonstrate I can generate the generation of repeatable nuclear magnetic resonance signals and control of the Larmor precession frequency using a uniform magnetic vector field applied to a sample of deionized water or other material samples. Measure how acceleration due to periodic oscillation of the sample, like bounce the sample on a spring or a rubber band, how that affects the acceleration affects the change in the Larmor precession frequency. Then apply an oscillating magnetic vector field that replicates the changing Larmor frequency previously measured in an attempt to exert forces on the sample at the same oscillation frequency. So this is grabbing hold of those fermions and trying to exert a force on them all together, all at the same time, all the particles moving, accelerating uniformly. We then apply a static magnetic field vector field gradient and attempt to nullify the weight of the sample. We also do the reverse the field gradient and attempt to increase the weight of the sample, and then repeat for various other materials. Now this is all with a vector field. I haven't yet figured out how to do it with a scalar field. When I do, this list will be repeated. So this is my little lab bench over here. And this is my setup, or the initial part of this setup. I have a pair of Helmholtz coils here, 44 turns. They can generate a field of up to 300 Gauss. And then I have a 9 millihenry coil here that is actually wound in the same direction as the Helmholtz coils so that I can create a gradient in here. So I can either have a nice uniform field in this area, or I can have a gradient field passing through it. The field lines would be in the same direction, but it would be stronger here, and I can get a gradient this way. So this is a close-up of the coil. Again, it's a, I ordered these in pairs of 2 of them, and they packaged them very poorly, and they knocked together all the way here until the tie wraps broke and the wires came loose, and I had to have them send me another pair, and they did the exact same thing again. So then I had them send me another pair, and I told them to individually wrap them, please, and I finally got a pair that were usable. I found out that in my neighborhood, I have a lot of stray magnetic fields. It varies quite a bit. So I got some at Paul Murad's suggestion. I got myself some high mu 80 sheet metal and built myself a 0 mu chamber, a 0 Gauss chamber. So this is actually 3 layers of high mu 80 mu metal and a bottom. It's 12 inches in diameter, and then another layer that's about 1/4 inch less than that. Oops, I can't hit it. And then the inner layer is 8 inches. And so there's a bottom, and these are the results. Where I had 51.3 microtesla previously, now I have 1.7. So it worked quite well. I have a little bit of extra field. Most of it is in the Z component, probably because there's no top on it. But what I did was I added a thin coil here in between to null out that last little bit of Z field. I don't know why it keeps doing that. And then this is my pre-polarizing coil, and this is my sample tube. So the sample goes down this tube, which can be weighed or bounced or whatever I want, and it sits inside this coil, and then I can adjust the magnetic field however I need it and take readings. And this coil is then attached to a circuit board that I designed. Excuse me. The schematic is basically a timer with a fourth order bandpass filter, and that coil feeds into a capacitor, making it like an AM radio tuned circuit. So I tune it for the frequency I'm looking for from the resonance of the protons. And then I amplify that with a very sharp filter. And then that signal gets fed out this little SMA connector because my scope probes are way too noisy. And then that goes into my oscilloscope. And then that coil hooks over here to the board, and the MOSFET is used to charge the coil to polarize the water. Then when the coil lets go, it is clamped, the voltage is clamped by this metal oxide varistor and drained very quickly by these resistors. So it's over damped. So I don't have any oscillation. I don't let the voltage reverse or the current reverse, because all I want to do is align the protons along the coil and then let them relax back to the Helmholtz coil field. And in that way, as I can, the harder I polarize them in that direction, the faster I can get them spinning. And then as they relax back down, we'll watch that with the scope and can measure the relaxation time and the frequency. And then varying the magnetic field, I can control the frequency. That's the goal. This is where I'm at right now. So I designed this board. The boards came. I built one using 555 timers, and it would work for one frequency, but I want to try multiple materials and multiple frequencies. So I restuffed the board, and I put 4 capacitors in little sockets so I can change them out and change the value and tune it to different frequencies. And and then I did a Arduino, which now controls it, and I can control the timing and change it to however I want. So I can have a program that works at 2.5 kilohertz for water, and I can have a program that works at 1 megahertz for other materials. And so I should be able to do NMR and electron parametric resonance with this setup, because I can vary both the frequencies, the tuning, and the magnetic fields. And so I made a little magnetic probe here with some Hall effect sensors, which I can drop down in there to test the field and see what strength it is. And with the Arduino, I can actually log that data. But I need the oscilloscope to actually see the signal because the Arduino is way too slow. And so that's it. That's where I'm at right now. My goal is to, keep working at this. I need to get an accelerometer, and I need to get all this put together and tested and start recording some signals. Seriously, I just finished writing the program today, and it took a couple of days, and stuffing the board took a couple of days, and I had to work too. So it's coming along pretty good, and hopefully soon we'll have some data to share. So that's about it. You have any questions? I'm open.
Let me see. We've got Jeremiah and Eric. And why don't we go to Eric? Eric, would you like to go first, sir?
No.
Oh.
I'm explaining what I can explain in the messages, and that'll be it.
Okay, I've been talking. I haven't read anything yet.
Oh, I'm sorry.
I'm not posing a question.
Oh, okay.
I apologize. I think probably me
But
and
Todd,
both.
Todd has it. Todd, in my opinion, okay, it's my personal opinion. Todd is on 98.999% of the correct track.
Thank you.
In my opinion, but I don't know anything because that's what we've all been told. So I'll leave it at that. And I'm done talking.
I think you know things, Eric. I think you know a lot of things.
Honestly, I'd like to have Eric on. I mean, that guy knows so much. I would love to have you speak for an hour. I would love to pick your brain in the Q&A.
Okay, well, let's do that then. Let's get Eric as one of our speakers. And I will write him as soon as I finish apologizing to David Chester. So.
No worries. Yeah, I also figured I could provide a few comments and maybe a question at the end. So I see a little bit more detail about what you're talking about in terms of this scalar. So yeah, I know what that the gauge dependent scalar, that's usually gauge dependent, that kind of relates to longitudinal effects in certain modifications of electrodynamics. As far as I've looked into it, you could make a very solid case that Maxwell's treatise does allow for that scalar, especially when you look into the work of Heaviside shortly after. So I just want to say that
in fact, Heaviside is the one that gauged everything out. So he's the one that screwed everything up.
Yes.
So he defined. So in order to explain the magnetic vector potential, he comes up with the magnetic field that equals the curl of that. And so then you can now arbitrarily choose your gauge. And so there's the Lorentz gauge and there's the Coulomb gauge and whatever other gauge that you want to invent for a particular problem. And those things work well for almost all of the current problems in physics and especially electrical engineering, because everything like Ampere's law, right? That test is done with copper wires, and they're identical copper wires. Okay, if you change the material in one of the wires, and you make it the drift velocity higher in one of the materials, or the geometry different in one of those wires, you're not going to get that force, that Lorentz force between the wire that you normally see. You're going to have additional effects that are indeed difficult to measure, and they're not obvious. But when you do it correctly, you observe them. And Maxwell had 20 equations originally derived, and they were reduced to 4. And the magnetic field, in Richard Van Durek's opinion, my opinion, and his strong opinion, I mean, he's 100 times more intelligent than I am, but he has figured it out, I think. Of course, maybe he's wrong on some things, but he's not wrong on everything. And the point is that you have to look at the material of the conductor that you're using when you're applying Maxwell's equations, and you have to look at the geometry of that conductor versus the geometry and material of another conductor that's interplaying with that conductor in different reference frames. So you might have one in a rotational frame and one in a stationary frame. You might have two flat surfaces, passing across each other parallel or perpendicularly, and you'll get different effects, right? And there's also a way to amplify the effects. And so there's these cross product and dot product terms that can be amplified with geometry. And then so you can get, more powerful effects out of that. And Richard goes into this, and so I can say this, but the scalar potential, when it's built up at a coordinate position in space, that dilates time. And when you realize that the gravitational field really is a time dilation gradient, where things accelerate in the direction of decreasing time dilation. Black holes have huge time dilation, right? And you're sucked into it. But time does not stop. So the frequency of a photon never goes to zero. So it's important to note that time. So there is an absolute frame and there's an absolute clock. And that's what Dr. Randy Mills has figured out. And I don't care what anybody thinks about Dr. Randy Mills and brilliant light power. He is correct on pretty much everything in his book, and his power source works. It draws from potential energy in the hydrogen atom that's available. There's no perpetual motion involved. But the point is that really, in terms, let's talk about propulsion and not energy. It's mostly about time dilation. Now, I don't know that. So there is some aspect to warp speeds and warping and faster than light involved in this, but Richard is that is something that's unclear, and then also that's something that Richard handles. But so Jack has this warp theory, right? And all the power to him, because we're not going after a warp theory. We're not going after faster than light. Maybe Jack is perfectly correct. Maybe he knows how to go faster than light, and maybe we don't. Maybe we probably don't, right? So who cares though? If you can get a propulsion mechanism to give yourself a hoverboard, or to launch cargo into space, or to keep a satellite stationed in orbit, that's very useful, right? And there's that's so a lot of it has to do with time dilation, and there is a way to control the clock rate in the local environs. And so when you see these craft, you look up in the sky, you see this craft jump.
Ooh, lost audio on Eric.
Is sped up. So that quarter second that you experience is actually maybe 5 seconds for them. So they're a leisurely acceleration into that, right? And their ruler expands. And so in other words, literally their rule of measure expands. And so instead of having a 3 meter, a 1 meter stick that you hold in your hand, their 1 meter stick is 10 meters long. And so to get to the sun, just on a normalized fashion, you might have to travel 10 meters, but they only have to travel 1 meter to get to the sun. You understand? Because their ruler is expanded. You understand what I'm saying? So I think that's in part how it works. I don't know that maybe there is no warping, and maybe it's just a change in the rule of measure and control of the local clock. And so Jack talks about time travel and all that kind of stuff, and maybe he's right, but I don't think it's time travel. I think it's the mastery of time. So you can control the clock rate, but you can't fuck around and go back in time and forward in time and all this bullshit. And maybe I'm wrong, but I don't think that's possible. I think you can control the clock rate. And the interesting thing about controlling the clock rate is, let's say what I call them are engineered habitats, right? So you engineer a habitat where the clock rate is increased, and now you can suddenly perform more computations per second than you can outside of that environment. And that's where things get really interesting, because then if you can do that, then you have the advantage, right? So if another country can do that and they can compute more per quote unquote second, you have a disbalance of power. And so these technologies have to be, if they work, they have to be accepted by this world civilization, and they can't be They can't be fought over. They have to be used for peace. Do you understand? We can't. We have to tear down the Berlin Wall along every border of every nation, if you understand what I mean. And I'm not talking about socialism. I'm talking about we have to tear down all of these Berlin walls and real
globalize.
Lost again.
Yeah, he's coming in and out. I still have a question yet for Eric before he ditches.
Yeah, go for it.
Tim, you're muted.
Eric,
I think he time traveled.
Jumping in.
Tim, you're muted too. Just I seen you trying to talk there for a minute. Check your mic.
He went to another dimension or something.
Yeah, Eric, do we still have you? Or no? Are you gone? He's gone. He's gone. Tim's out. Who do we have?
They got him. All right. So I have a question for Todd. If he's here, we can roll to that.
I'm here. Can you hear me?
All right. So Todd, I had a question. One comment said that you were totally right about high magnetic polarizability also changing the impedance and help to trap xenic surface waves or surface plasmons. And these different like surfaces of like those layers in the metamaterial. But how do we prevent accidental stirring of the water in your experiment too? Because you had that water sample, and do you think we should use solids to avoid accidental like stirring of the molecules in the liquid?
Well, I mean, I looked at I can't think of the guy's name now. Damn it. I looked at the equation that that governs this, and the temperature difference between 0 centigrade frozen water versus room temperature water, it's pretty much negligible. And unless you're down into the low Kelvin, it's not going to make a heck of a lot of difference. So it's the population density, that you're going to get. But you do, I mean, there's probably better materials to use than water. Probably the mu metal is a better material to use than the water, but I haven't spent the time looking into it yet because I'm just focused on doing what I started out to do.
Right. This is just a basic preliminary setup too. I want to remind the audience watching that water is used in laboratories. That's what's used in most NMR machines. Is they put samples inside of water when they analyze them. So, I guess unless it's boiling, it's not really a big. They're not moving around enough to make much of a difference.
Right. And this is a proof of concept. So it's it's a learning experience for myself because I've never done this before, and 5 years ago I never thought I would. So here I am trying to make a nuclear and magnetic resonator in my garage. We shall see how it goes.
You can always use ultrasonics or acoustic waves to effectively vibrate or mechanically disturb that material without having to worry about it sloshing around too. If you didn't want to get other weird or compound erroneous measurements.
Yeah. The thing with the measuring the change in the Lamore precession frequency with respect to vibration or oscillation, so I can get a calibration of how the frequency is affected with the rate of acceleration, which is the connection to gravity, right? So that's what I want to measure. And that measurement is going to be difficult because it's not going to change very much at low rates. So I actually need something that's going to make it accelerate quite quickly. And I have some piezoelectric transducers, thanks to Jim Woodward, that I can use to make some really high vibration frequencies. And I have the frequency generator to do it. So
that you do.
So this is going to be an interesting couple of months to get all this together and test it and working. But, and then after that, I've got several of these the mega drives that I made to test and some new ideas that I have on my own. And I finally have the springs necessary to measure a change or measure some level of thrust, hopefully. If
Did you
there
get
is.
the same ones they talked about at Estes Park or something similar?
Yeah, the same ones, and a couple of others that are a little stiffer. But I got enough of them to make like a bed that it can rest on, so that if there's any kind of thrust at all, it'll change height.
Now you built your Mega Drive though, right? Or did Woodward send you something?
No, I built them.
Testing.
Yeah, you built.
Testing.
That's awesome.
I
We
had
can
a
hear you.
buddy of mine
hear
that
you.
works in the metal shop, and he did the metal work for me for a bottle of tequila.
That's not bad.
Okay, sorry guys, you can hear me okay now?
Yes.
Yeah, you're all good, Tim.
Okay,
I
I'm
want-
sorry. I'm sorry about that.
Machine. Your work on your machine, Todd, is just gorgeous. Those coils and everything, they're sexy, man. I wish I had built something that looked that good. Now, if it works that good, then we'll all really be impressed.
Yeah, I hope so.
Todd,
Paul.
it sounds like you're doing some good work.
Thanks, Paul.
I'd like to make some other comments. I've been rather quiet about all this, especially about Smiling Jack. I have argued with him for years, and you see it in the write-up, that, hey, it's great to have a idea, a theoretical idea, but if you can't put it together, it's useless. And he's beginning to sound more like an engineer. But the question here is that, I have one thought, and that is, when you have this metamaterial on it, you've got to get it in the same phase at the same time, or you might have some problems. Like you may have the wrong phase where it's gravitational in part of the spacecraft, and if it's anti-gravitational in the other part of the spacecraft. Now, either you're going to tumble around like crazy or you're going to tear yourself apart. So there's a lot of engineering materials that have to be looked at. Now, Jack made the comment about historical sense. As far as I'm concerned, I've looked for as much information as possible about the wrecks of UFOs and the materials that were involved. And with only one exception, a piece of Russian work in a hill that was identified with Paul Potter, they talk about 3 balls. I believe in the constellation work of Potter and so on. We have 3 spheres rotating, and apparently there was 1 sphere, and it had some funny material. But the rest of the spacecraft showed nothing. I've never heard of any spacecraft wreckage that has been involved with metamaterials. So I raise questions about that rationale. I'm not saying he's wrong. I'm not saying he's right. But I'm just saying, looking at the evidence, it's tough to say that, hey, you could see something like that.
I believe there's this researcher named, it's like Elizabeth, is it Moulton Howe or something like that, who allegedly may not had some material and gave it to put off. That's just what I've heard. I have no idea if it's true. So
All I'm saying is what we should do is look at this type of stuff out there to see if the evidence exists. Now, last week I made this comment about the magnetic field, and I'm beginning to wonder right now that if you look at the Lorentz force, there's a 1/c involved. So the magnetic field may not be as strong as an electrical field because you have the 1/c term on it. So I'm beginning to wonder about those things as well as other things, but that's as far as I'm concerned. And I'd like to suggest that if anyone blew any of you guys away in terms of personalities and stuff like that, ignore it. Ignore it. He's a nice guy. I still like him, even though he is an asshole. So all I'm saying is hang in there, and maybe you could find something goodness out of all this. And with that, I'm going to eat dinner. Thank you.
Thanks, Paul. Hey,
Well, I mean, Paul, is there a spacecraft in the possession of the United States?
I would argue that based on
yes,
what I know,
yes or no?
not for me. No, I didn't do it work-wise. If that's what you're hinting at, well, I'm saying
I'm not hinting at anything. I mean,
okay, as a private citizen, I believe in Roswell. As a private citizen, reading the open literature about the Russians, they've shot a few of them down. Okay.
All right. So who's the best person to ask in the United States?
The other question that you have to be concerned
I
with.
can reply to that.
Okay,
There is,
well,
I'd like to say something here. I was contacted by a very credible witness who is afraid to go public. He's seen this many years ago, he and another eyewitness. He testified to me in a letter, proved his credentials. He's an engineer, like many of you guys, who testified that he was very close, he and a friend in the New Mexico desert, to a UFO. Apparently it was as close to it as you could touch it. And he saw written on the UFO, U.S. Air Force experimental. I believe the guy.
okay, that's
I believe
fine.
the guy.
That's
And
fine.
he was very credible.
But let me mention another factor here, and some people were hinting at it, that can you destroy a UFO? And it seems like whenever people are being abducted, if they're using a flashlight at night, these things start moving around. And if you recall, there was a shuttle picture film of an object moving along, and then all of a sudden it moves away, and this big splat comes through it. So apparently, these UFO guys are concerned with lasers. And that might be the way to look
Sheila
at it.
Wignall, the Secretary of the Air Force, Sheila Wignall, who's also an MIT alum, she sent me pictures of a telescope image, a few of them, where, you know, when the Challenger blew up, that there was there was essentially some type of beam that blew it up.
Yeah.
And she did this while she was the Secretary of the Air Force, and she did it because we both went to MIT. And I still have those pictures, but they're not very convincing. But I mean, why would she send me that, right? So my
There's
question is,
another picture, another film where it's going on against a UFO with a ICBM.
Of course, that was on NBC News, I think.
Somewhere. So, you know, how real are these things? I said, well, gee, you know, why not?
All right, so who do we ask in the United States if there's a spacecraft in the possession of Department of Energy? Who do we ask?
I got involved with the Challenger details or about it getting destroyed, okay? And the question was the problem occurring after 73 seconds, or was it happening right away? And guess what? With all of the shuttle pictures for the Challenger, NASA said, we didn't turn on their cameras. We did not.
No, I'm sorry. Not the one that blew up going up, the one that blew up coming in.
No, I'm sorry. The one that went up. The one that went up.
No, I'm talking about the one that blew up on its way down.
Discovery.
Oh, shit.
No.
Discovery, yes, that's it. The one that blew up on its way down, Sheila Wignall sent me photographs of that getting hit by something, and that's the one that's of interest. Not the one, not Challenger in 80 or 84 or 88, whatever that was. It was after that.
Having worked on the shuttle, being an aerodynamicist, and doing all sorts of great things with lasers, I believe that the wing leading edge of that thing was broken with ice. Just like it burned out, because it starts talking about the wing disappearing and then the wheel getting hot and the way everything went. I believe that. Right. But to answer your question, the issue is that you have to look for the truth amongst yourself. You can't depend upon governments because they have their own agendas, okay? And you will never know those agendas. For example, I'm going to be giving a presentation about UFOs, about how it started. And I'm suggesting that in 1947, Einstein sat down with Oppenheimer and they laid out the rules. And they kept those rules going for over 70 years. And they identified, just like Jack said, we can't do a damn thing about it. We can't chase them. Well, you know, like I said, the Russians have been engaging them with Su-27s and other craft and stuff like this. But that's the way it goes. So you have to look for it yourself. You've got to look at some enigmatic material. and half of what you see you could throw away, but the other half might be, pure gold.
No, but I mean, I don't want to, that's not a productive. I wanted to ask somebody who knows the answer, right?
What is productive?
Well,
and what
so
do you do to get
so
the
if we have
answer?
Sounds like he doesn't
spacecraft
know.
so if we have a space,
Eric, let me respond.
if the Department of Energy has a spacecraft in its possession, then other people should be allowed to inspect it so that we can all help understand the propulsion mechanism.
Well,
so who do we ask? So
You
who knows?
heard the argument that if this
We
gets
should do a
out,
whole separate conference on this because I have a lot that I'd like to present. I think we should let Paul present, and I'd like to present my whole research because I have a ton of research that I've been doing into Roswell. I'm going to be talking and debating on that next week on with Cal Korf and Kevin Randall and some of the with skeptics and other researchers next week and stuff. So let's save all this for like another separate conference and get back.
Okay.
Yeah, let's do that. So, Jeremy, will you email me about this? Just email me.
I
We'll
want to
get it
set
on the
that up
books.
with Paul because I think it would go right in tune with that, and it's separate from we should definitely set that up because this is something that we should hash out within this group and kind of filter through for the actionable intelligence, like Eric was saying.
Okay. Bye all.
Thank you again, sir.
Definitely.
Paul,
Thank you, Paul.
About the metamaterial and having gravity in the front of the ship and anti-gravity in the back of the ship. Oh well. You didn't hear me.
Oh, okay.
But
okay. Well, Todd, thank you. Let me see. So I'm going to try and organize this back up. I'm going to mute. Let me see. I'll mute Mark. So does anybody who has questions next for Todd? I guess that would be the.
I still had some comments and questions to
go ahead, David. I'm sorry.
Oh, that's fine. So I just wanted to say that the scalar field that is going in that Lorentz gauge thing, I know exactly what's going on, and this is kind of a controversial topic. And the main reason why academia doesn't accept this is because it pokes a hole to the entire idea of gauge invariance, which is an important foundational concept for everything that's going on here. But I don't think the solution is to say that we should throw away gauge invariance, which I've done some work on this and I haven't published on it because it's very subtle and it takes a while to figure out. But the metric affine gravity theory is the gravitational theory that gauges how you have rulers and metrics and length and stuff. So, so I heard some comments before and people say, oh, that's not, maybe gravity actually is this. That is exactly what this metric affine gravity framework is. And within that, you can reconcile some ideas such as Tesla or others back in the day who would have preferred variable speed of light models rather than curvature. And that might be an interesting perspective to take. But I mean, in terms of convincing academia, a lot of work is needed done to go into the complicated math and then make it simpler to see if we can get back to these simple ideas that are kind of being talked about, which is kind of why I think a lot of the Heaviside gravity people like it because it's so simple. But so, I mean, I think you're on the right track, Todd, in terms of focusing on that potential. But then at the same time, I wouldn't just stop and say, well, like we fully understand gravity from that perspective. So I think in time, there can be this story that will come out where the way we think about gravity kind of unifies the ideas of Tesla and Einstein in a more friendly way, because Tesla was his whole point was saying like space-time is not a thing. It doesn't have properties, right? It's like we're measuring these events, but there's nothing there. The space-time, he's saying there's this ether, this material, and really that's what all of the stuff that I was talking about before is getting back to. So it actually is in that gravitational framework of general relativity, if you refer to it as the most general theory of relativity, because that's what it is. But it's just taking time for quantum gravity people to realize that. And so once all of that occurs, there should be simplified theories that come out that might be helpful. So yeah, as you're doing this research, don't feel like you're completely alone, or don't think you're as radical as you might think you are, because there is a chance that conventional academia could reconcile all of this.
I appreciate that. I just wanted to say that like I've been working on this for over 30 years. And so I'm 59 and a half, and I've been doing this for a long time since I started dreaming about this when I read my first book on Einstein when I was 17. So it's a little bit a long time coming. And the I've tried to get published. I've had several papers published a bunch of them in an old journal called Physics Essays, because that was the only place that would publish me, because I'm not associated with any research organization, or I mean, I've got a Bachelor of Science from UC San Diego, but I'm not affiliated with them, so they won't publish my work. So I decided to bypass all that and go straight to what do I need to make it work. And then once I have something that works, then maybe people will notice. But so that's where I'm at. One thing I'd like to mention though, Jack wouldn't let me finish because his cosine theta idea is wrong, and I can explain why. And the reason it's wrong is like in my model, and as I was saying, gravity is a loss of power. So time dilation and length contraction are the matter itself is losing power because it's not being excited to those energy levels anymore. And so it collapses in on itself and free falls. Anti-gravity is the opposite. You're exciting the matter, and exciting the matter, you're doing work on it, just like lifting it to go uphill, lifting it up. You're doing work on the matter, which inflates it. Energy, the matter gets excited, it inflates in size. As the matter volume increases, the energy goes up slower. So the energy density is going down as it inflates. So as like I lift this battery up, its energy density went down. And that's the nature of negative energy density in warp drive and in this equation, is that in a variable speed of light model, the speed of light here is slower than the speed of light here. Same thing. It's the same procedure. It's the same process. And so you don't need a negative energy density that's below zero. You need a negative energy density added to the positive energy density of matter, which makes it less dense.
It's all about how you calibrate everything you're working with. So it could be possible that different calibrations actually are agreeing in complicated ways. So, that's why I like to stick to general relativity, just because there's so much and stuff beyond that, just because there's so much experimental success. I mean, cosmology is a mess too, but that is being figured out with conformal gravity. And so, I mean, in terms of other theories of gravity, like I'm not trying to shut them down or anything like that, but if you're going to use intuition from that, then we need to first make sure that that theory is, comparably successful to, can we get the perihelion of Mercury? Can we get all these different things? So, yeah, just comments, but
if I could jump in, David, I really like that. When you just expressed the framework of using a model, right? And I mean, Todd may be using a slightly different model. I've heard, because I've done a lot of interviews in this area, I've heard probably hundreds of different models. But I think it's always important to remember that we are working within these frameworks, right? Now, whether that's custom built or like Dave is working within general relativity, or there's QM, but and each of these models has limitations, and they've got their own structure to them, and so I think that's one of the things that I've seen is a lot of people run into trouble because they're kind of like, well, this is how it is, this is how it isn't. But then that always kind of relates to the model that you're working with too, right? So.
I just want to say that the back in the late 1990s, Hal Puthoff and I both developed a concurrent model based on, we called it the polarizable vacuum model. He called it the polarizable vacuum representation of general relativity. And in that original paper, he showed how it agrees with the perihelion of Mercury and time dilation and all the experiments of general relativity that rely on basically the Schwarzschild solution. And I came up with a similar theory. And then I took it one step further because I took it down into quantum mechanics and damping and QED, and showed that when you add a relative damping factor to the equations of QED, you get the polarizable vacuum model exactly. And it's already been shown to match general relativity in all the observable experiments. And we did this back in the late 90s and early 2000s. And Jack now, puts a refractive index in Einstein's equations and, claims he thought of it. But Hal and I were doing this with the refractive index since 1998. And we had the polarization and the magnetization in the TUV tensor, decades ago. And I wrote a paper in 2003, warp drive propulsion and Maxwell's equations. And on that paper, I, hypothesized that the effect you want lies in the hull of the ship, not in the space around it. And so all of this stuff has been around, basically I'm about 18 years ahead of where Jack is on this. And I know what's going on. And Tim, in regards to what you just said, I agree. Everybody's got a slightly different model. But at times when people are presenting their model, I can see where the differences are and I can tell which one is right and which one is wrong. And sometimes I know it well enough that I can tell you that. And
I won't disagree with that. Although the thing that I do like about models is that I think it helps prevent fist fights, right? So that's always a bright spot. It's much easier to agree to disagree, I think, that way. So, and I am not disagreeing with what you're saying.
I'm a natural-born educator, so I like to teach people what's so and unfortunately I like to correct errors and fix things, and a lot of people don't appreciate it, but I appreciate that David does and Eric did, and I know you guys do. So I'm I'm happy to be working on this stuff, and I'm happy to be part of this group.
Yeah, well, and thank you for presenting. So if it's okay, let's jump over to Mark next. Todd, if you're all set.
Yeah, I'm done.
Okay, thank you, sir. Thank you again.
Thank you. Okay, so we have a little group called Falcon Space, and this sort of melded into APEC over time. And Jeremy Reyes, Todd Desiato, and Jeremiah, and also Sean, who's joining us here just on audio, are all part of that group. And I'm going to show you a little presentation, just a whole bunch of pictures, giving a bit of a timeline of how we got to where we are and what exactly it is we did. So starting off, we have, let's see, can you see that now?
Yeah, I see a picture.
Okay, so this is me and Jeremy. He came down to the lab in February of 2019, and Jeremy, of course, alien scientist, he went on a road trip down to Virginia to the to some library in order to do some research on anti-gravity. And I hit him up on the way back, said, "Why don't you stop by the lab, check this out?" This led to a live stream tour of our first warp drive laboratory. This was back in March. Not much was learned over here. We were talking about T-Towns and Brown and stuff, but in the comments to this video, which I can't access right now for a moment, for some reason, was the first time I had any inkling on this experiment called Alzafon, or Frederick E. Alzafon put out a paper in 1981 called Anti-Gravity with Present Technology, Implementation Theoretical Foundation. It was published in the Joint Propulsion Conference in Colorado Springs, Colorado. And this is a paper that is fundamental to the work we're doing. Todd Desiato's theory is very similar to this. And I've heard several other theories that sort of connect with the same fundamental experiment that he outlines here in the paper, which I'll show you in a moment. It's basically, again, a laminar magnetic field or homogeneous magnetic field around a sample of aluminum with a little bit of iron added to it. It's important that the aluminum be of very high purity. The iron is added as a stepping stone to sort of build up what's called dynamic nuclear orientation, which happens in the nucleus of the atom where you're orienting the subatomic particles. Todd is trying a similar thing, and Todd, correct me if I'm wrong on this, with nuclear magnetic resonance, where he's hitting the Larmor precession of the entire nucleus, versus what we're doing over here is hitting the Larmor precession of the valence electron. The valence electron is the same for every material, so it's 28.025 gigahertz per Tesla. So no matter what material you stick in there, you are going to be hitting the valence electron if you get the numbers right. And accuracy is key over here. You need like 1 part per million in order to hit these frequencies correctly. 28 gigahertz, that's 28 billion cycles per second. So if you're not accurate, it's like at least 1 millionth, you're not going to, you can be hitting it wrong and weakening the Larmor precession. So it's very important to get everything correct in this experiment. So the first thing I purchased was this signal generator. Found it on eBay for a steal. It's capable of 9 to 9.5 gigahertz, which is the frequency range that Frederick Alzafan was using when he tried this experiment. When he tried it in 1994 in the basement of a big university where they had an EPR machine. And apparently they got weight loss of 80% in a 1 gram sample within less than a second of turning the device on. So this was, very exciting experiment. So I decided to go forward with it. We got the signal generator. Wasn't sure what to do next. There's the back of the signal generator. Interesting thing about it, it is serial number 110. So that probably means it's the 10th one that was ever built. Never found another one of these since. It also has, I don't know if you can see over here, there's the capability of changing the pulse output, which is important because you don't want continuous RF controlling the electron spins. You want it pulse it every like 5 milliseconds or so that then the orientation of the electron, which is then energized up, can move into the core. And the iron is in there to help transfer the orientation to the aluminum, and the aluminum is there because it acts as a reservoir of dynamic nuclear orientation. This is how I understood it from David Alzafan, who wrote a book on it. David is one of Frederick's 2 sons, and they both kind of are very into this science. And David wrote 2 books on the subject, and Daniel Alzafan was working with Hathaway and some other lab. He was also working with Hal Puthoff and some other physicists related to NASA, and they've seen some very strange effects with this experiment. So I really wanted to move forward with it. So what we did was we went to AlienCon. This is me and Jeremy at AlienCon, and we presented over there in one of the booths, showing off all different types of anti-gravity. We met a couple very interesting people, including this guy, Carl Miller, who is an RF expert, and he agreed to help us out. He donated some equipment and sent it directly to the lab. This is a RF antenna for that range. It's the X band of microwaves, so it's 8.2 to 12.4 gigahertz, and we're smack in the center of that with 9 to 9.5 gigahertz. There's the other side of it. You can see that is the entire antenna, because gigahertz are really small frequencies. I think the wavelength is somewhere around like that long. You're talking about like 2 inches or so. He also gave us this nice cone, or the waveguide, and some wire as well. And we also got this for making the material, the aluminum iron mixture. Picked this up also on eBay. As you can see, it has 5 nines on it, so it's 99.9999% pure aluminum slugs, and we melted that along with a little bit of iron, and we ended up with these little samples. And this is the force sensor that we used. Jeremy actually recommended that. There's very few scale measurements that graph on a computer that are available online. They're very difficult to find too. So this was a great find. As you can see, it's not shielded in this picture, and we later discovered that that was a major problem because RF does interfere with the crystal inside that is essentially using the piezoelectric effect to give you a voltage, and so we had to shield the hell out of this thing. And in fact, several layers of shielding went on it at the end in order to get a clean signal. This is the test rig. And here is the electromagnet that we started building. A lot of work went into this electromagnet, and this is the first iteration of it. It's not connected at all. Everything was loose. And then I took it to a local mechanic, and we were welding it together. And yeah, I set this up. Here's the original setups. The red bucket over here is full of salt water because we're worried about just the extra RF in the room, giving us biological damage and whatever. So I filled the bucket full of salt water to act as a load for the microwaves. This is pick this up also off of eBay. Great deal. Goes up to 22 gigahertz spectrum analyzer. And it show you the the waveforms and pulses and everything. It's a really great piece of equipment that we picked up. That's my 2-year-old. He figured out how to turn it on. Oh, next came the well, we needed some sort of amplifier because the signal generator is putting out milliwatts, and we quickly realized that the most of the stuff being sold on eBay, the traveling wave tube amplifiers, are broken. Tubes are broken. So I bought one, it was broken, ended up returning it. And then I found another one that was pretty cheap, and the guy didn't even have a way of testing it. And he offered a full refund if it doesn't work. So he sent it over, and sure enough, it didn't work. But here's the exciting part. It didn't even turn on properly. And for an electrical engineer, when something doesn't turn on, that's usually an easy fix because it could be a fuse, it could be a transistor, it could be something simple. Turns out the problem was in the low voltage side that powered the tube. It wasn't in the tube itself, which is pretty much the entire device. And the most expensive component of this device is the tube. So I was able to fix that by the help of the manual that came with it. And it started working. And you can see it right over here. And that is the traveling wave tube amplifier. It puts out 20 watts. I had it set up with the scale over here, and there was a multiplication device, like a leverage arm with the sample in there. Here we can show you, this was after several hours of experimenting. I found that there was a certain spot where I was getting around 18 or 17% weight loss. To show you this briefly, it's around a 30-second video. Let's go back to 892. You can see the weight loss over here on the laptop. And I'm changing the frequencies very slightly. Yeah. The fans you hear are from the cooling of the tube. And here I'm turning on the, what was that? The attenuator. That's basically shut off the power. And put it back down to 0, and we can see some sort of weight loss was happening in the sample. Again, this is close to the noise field, so we really wanted to take it to the next level. But we did see some promising results with this experiment, so we wanted to move forward. This is kind of what we really need. This is a proper EPR setup, or you can use this for NMR as well. And I actually found one used out in California that we're looking at picking up. These things weigh a ton, or several tons actually. So the magnet we have right now has a cross section of homogeneous field that is probably around 1 inch and 1 inch by half an inch. We need something a little bit bigger to get a larger sample in there. Also, something that was brought up by Tanya, who's here as well, is that having a horn antenna like we had in that setup and bombarding it from the side is really wasting most of your potential RF energy. And it's not going into the sample. You're getting, less than 1% going into your sample. So what you really need is a tuned cavity, like meaning it's all encapsulated. You have holes for, string to hold it up to measure any weight loss. And that's something that we're moving on to next. The tuned cavity needs very accurate, you need to be able to move the parts in and out so that you know when it's tuned, and you need a reverse power meter to know when it's tuned, but that is all in the next iteration of the experiment. So what happened next was we were going to make some samples. These are, we decided if we're going to do dynamic nuclear orientation, let's just try a whole bunch of samples. David mentioned earlier Linton Moulton Howe's sample that had bismuth, magnesium, and I think it was tin or something like that, layered. So we have over here the bismuth, magnesium. We did it with iron as well, because according to the theory, iron acts as a catalyst to bring the dynamic nuclear orientation to other materials that aren't so ferro. And we are encapsulating them inside of epoxy. These are all the different iterations that we made, different mixtures of iron, aluminum, niobium, bismuth, bismuth trioxide, vanadium, copper, nickel, silver, tin, and magnesium. And we did 28 different samples. Jeremiah came down to the lab. He was helping me with Falcon Hybrid, which is the hybrid battery business. And at night, we were working on the anti-gravity stuff. These are all the samples. We made them in little tin cups, and cups, and we put them inside a vacuum chamber to remove all of the bubbles, get nice, clean samples. And we started setting up. You can see over here, Jeremiah's working with the setup. This is an isolator, what he has in his right hand. Isolator is like a one-way valve, like a diode in RF. This is the attenuator, and this is the horn antenna. And again, we're just putting the setup together. We also realized the magnet and the welding was a really bad idea, so we had to take that apart. And the next thing we did was try to smooth out the top of the the center iron cores. And we didn't really have much tools in the shop at that time, and we got a little creative. This is Jeremiah's idea. Let me show you exactly what we did. Bet y'all never thought Elgathon would look like this. We ended up rounding out the core pieces because the field laminarity was an issue. And they're looking good now. Okay, yep. So that was how we did that. And we finally had an entire test setup. This was like cutting it close. He was about to fly back the next morning, actually, and we were up late working on it. You can see over here, we got rid of that huge cone because it was dispersing the energy way too much. We want to concentrate the energy as much as possible. So I found this other cone on eBay and stuck it on. It's supposed to work for the X-band frequency. And here's the setup from the other side. You can see this is a Yagi antenna that's also for the same range, and it's attached to the spectrum analyzer over here, so we can see what's actually coming out the other side, make sure the pulses are correct. And this is the sample holder. This is the first iteration of the sample holder. It didn't work very well. We moved on to something better. There's some other angles of it. These are all these samples. This is the newer version of that sample holder. Went with just two strings on the side that were held down by weights, and this was 3D printed. And this was the newer version of the holder. So the electromagnet would go over here. We would have the scale measurement sliding along this top bar, and this bar over here is connected with some bearings and a little brass rod, giving it a very free range of motion. This experiment also yielded some results. It was in the noise range, but we did see something there enough to get excited, but not enough to publish. Here's the AutoCAD for the new device. I actually made it a little larger so it would fit larger samples. And here is the sample holder. This was one of the first versions of the sample holder. using little pieces of clay to tension the wires or these are actually fishing line that we're using. That allows us to move up and down. There was hysteresis problems because there is a little bit of iron inside the sample. We're talking around like less than 1% of the sample does have a little bit of iron. And these samples, by the way, are inside of epoxy. So there's tiny pieces of aluminum, tiny pieces of iron that are all mixed together. We didn't have the, what do you call it, that shaking device to the vibrator, the ultrasonic vibrator yet in order to disperse them properly, but it came out however it came out. And again, we did see something, but it was within the noise floor, so it's hard to say exactly what it is we saw. And here's the problem, it's out of alignment. We had to fix that. Okay, so this is the next time Jeremiah came around, we decided to get a little bit more professional. We found out the next door there is a humongous lathe that they do not know how to use, and they were more than willing to lend it to us or let us use it. The thing is bolted down to the floor. It's freaking humongous. And we straightened out the core pieces. This was happening during Estes Park. And we run out during the breaks and work on the electromagnet over here. You can see we also made new bobbins for the electromagnet, added a bit more copper onto it, and we got this Gauss meter over here from a local company because our Gauss meter broke. Everything was done sort of last minute. This was Ubered over from South Jersey. Turns out it had an analog scale on it that didn't work for us very well because we couldn't read it properly. And we had to return that. And here we are playing with checking the homogeny of the field, which is like the difference between the center and the outside. You want to make sure that there's same amount of magnetic flux or magnetic strength throughout. Okay, and this is the new setup with the new electromagnet. This is the power supply. We had to modify the power supply as well, changing out the pots to give us more resolution on the current, because the current is all that really matters. We added in a capacitor as well so that the signal or the load for the power supply would be a little bit more steady. And here's a close-up of the setup. This knob over here would control the frequency. This would show you where the frequency's at. This will show you whatever. This will show you basically how much current is going into it. But we realized that there wasn't enough digits on the current to really show you exactly, how steady this power supply was. So we added another shunt in, like custom-made shunt, and connected it up with this Fluke voltmeter. And that was down in the millivolts, and it showed us that the power supply was putting out a pretty steady power, and that is extremely important. There's it from another angle. So what happened next is with this setup, we started to get headaches. 20 watts of RF X band gives you a headache, and that was not comfortable at all. So we decided to finish building our Faraday cage, and Jeremy's over here putting in the floor for the Faraday cage. We have an 8-foot grounding rod in the center, and that's how we sprawled out the wire. I think it's like a 1/4 inch or 1/8 inch, I think around 1/4 inch plates, aluminum plates on the floor, and it's a bilayer Faraday cage with basically a capacitive layer. There's wood in between, and there's aluminum on the inside, aluminum on the outside, and they're both connected to separate grounding rods. This is inside the Faraday cage after we started setting it up, and we were shielding the wires as well because we were getting noise problems. And this is a thermal image. We have a couple thermal images coming up showing what was heating up in the sample. We expected the coils, of course, to heat up. They heat up very little because when we added more copper to the electromagnet, the total wattage to achieve the magnetic field, which was around 3,300 Gauss, that was necessary to have our more precession of the valence electron at 9.5 gigahertz. It dropped down to only like 15 watts, so there wasn't much energy being used to power the electromagnet, which was that was good. There was a little bit of temperature rise in the sample, which indicates that we were getting something, but it was nowhere near the 20 watts that we were outputting. There was probably around 1 watt that was entering the sample at most. It was around 46 degrees centigrade. You can see there at the hottest point. That was the point where the RF was directly hitting the sample. Isolator had a little bit of heat. We also used the heat sensor to find where there was kinks in the wire and possibly, RF feedback. And we had to take the wire apart to fix that. So infrared camera is something that's definitely useful. This was a new waveguide that I designed on the 3D printer, and we covered it with aluminum tape on the inside. That is to concentrate the energy more directly into the sample. Over here, we had a bilayer of aluminum that was protecting the scale from the RF energy. And then there's several layers of shielding on the scale because the scale kept on interacting with the RF in this chamber because RF is bouncing all over the place in here. And again, there's a bucket of salt water over here to try to absorb most of it. Had some really interesting wave patterns when we turn this thing on. Move anything ever so slightly, like 1/10 of a degree, and everything changes. It's like super, super sensitive with this setup. And you can see it from another angle. Jeremy named this the EPR NMR laminar spintronic alignment rig. That was our electromagnet. We still have this set up inside the Faraday cage. Okay, this is the equipment. We had an oscilloscope hooked up to the signal generator so we can see the pulse waves, pulse of on and off, and it's supposed to be at 5 milliseconds. So we had to hook that up to confirm that as well. And this was the final setup. Again, we have the shunt resistor over here to read our current. The current now is way down. It's around 3 amps and 4 amps and 4 volts of around like 15, 16 watts total. And we're measuring our millivolts over here as well. And we got the paper. This is a spy cam, so we're able to see if anything was moving inside the chamber. From a camera coming in. And it's all going in through the wall over here. There's these holes in the wall where we're able to stick all of our probes and our power into the chamber. We did see some results here as well. We got really excited one night when we saw like 50% weight loss, but that turned out to be noise from RF, and we had to shield it even better. But again, there is a possibility that what Alzafon saw over there was a noise from his microwave setup. So that's something to look into. This was about the limit of what we can do with the 20-watt system without going to the chamber idea that Tanya talked about. Next thing that happened was Jeremy Riss was searching on Craigslist, and he found this lab that was going out of business. And he started sending me pictures of all the shit they had over there for sale. And he sent a picture of this. It was a 5,000 volt power supply at 0.5 amp. And I don't know if any of you know this, but to find a power supply like this is pretty darn hard. I've never seen one before. And right away, what I thought was, get that piece. We need it. We're going to use it for power klystron. So they gave it to him at below scrap value. I think he paid like $50 for it. The thing weighs like 200 pounds. It's fucking awesome. He brought it down here to the lab, and sure enough, it was broken. So we had to fix that as well. It was actually the safety features. There's tons of like safety devices on here, so we had to remove all that shit and just make it run direct off this big variable, turn thing. It looks almost like a
there
safe.
Was like mice nesting in it, and there was a whole bunch of that was just terrible, man. It was everything in that shop was covered in mouse urine and mouse crap, and like we had to clean the whole thing out. It was pretty bad, but
yeah, we cleaned it up, man. We reversed the rectifier direction, and so we could have the inverted output polarity correct. The klystron needs a floating high voltage negative cathode, so it was not configured for that exact application. But hey, it does jack out almost 2.5 kilowatts at peak, so not bad.
Yeah, this thing is a beast. It actually running it here in the second lab, which is far away from our input power for the building. We were blowing fuses when we were powering this thing up. So it really is a beast. It takes a lot of energy. It's something that can power a Klystron. And there were tons of Klystrons on eBay. So we picked one up. This one was around $300. It goes up to 3,500 watts, which is more than our power supply can supply. So whatever, we got it. It's in the C band. And interestingly enough, when Jeremy went down to that lab to pick this power supply up, they also had a whole bunch of C-band waveguides that were all tuned to a very specific frequency. And these waveguides were tuned. I showed it to Tanya. She was like, "Oh my God, I feel bad for whoever tuned those things," because they were literally tuned to 6.281, way down. It had like 5 digits of the tuned frequency that can go into it, meaning that any frequency above or below will be pulled out. So that was a very interesting find as well. And we were able to hook it up all together and get a very accurate microwave output. Now, this, of course, means that we're only going to be able to control one side of the experiment, meaning the magnetic field will be able to change, but the RF is not going to be able to change. We're going to have the RF steady. And since it's a correlation between electromagnetic field or homogeneous electromagnetic field and RF hitting at the Lamar precession of the electron, valence electron, therefore that means we're going to need a very accurate power supply, DC power supply, to run the electromagnet. These are the components. This is a channel selector. We didn't end up using this. Here's it from several different angles. It looks pretty small. It is pretty small. This thing weighs almost 100 pounds, and it has extremely powerful magnetic fields. We can't get anything close to it. It'll pull, like, when we were attaching parts to the output over here, it kept on pulling wrenches in. It has very powerful magnetic fields. This over here was some aftermarket construction that we did because the wires were getting frayed. So we put on some Teflon and we put on some Kapton tape and then covered it all with high temperature silicon in order to protect the device. And as Jeremiah just mentioned, the power supply was putting out a positive output, and these need electron flow, so they really needed a negative output. So we had to change the polarization of the rectifiers in order to get a negative output from the power supply. This is what it's rated for: 8.3 kilovolts DC at 1.07 amps. So we're talking like 8,500 watts is supposed to be going into this thing to run it at peak power. That's a crazy amount of energy. Okay, here's some more pictures, and these are all the channels that are available. Oh, this is a great book on dynamic nuclear orientation that was recommended by David Alsfond. Picked that up as well. This is a waveguide handbook that I picked up on Amazon, and it is stock full of all these crazy long mathematics and stuff that I couldn't make heads or tails of. And when I was speaking to Tanya, who is our waveguide specialist, she said that most people don't understand all this stuff and just do everything off of experimentation, because there's so many variables and there's so many different components that go into waveguide engineering that it's really above anybody's head to comprehend. It's kind of stuff that's done on a computer.
You can solve the Helmholtz equation for that chamber, but theoretically, but does it really help you if you're off by a little bit? And you need to tune these things, and they really require like an art and finesse in the experimental sense.
Exactly. There's really no way around actually just doing it, because you can calculate the math to hell, and and then there's a 1/10 of a millimeter difference inside your chamber, and all that's out out the window. So everything needs to really be done manually. And what she recommended was to have a setup where you can move the panels in and out with screws, and then you would have a piece of what was it? A piece of carbon, like graphite, inside, and you just run the chamber for a little bit and check it with an infrared camera, and then you'll be able to see where the waves hit it and where it got hot, and then you'd know whether you're in tune or not. You also need a reverse forward and reverse power meter in order to know what's going on. None of this stuff is sold commercially. It's not it's all stuff that you have to pretty much figure out on the fly. This piece over here is the forward and reverse power meter, but it needs to be hooked up to these little guys over here, which are power meters in their own right. They're cross guides, so they're reading the magnetic component of the wave, and because they're offset, they can read the magnetic moment at different the magnetic component at different intervals along the tube. And we were able to see some numbers over here. I'm not really sure what they correlated to or how much power is actually coming out. This is a double isolating system that is meant for the C-band, and that goes into an input antenna that then went to a massive what do you call it? It went into a massive attenuator that was rated for like 50 watts or something like that into our signal analyzer. The last thing we want to do is blow up our signal analyzer. It can only accept 1 watt. That thing could put out several hundred or several thousand. So this is the rough setup that we had going on here. We also needed power for the tube itself. So and the power needs to all be floating because it's at a potential of 35 or 5,000 volts DC, negative DC. So you need to have a system to both power the coil, which is at 6.3 volts at, I don't know, like 10 amps or something like that. And of course, that was done with an RC battery, like a little lithium battery, and it's floating on a piece of PVC to shield it. And we have 2 buck converters that provided the power for the tube. And we can see this from a couple of different angles. Here's Jeremy and Jeremiah at the lab. I've got the Alternative Propulsion Engineering Conference sign just above my head right now. And yeah, here's the whole setup. Oh, also, I plan on using these capacitors over here. These are 10,000 volt capacitors. We're going to put them all in parallel. That's how they're wired up right over here. And we're going to attach them to the output of the power supply. And what that's going to do is when there's pulse, when we're doing running the final experiment after we get all the tuned waveguides set up, this will give us a little extra power because we'll be able to pulse it. It's going to drain the voltage and go back and forth, and we'll be able to get a little bit more than 2,500 watts available from this power supply, and bump it up a little bit. Pinky was inspecting it, and let's see what else we have here. Yeah, this is a side view of the entire experiment. Oh, okay. Yeah, so then here's the power supply. So this is basically the entire experiment. Over here, you can see it actually running. This is not the experiment. This is just testing the components because we're missing some components. And this experiment, by far, is one of the hardest experiments we've ever tried. If we were ever to, get successful results, none of these components would be used in an actual craft. We'd have a coil around the entire perimeter of the craft, which would create a homogeneous field line in the shape of a flying saucer, which kind of like makes sense why they are shaped like flying saucers, because that is where the homogeneous field lines are. And then we'd probably radiate the microwaves from the outside or inside the skin of the craft somehow. There's many different ways to do this. Another idea that we've looked at was the ARV, or the Alien Reproduction Vehicle. This was brought up by Mark McCandlish. There's a lot of speculation about it, whether it's a real thing or not, but this was shown to Frederick Alzafon, the inventor of this experiment. And he looked at it for a second. He said, okay, what's probably going on here is this is another way to create dynamic nuclear orientation. What's happening is the coil on the outside, this red coil over here, is being pulsed by these massive capacitors in the base, and alongside with the aluminum flywheel spinning, it creates dynamic nuclear orientation, which is contagious, by the way. It's not just like, we're not just making the flywheel weightless. We're making everything that surrounds it weightless as well. Think of it like electromagnetism. You have a magnet, and it magnetizes everything that's around it. Well, this is more like nuclear magnetism, where you're orienting the core of the atom, and that effect is also contagious. It also goes to everything that surrounds it, and therefore there's some other propulsion device in the craft that allows it to fly. So this whole thing is all about inertial mass cancellation or gravity shielding. Two different ways of looking at it, possibly either inertial mass cancellation or gravity shielding. Both of them are not really mutually exclusive, because you could run the experiment and see weight loss and say, oh, it's gravity shielding, or you could say it's inertial mass cancellation, but there is no experiment that can really differentiate between the two because of the gravity mass equivalence. So there's just two different ways of looking at the same experiment. And I've actually been contacted by lots of people about this experiment with all different theories about why it would work. It seems like everyone wants to throw in their hat on the theory side of why this experiment would work. But Todd Desiato and Wayne Ojala, who has a channel on YouTube called Fail Forward Research, definitely check him out, are the only people I know of, other than Hathaway, who's no longer working on this, who are actively working on these experiments. And we all communicate continuously, night and day, about the latest progress and what it is we're working on. So we called this experiment, Wayne came up with the name Easy Alzaphon, because it's a much easier way to do it. And here's a picture of that craft, or something similar to it, that was pictured by some pilot. So it's possible there was really a craft like this. Now, so for Easy Alzaphon, we need a aluminum disc spinning. So I went down to the Metalworks shop here in New Jersey, and we picked up some aluminum. And when choosing the aluminum, they asked me, what grade do you want? So I was like, okay, what's available? And started scrolling through it. And there was this one aluminum called 5052 aluminum. And if you check online, it has, I think it was like 96, 97% aluminum. And then there's magnesium, and then there's iron. And magnesium and aluminum have very similar properties in terms of acting as a reservoir for dynamic nuclear orientation, per Frederick Alzaphon. So they can be used interchangeably. And the iron is needed as well to act as the catalyst to bring the dynamic nuclear orientation into the core of the magnesium or aluminum. It's also interesting that it's called 5052 because it's missing area 51. So I thought that was kind of cute. We picked this up. They were balanced as well, and I'm here in their metal shop making sure that it was balanced properly, and it sure was. We spun it up to a very high speed. Next thing we did was make a coil for this experiment. Here it is. I used that as a bobbin. Didn't work that great. I mean, the wires are a bit of a mess, and it was a lot of work. And I have determined that in the future, if I'm making any more coils, it's a two-man job at the minimum, because you can't really do this on your own. You need somebody to hold the wire. You need somebody to do that. It's a lot of work to make these coils properly. There's some more pictures. That's the spool of 300 pounds of wire that we have here in the lab. And so we unspooled it. And there's all the disc sizes. I promised Todd one of these if he wants to try the Easy Alzaphon version of it. And here is the setup. It's actually right behind me if anyone wants to see it. We did try it 2 weeks ago with just a DC field on the magnet. There was some results, but it might have been air currents, so I wouldn't say anything is positive. But we then wanted to try with the pulsed magnetic field, and Jeremiah, and we use the high voltage capacitors, which I have over here as well, right behind me, to pulse the magnetic field inside the coil. And when I set that up, the high voltage was jumping in between the coil wires, meaning that it wasn't actually making it all the way through the coil. It was shorting to itself. Sparks were going everywhere. There was breakdown of the insulation, and the picture's not in order. We pretty much determined that the proper way to do it would look something more like this, where the wires are encapsulated in a very strong dielectric. In this case, they claim they used glass. We're thinking of using epoxy because that's what we have available. And epoxy and glass have similar dielectric parameters. And in order to do that properly, we need to get a proper bobbin. We need a separator. Jeremiah recommended we use fiberglass in between each layer of coil. And we need a vacuum chamber that can then suck out all of the air bubbles. So that meant we needed to get a larger vacuum chamber. And I'm just going to bring the laptop around over here. And I'm going to stop the screen share so you can all see what it is I'm talking about. Okay. So we got this vacuum chamber over here. It's quite a bit bigger. And it will be large enough, hopefully, to build this coil. This is the fiberglass. And we're just waiting on the bobbin materials that are coming in. It's a big PVC pipe. We're going to have to put some separators on either side of it in order to build this coil. It's going to be like a 2 or 3 man job. And once we get that going, we'll be able to take the experiment to the next level. Over here, we have the capacitors I was telling you about earlier. These are the ones that we were using for the pulse version. We also have 2 rectifier tubes that we're using for isolation, because we're going to be pumping energy into the capacitors. We are a high voltage power supply, but we don't want the when it goes into the sinusoidal phase, when it goes into positive, because it's a negative output. When it goes into positive, we don't want that feeding back into our power supply and blowing it up. So that was kind of important that we have isolation there as well. We also threw in a row of resistors. And this is the current setup we have over here. I'm not going to run it right now, but that's how far we got with the Alzafon experiment. Any questions? Any questions, anyone? Don't all jump at once.
I'm just wondering, Mark, have you done anything more with setting up your waveguides? The experiment actually be able to put a sample inside a waveguide configuration.
Oh yes. So sorry, I forgot to mention that. So we ordered some copper, and we're gonna plate it silver. I got the dimensions set up, and I sent it over to a machine shop to cut it, and I told them that the measurements I gave them are very precise. It needs to be off. It can't be off by more than 1,000th of an inch, and I'm still waiting for that to come back. And when it comes back, we'll be able to move to the next phase and start doing the experimentation. But I do have the forward and aft power set up with those 3 cross guides and the power meters, and those are working correctly. So it's a lot of work. Like you said, it's a lot of work to do something like this. And it's really like next level engineering to work with RF. Extremely confusing stuff. And thank you all. Yeah. Thank you very much. You've been very helpful. There's very few waveguide experts that I've been able to find that would talk to me.
And again, I wouldn't even qualify myself as an expert. I just have some experience.
Right. Yeah. I don't know if there is any experts, because it's almost a dying field. Like, who deals in this?
Well, in the military circles, there are people who have a lot of expertise in that sort of thing. And that's why I really like the idea of having some people on who may have connections with, some information about vehicles that really do exist already. Anything we can glean further from them would be really nice. But I think it's great you're trying all these things. I like what you're doing.
Thank you for all your help, Tanya. That was really helpful.
Well, and thank you, Tanya, for coming back as well, because we haven't seen you in a while, man.
Well, I'm usually here. I just keep I keep the video off because I'm rocking around and I'm eating and things like that. So, I've followed almost everything today. I thought it was a really great discussion today. Really good presentations. I really enjoyed it.
Yeah,
even the little, flare up.
Well, I was really excited to have David present. I mean, it was just that was just like a tour de force, you know. Now, the math, admittedly, you're way beyond me on that, but
I really appreciated David's presentation too. I actually started out in gravitational physics in my senior year of undergraduate. That was my planned course, was to go and do Kaluza-Klein theory, actually, the higher dimensional space-time idea, but I wound up going into experimental physics instead. So yeah, I really appreciate all the mind work that has to go into studying so many different theories, and so that's quite interesting.
There's definitely a lot of that, but I found, and Jeremiah has noticed this as well, and so has Tim, that there's many different experiments that have been tried with claimed positive results that all come back to this dynamic nuclear orientation theory, like spinning superconducting disks. Like, what is that doing on the nuclear level? Is orientation happening there? If you add a magnetic field, maybe there is. It all really comes back to the same experiment, which is something that a PhD physicist had written a paper on, peer reviewed, claiming later on that it worked. So I think that's to start with.
Yeah, and I'm based on my experience just reviewing experiments, and again, David touched on this. If I was going to say what does it come back to, I would say rotation. Now that could come back to the NMR thing, but I'm a little bit more general. I'm saying that the rotating, what I've seen is rotating magnetic fields. When you get these positive results, it seems like that is kind of one of the things that pops back up again, and again, I think David was saying that torsion was embedded in a lot of these other theories, and that was kind of what intrigued me with it, is this aspect of rotation. So now, again, that could be NMR, it could be related to it, could be the same underlying mechanism, but for me, that's kind of the piece. So
that's why it's really interesting about the magnetic energy converters. When you start to get into these energy devices, it's those rotating magnetic fields, and there's always a component that makes them seem less, less mass. There's weightlessness that comes along with those technologies. So that's something that I've been interested in for a while. I don't fully understand it, but I guess the first speaker was touching upon that too.
Yeah, rotating magnetic fields, I've heard a lot about that, and it would also fit in with this theory, because if you can rotate a magnetic field around a sample, then what are you doing to the electrons? What are you doing to the core? Is there orientation happening because the spins are aligning or something like that? It all seems to fit together with Alsfon, and I think there's more than one way to do this, probably more than a dozen ways to achieve the same result, which would explain why there's a plethora of different shaped craft out there.
Well, and if I could jump in again, and this might be off topic, but when you're talking about experiments, and for me, again, when you're talking about the mythology of gravity modification, right? I mean, obviously, superconductors made an entrance with Pogleonov, but one of the other ones that's always intrigued me is bismuth. And so I guess the two chemicals that seem to pop up again are bismuth and mercury. Mercury, it makes sense for so many different reasons, because it's a liquid metal. It has unique, physical properties, right? And so that makes sense. But bismuth to me never made sense. But yet it comes up again and again and again. And
there's something special about bismuth. It has some property, I can't think of what.
It's mildly diamagnetic, But what's also interesting was, let me see, I'm trying to think of some of the different things I've heard. I met someone who did experiments with it, and they said something about the E field when they were running current through it. The E field propagated strangely. It was like, they said the E field didn't propagate like it did with other metals. They were doing conductivity testing. And then the arts parts, right? That old UFO thing, which may be related to the TTSA, I'm not sure. Arts parts was supposed to be a bismuth magnesium bilayer. And actually, I had heard references about that with gravity modification going back before arts parts. So I thought that was interesting. And then, for what it's worth, taking it just a step further out, one of the theories that was out there was the reason they had these weird effects on the Philadelphia experiment was during World War II, when they were trying to put these ships together, I guess they were having lead shortages because they used it for bullets. So they were running bismuth in the welds. And so I think that was John Daring who'd said that. He said they would have had unpredictable results because it's mildly diamagnetic. And he said all the whole welds.
It's the most naturally diamagnetic material.
Yeah. Okay. Well, there you go. Now, I don't necessarily know if the diamagnetism itself is what does it. I don't think so, but maybe that's a
high spin too. It has a 9/2 spin ratio. Very few materials have that.
It's intriguing, isn't it? Though I mean, again, for me, I'm just seeing a pattern in the mythology. That's all.
There's a lot of mythology about bismuth. Also, something interesting about bismuth is it's kind of rare, and it's super cheap. Like you can buy a pound of bismuth for around $3-4. That's because the only known use for bismuth is Pepto-Bismol, which is like for upset stomachs. If we could find any usage for bismuth in anti-gravity spacecraft, buy bismuth because it'll become more valuable than gold.
Actually, if I could jump in really quick, rather than try and refine Pepto-Bismol, which I'm sure would be a nightmare, it would be interesting but painful, I'm sure. You can get, I believe, pure bismuth in lead-free deer shot or buckshot for shotguns. That's what they use instead of lead. So, and you can buy that and melt it down.
Yeah, there's no need. We've got plenty of bismuth. This is from Mark's private collection of bismuth.
Oh, of course.
But this is only a tiny sample of it. I mean, he's got about 3 times this weight. And this thing is freaking heavy. We've been screwing around with it, working on its crystallization formations and testing other parameters with it. We actually use some bismuth powder mixed in with a crete type compound, a type of cement, in between 2 carbon or graphite plates to test a variation of the Pockenoff pore experiment. But yeah, bismuth does offer a lot of really interesting properties, and it's pretty unique in terms of its diamagnetism. As far as a natural element, even though it's weakly diamagnetic, it's still important to point out that it's one of the strongest diamagnetic natural elements that we have.
Now, it's possible, though, that if it does play, like, again, with arts parts, maybe the role that it plays has nothing to do with the diamagnetism. Maybe it has to do with it functioning as a metamaterial, right? I mean, if you
I
put it
very
in
much agree with that. Yeah, diamagnetism may just be an interesting property of one of its many properties that we have not yet discovered because we haven't really taken it through its paces and seen what it can do.
Yeah, I mean, because I've met people who've experimented with it and haven't seen anything. So
Rob Chambers just mentioned something that I noticed before. Bob Lazar got all excited about element 115, which isn't stable, by the way. But right above element 115 in the same family, the first element that's actually stable is bismuth.
Okay, well, there you go. Yeah. So it checks all of the boxes for UFO conspiracy theory materials. You know, we're set. Now, whether or not it actually does anything is another story. But as far as mythology goes, it's the Holy Grail.
Right. Another thing that I didn't touch on yet was the this was my take on the Alzheimer's experiment of like the theory behind it, and I'll get into David and Frederick's Alzheimer's theory after that. Basically, this is something that I asked Jack Sarfatti before. He didn't have an answer for it. He said that it's impossible to get rid of inertial mass. So I had asked him, where does inertial mass come from in the first place? Answer that, and then you can tell me that it's impossible or possible. Well,
equivalence principle. That was his answer.
Well, there is an equivalence principle with gravity. We know that. But well, let's say let's look at the core of an atom. That's where all the mass is stored. So what's in the core of an atom is a whole bunch of electromagnetic fields that are spun in on themselves. That's what protons and neutrons are. So what do you have? What happens when you have these fields that are, electromagnetic fields that are spinning on themselves? You basically have gyroscopes or complex gyroscopes. It's not just one spin. There might be a spiral and then coming back. There can be all different variations of what's actually happening there. But ultimately they're spinning. And second law of thermodynamics states that everything is going to a state of higher and higher entropy, more and more complex, variations, randomness. So I would assume that in the core of an atom, you probably have lots of random spins going on around. So if you were to like take a baseball, for instance, and you throw it, the inertial mass, the inertial thrust that you're giving that baseball can be converted into energizing or slowing down the subatomic spins in the cores of all those atoms inside that baseball, and that's where the energy is being stored. So if the and because there's so many random spins going on in the core, therefore the inertial mass will be equivalent in all directions. But if you were able to orient the subatomic particles in the core of the atom, then along its plane and axes, the craft will be essentially weightless, but only along its plane and axes, which explains why flying saucers were seen to like slowly tilt and then they shoot off along the axis, or they can fly very rapidly along their plane. Seems to correlate with this theory. And you basically, by orienting all the subatomic particles in the core in the craft and its surrounding objects, you also make surrounding things weightless as well. And David Alsfon or Frederick Alsfon had a different theory. Todd, we'll get to yours next. I know there's more than one theory, more than two. And he said that gravity is also coming from the core of the atom, and we know that there's randomness over there in the core of the atom. So if the field is, the gravitic field is emanating from the core of the atom, and the core of the atom is random, or the spins are random, so you'd expect the gravitic field to be, completely random and incoherent. By creating coherent matter, which is what we're doing, we're getting all the spins aligned, gravity will then have to do work on the craft in order to make it incoherent, in order to attach to it, in order to react with it, and that essentially cools down the gravitic field. Also, and it's important to note, this effect is not immediate; it's a build-up effect, and over time you slowly build up the dynamic nuclear orientation of the craft to a point where you're losing more and more weight or inertial mass, and then you're able to use a secondary system such as light, or there's M drive, and there's a lot of other potential methods to actually create the thrust that's needed. But if you only weigh 1% or less of the weight of the craft, the thrust necessary is negligible. Todd, you were going to say something?
Hector might be. He had a bunch of comments about bismuth. I don't know if you're open to that or not, but Hector is pounding them out in chat right now.
I was just going to mention in terms of origin of mass that, it's related to superconductivity because we don't understand the mass of the Cooper pair. So you get two electrons that pair up and there's this additional mass that is acquired, and no one understands that. So you could say it could be related to what's going on for inertial mass, like how, the question that was asked to Jack, how does that come about? And basically through the conformal gravity, it's related to like holography as well. Randall Mills had his soap bubble thing. You could say that there's like some things stored on the boundary of that soap bubble and say it's a hologram, right? So this origin of mass thing will relate to superconductivity, and it's about understanding how basically it's like a phase transition of the quantum vacuum itself. So someone's got to figure that out at some point. And at really high energies, mass doesn't matter. So effectively, it gets to a point at really high energies, everything's massless anyways. It doesn't matter. And so that's effectively a different phase. And when you cool down from that, and in the early universe, as you start expanding, eventually there's a phase transition that occurs and particles acquire mass, just like the Higgs mechanism in electroweak theory. And there's a gravitational Higgs mechanism that is, very interesting, and people are just starting to figure out in academia maybe how that connects to, visible reality. So once that happens and people figure it out and really connect it to superconductivity, that could help. But who knows? That could be 5 years away or 100 years away.
Or 50 years in the
Yeah.
past.
Yeah, that as well. There's a lot on the internet. I think most problems have already been solved. It's about putting it all together.
Yeah.
Yeah, and a lot of digging.
Well, Mark, yes. When you have a bunch of spinning particles, spinning charged particles, all compacted into a nucleus or a matter, and you accelerate that matter, according to Lamour's power equation, the amount of power radiated has to go up. Well, that energy has to come from somewhere. Well, it comes from the work you're doing to accelerate it. And so that power being radiated away, that is the dissipation that I'm talking about, that Jack's talking about, that, I'm talking about damping in my model. But it's that when you try to accelerate matter, you excite it, and the Lamour precession frequency goes up and it radiates more power. And it's the same as what I was saying before to David, is when you lift something in a gravitational field, you're exciting the particles, their acceleration goes up, the Lamour frequency goes up, you're opposing time dilation, and you have to do work to give it that energy to do that. And so that is the same. Gravitational mass and inertial mass are the same thing. And that's how it works. Now, to nullify the weight in this model, you have to have a pump. So you use the magnetic field to pump the frequency up to a very high Lamour frequency, and then let it free fall in whatever direction you're directing that gradient in the magnetic field. If you direct the gradient upwards, you'll free fall up. And it's the same as being massless.
Okay. Another thing I just want to explain to everyone, what we're talking about by Lamour frequency is the precession of the precession of the axis. Now, like Earth has an axis, it's 23 degrees off the sun's axis, and it rotates around itself every like 25,000 years or so. What they call it the precession of the equinoxes. So that is what we're talking about with Lamour precession. Also, there's a lot of different Lamour precessions because you can precess the core of the atom. If you're precessing the core of the atom, it depends which atom you're talking about. If you're talking or molecule, Todd is working with water, deionized water. It has a different Lamour precession of the nucleus than, let's say, bismuth. Yeah, there's a chart. And also for the unpaired electrons, or for the valence electrons, it's all the same. It's 28.025 gigahertz per Tesla. But if you wanted to go for a different row of electrons as you get closer to the core, the frequencies change. I believe they go up. And there's a lot of different Lamour precessions that we can hit. Todd is working in the megahertz range, which directly interacts with the core. And I'm working in the gigahertz range, which works with the electrons, which then interact with the core through hyperfine coupling. So there's many different methods of trying it, and there's also the one where you're not using any RF at all, you're just spinning it around, which is easy alzaphon, as we call it. And that method is probably a lot cheaper to replicate if anyone wanted to try it, but it's there's a lot of problems of having a craft with a huge spinning disk in it, which we don't really have to get into. Obviously, the craft will spin in the opposite direction, and you'd have this huge aluminum disk spinning around. So there's a lot of disadvantages.
The gradient in the acceleration of those atoms, and it'll cause them to precess at higher and higher power depending on the acceleration, which depends on the radius on the disk that's spinning. So it's a cool experiment. I'm anxious to see how it works out.
If you want any of these discs, to try it yourself.
I may want a smaller one. Mine's like 24 inches in diameter.
Well, we have 3 different sizes. I have the size over here, which is around 4 inches, and we have a 6-inch disc, and we also have the much larger 8-inch discs. And
I have Or 24 inches because I was making an energy storage device flywheel. But
what kind of aluminum is it?
I'd have to check. I think it's 6061.
Well, you have to check what 6061 is made out of and make sure that it's appropriate.
If it was pure aluminum, I'd be fine because aluminum would precess. I mean, it has a precession more frequency, so it's got an angular momentum already, so it should work.
Okay, we can try them all. The problem is making that coil. I was having a conversation with Jeremiah. If you can unmute yourself, Jeremiah, about the one. Well, we were having a conversation with Todd and Jeremiah about the coil configuration for the pulsed application of easy alzaphan. And
yeah, I was thinking about that too, Mark. And the specifically the thing that you haven't mentioned yet that you're really on about, and Todd pointed out, is the angle of the taper of the coil. This really important factor of a diversionary gradient field being produced by that coil. Let's talk about that.
Yes, yeah. Todd was mentioning in a comment earlier that you would want the field to be stronger on one side than on the other. And I was looking at the ARV picture, and I noticed, hey, the coil is tapered. Would that, would that produce that effect? And Todd was like, yeah, it probably would. Another way to do it is to offset it. But if you had a tapered coil, exactly as is shown in the ARV picture, it should produce some sort of effect. And that is how we plan on doing the next coil. When I get all the components in, and we'll build that coil. It should look really nice.
Yeah, and having a
Go ahead,
loop
Todd.
have a strong magnetic field gradient because the field drops off like 1 over z cubed. So so it'll have a very strong gradient above the coil, which is what you want.
Yeah, it'll be interesting, Todd, to see your results too, because you're going to be able to test that gradient field in a more specific and refined way. So that will actually give us valuable data to assess engineering futures.
Robert O'Keefe wrote that he assumed that off-world technology would not have the same periodic chart. I would disagree with that. I think the only common denominator of our entire universe is our periodic chart, but they would have different different variations of the different makeups of the materials of the
isotopes.
Right, they would have different isotopes depending on which supernova created their solar system. So that is a possibility. There's different types of supernovas, different energy levels create different elements, and different age can create different isotopes, some of which are radioactive. Also, something interesting that Jeremy brought up about NMR and EPR is that the people who were involved in this in the early stages were then taken on to work for different secret projects, with the secret space program.
Yeah, Edward Mills Purcell, he won the Nobel Prize for NMR, of course, alongside, I think, Felix Bloch, and both of them had security clearances and did other classified research and stuff for Atomic Energy Agency and also EG&G in Area 51, believe it or not. Purcell headed the CIA's Project Rainbow, which was their whole study on radar reflectivity and electromagnetic frequency response in order to study and understand radar and radar return signals and that sort of the whole physics, the core underlying physics behind those principles. They're the ones that came up with that formula for radar signatures and returns, and that was the basis for the stealth fighter and understanding a lot of the physics that led to stealth technology. Of the existing stealth technology that we know about publicly, not including some of the more advanced stuff like the paint and these phase conjugate mirrors and these phase conjugate paints and stuff. Which there's been a lot of research and stuff into that, and I know that those phase conjugate materials and some of the microwave phase conjugates were part of Project Skyvault, which is mentioned in Paul Laviolette's book on Secrets of Anti-Gravity Propulsion too.
And Paul Laviolette was on the call with us today too, briefly.
Oh,
yeah.
really?
I saw him pop in, and I'm not sure what time he peeled out at, but he was here. So.
Oh, we would love to have him on to do a presentation. Also, something else that Jack erroneously said, that it's impossible to shoot these craft down. I call bullshit to that, because it was done in 1947. How was it done in 1947 with Roswell and the previous crash? Well, they turned on a new form of advanced radar. Now, what is radar? Radar is pulse microwave wave.
How do you know this, Mark?
I'm not sure exactly where I read it, but I think it was in The Day After Roswell by Philip J. Corso. They talked about
you're so smart, why do you smoke cigarettes? I'm just kidding.
You know who would know this? Ron
That's a good question. That's it.
Remembers the case of the microwave measurements that were being done on that craft. I bet you he has this memorized and knows exactly where the report came from.
Well, if you were to hit a craft that works using microwaves to make it weightless, so it really doesn't have much of a propulsion system. If you were to hit it at its Larmor frequency, which it's broadcasting to the world, you would be able to interfere with its weightless system, its inertial mass dampening or gravity dampening system. And so long as you interfere with it, just at 1% or whatever, you suddenly make the craft a lot heavier than it can propel, and boom, it'll crash. So
Mark Fiorentino said he thought he heard the craft was hit by a lightning bolt as it flew through a storm. But
I've heard that theory as well.
I do think it's interesting. Like now, if the craft is invisible, then that does present issues. But that's why I thought like lasers might be the way to go. If you were going to try and shoot one down. Although I don't want to sound, I don't want to sound too militaristic. I guess it just, it's an intriguing question. That's probably all.
I just wanted to add that since I've been reading up on triangular UFOs, a lot of them fly very low, so they're below the radar level. So I think that's one way they avoid getting hit by it.
Well, and one of the things that's really interested me is, and I've again, these are all rumors. All of us have heard these in the past, but Frank Milburn had mentioned underwater UFOs, right? That submarine captains are reporting, and this was in the part of the Begum Sadat report that we did the interview on yesterday. That was kind of intriguing also. And I thought, well, there are a few different reasons that you might want to do that, but one of them would be stealth, right? That'd be a way to remain stealthy. So.
Also, something that David Alzafan brought up, and I haven't been able to verify this yet, is that through dynamic orientation, it is possible to make the craft invisible as well. If you think about why are things visible in the first place, it's because they're interacting with the electron field. They're not interacting with the nucleus. So if you can orient the electrons well enough, then from certain angles, not from all angles, the craft will become invisible to light. Light would just travel right through it, with some variation around the edges where the dynamic nuclear orientation isn't as perfect, which is pretty much what we see.
I think that's the first time I've heard that, Mark, that it actually made sense to me.
Oh, he mentioned it a couple times in the.
Oh, I know he mentioned it. I guess I never quite ran through it in my head to grasp the concept of why. Should have been paying more attention, I guess.
I think that these
isn't that always the case?
Yeah.
These overlaps that we are noticing between the research that's been done into invisibility and also nuclear magnetic resonance and just this idea of the core of physics. Really, this is the core of physics, Wheeler-Feynman absorber theory and stuff. I think that these are great questions, and this is a great direction for this whole conference. I just thank everyone for being here and taking part of it. We're nearing 5.5 hours on the stream, the live stream, and I think the last one I did shut off after 5.5 hours.
You know what? I think I should probably go. So I think it's probably time to close up shop for this evening.
I could go for another several hours. We'll start a new one and keep going. Saturday night.
More power to you. Thanks, guys. I'm signing off.
Our human stocks are down 50% since about an hour ago, so it probably is a good time to close out. I think most people have already gone to dinner. But yeah, thank you again for everybody.
Yeah, I will end the conference then. Thank you to everyone. Todd and Mark, thank you for presenting there at the end, both of you gentlemen. And thank you for everyone who attended. This has been a surprising conference, and I think we gathered a lot of new perspectives. So
it was great to have David. I want to see more of those gravity research guys come back on for the quantumgravityresearch.org. Those guys, that was awesome to have David Chester on today. He really hit the ball out of the park.
Thanks, Dave.
Yeah, thank you. Appreciate it.
Okay,
well, I'll say it again publicly real quick. Hector, we would love to have you on at some point if there's anything you can talk about. We would really love to hear what's been going on for the last, 15, 16 years on all your research.
And I know there's a lot that he can't talk about.
I know he's got investment in it, and there's vested interest in it, but man, there's got to be something. I mean, he knows so much, and it can't all be secret information about his tech and their company's tech about Gravitech. There's got to be something, right?
Yeah. Well,
he knows too much. He does.
Okay, so that's it for today, guys. Thank you again, and have a great weekend.
Take care. Peace. Live long and prosper.